Good morning, and a warm welcome to everyone at the ICRA workshop on scalable autonomous driving. My name is Chen, and I'm an applied scientist at Wave, where my work focuses on using embodied AI to tackle the self-driving problem. So, I would like to begin by explaining why we organize this workshop. If you're following the field of autonomous driving, you have probably heard so many times that the predictions that self-driving car will be solved in 2 years or next year or decades. However, it's already 2023 and we haven't seen the fully self-driving car scaled all over the world. And this year is a milestone as it has demonstrated how fast a technology can scale and change our lives. It's apparently that the challenge of autonomous driving is very unique. The complexity extends beyond the technology domain to including regulatory, ethical, and safety consideration. And today, we want to open up the discussion what technology challenges that need to be solved first, and how can we leverage the latest research to accelerate the larger scale deployment of autonomous driving. And we are honored to have 11 speakers representing both academia and industry who will share their insights and approaches towards improving the efficiency, safety, and scalability for the next generation of autonomous driving. We also have 8 outstanding papers on the topics ranging from leveraging novel sensor fusion to utilizing generative models for scene generation, all aimed at robust and safety of this autonomous driving. These works will be presenting as posters outside the conference room. Here's today's detailed schedule. We will have 4 guest talk sessions and 2 coffee and poster sessions, split between morning and the afternoon. At 4:30 p.m. today in the afternoon, we will hold a panel discussion, aiming to have more interactive discussion on the scalability issue of autonomous driving. The day will conclude with closing remarks to wrap up our insightful discussion. And finally, I would like to express my gratitude to the organizing team for their great work in putting together this workshop. Also, special thanks to Wave for encouraging this initiative and sponsoring my registrations. And thank you all for being here today for so early. And let's begin this exciting journey by introducing our first guest speaker, Yuning Chai. Dr. Yuning Chai is the head of AI research at Cruise and formerly a staff research lead and manager at Waymo, with a focus on perception, simulation, and prediction. Dr. Chai has built a strong reputation in the area of computer vision and machine learning and autonomous driving through his research publications, as well as his organization of CVPR workshop on autonomous driving and the Waymo open dataset challenges. It's all yours, Chai.
Let's get started. Well, thank you for the wonderful introduction, and really excited to be here. And I'd like to thank organizers of the workshop for this opportunity. And I'd like to apologize at first for not being here in person. I would have loved to come to London. I actually lived in the UK for 4 years. And, the UK will always have a special place in my heart. Anyway, let's dive into the basic topics. So I'd like to first get slides on who we are as a company. So we are a self-driving car company based in San Francisco, build self-driving cars, ride-hailing, delivery services, and we were one of the first to deploy driverless, and especially here in urban situation like San Francisco. Been doing this since 2021, and just to re-emphasize what driverless means there are no safety drivers, literally nobody on the road of the car. Our customers are not liable to damages caused by collision and other unfortunate events, and we're doing it at scale in San Francisco, and we are open to members of the public. So, because today's theme is about scaling, I thought I'll pull up one slide that I had during the presentation last year. There, I highlighted how we thought about the scaling process. So it was not a 0 to 1 from the very start. We didn't just release like thousands of cars onto the road, but rather we started. So when we launched the service, we only had 2 cars covering a small area in San Francisco. And we were also just driving at night because there's not much going on at night. It's a lot easier. So then last year in May, we scaled up to tens of cars covering 70% of San Francisco. And then during New York's time, we already were up to over 100 cars and covering 90% of San Francisco during the night and 30% of San Francisco during the day. And back then I promised, okay, soon we'll have 100% of San Francisco covered. We'll be driving 24/7 as well. So is that true? Yes, indeed. So we are now in, I guess, June in 2023, and we are now covering 100% San Francisco 24/7. And actually, in addition to San Francisco, we also managed to scale to other cities. So these are Austin and Phoenix. Oh, sorry if the slide's a little bit small. And we always had the assumption that because San Francisco is so challenging, once you are okay in San Francisco, it's easier to scale to other cities that are not as challenging in San Francisco. I mean, I have a video later. In San Francisco, we really see a lot of crazy stuff. And that assumption turned out to be not far from the truth. So we kind of have a fairly easy time to scale to these new cities where the roads are a lot larger, fewer pedestrians, fewer bicyclists, and just easier situations overall. All right, and we've also announced we're expanding to new cities that are Houston and Dallas. These are some of the most popular cities in the US. And we are also excited to introduce the next generation of hardware that's fully customized just for the self-driving car purpose. And it's not retrofitted on some existing cars. Right, enough about the business side of things. I mean, we are here to talk about technology. And I'd like to highlight this diagram where it's basically how every self-driving car company iterates its software stack. How it works is fairly intuitive. You have a software stack, you want to improve it, you drive on the road, you encounter problems that leads to kind of analysis, classification, and you do some data collection in simulation or real data mining, you do some auto labeling and so on, you retrain your system and you deploy it back. So this is essentially the iteration that everybody here probably is fairly familiar with. And what everybody is doing is essentially improving different parts of the stack. Right? People can be working on auto labeling, for example, here. So you can have cheaper labels. You can be working on optimization, quantization, really hardware-specific operations. Right? Maybe your hardware doesn't work so well on transformers. Now you have to figure out that. But today, I want to talk about 2 aspects of things. One is on this end, where you try to collect problems. And if you were just do it organically on the road, so you see all those self-driving cars. I think probably in Europe there are many self-driving cars in testing as well with a safety driver. So essentially, what people are doing is to try to figure out where the stack fails, right? But the challenge here is if you were to do it just organically, just wait for things to happen, it's unlikely to be sufficient. First, we are trying to identify super long tail events here. And we find one, we probably can fix them, but then there's the next one. It never ends. And in addition to that, the world is an ever-changing place. So you fix one problem, tomorrow there might be something that completely new. Maybe there's a new TikTok challenge that makes everybody dress like, I don't know, Lego figures. So, these long tail events will happen. Now the challenge is, how do you prevent it? How do you proactively make your system so robust? You have a testing framework that can catch these vulnerabilities before they are on the road. So the second topic is very related to this. So once you have figured out, hey, I know these problems, I'll then try to fix those, collect data, and so on. And now the second question is, how do I improve my models? And this is a continual learning process. Because you have an existing model, now you try to add something new. And what are some efficient ways to do that? And that's kind of very important. You don't want to train from scratch over and over again. All right, so let's start with the first topic here. So yeah, I promised you this video earlier. So I'll just let it play in the background. You can see all kinds of craziness that we encounter in San Francisco. And you have, people, bikers like that. You have, this fairly special vehicle. You have fallen trees, boxes, basketballs, people on a skateboard while playing a guitar, and all kinds of things. So the question is really, how do you prevent, how do you test your system against these things before you see them on the road? I mean, it's always easier to solve a problem in hindsight. Once you have already encountered this issue, then you can say, okay, now I can fix it. But now that's not sufficient for AB. Right? So the idea here is borrowed from this literature called adversarial sample generation. It's a relatively old technology. The one seminal paper here is from Christian Szegedy, where they argued, hey, you take an image, and you can, if you know the model, and the model is fully differentiable, then you can generate an image that's indistinguishable from the first image in the human eyes, and that will make the model fair. And the underlying idea is fairly simple. So you have some kind of input. It can be an image, but it can also be anything. Right? Especially in self-driving work with the kind of behavior data that's in the top-down domain. And you have a neural net that's fully differentiable, and you have some kind of loss. And what you can do here is to propagate the gradient of the loss with respect to so usually during training, we want to minimize the loss with respect to the parameters in the model. But here, you essentially compute the gradients of the loss with respect to the input. And what you get are these noise images, and that you can add to the original image, and suddenly the model thinks it's no longer a dog. But unfortunately, if we were just to take this literature and apply it to the AB use case, it's not that useful when you think about it. Because sure, you found a vulnerability in your model, but the chance of finding a cat that looks like this is very small. So equivalently, it's like saying, okay, I generate this impossible scenario for the AB to solve, but the chance of this scenario that us getting into that situation is practically zero, because I'm essentially optimizing, I'm overfitting to the model parameters in order to generate the sample. So the sample itself is not robust either. So what is some things that we can do to improve based on that literature? What we can do is really to regularize hard on this model. And the way we do this is to say we split the model into an encoder and a decoder, and we have a very low dimensional bottleneck in between. and that serves as a regularizer. And now everything else is fairly similar to before, but now instead of propagating the gradient all the way to the input, you would only propagate it back to the embedding, and now you get a new embedding that you need to decode. And how, it's a little bit more complicated than before. Now you need some sort of autoencoder. So if you follow my my pointer here to go through this path, this is essentially an autoencoder, and that you can train. And here, if you decode the one where the noise has been applied, you'll get something different. So here, there's usually no guarantee that the decoded image will be in the domain of natural images. So, I mean, there's a chance that just work out of the box. So there's some literature on that doesn't apply a discriminator, but especially for images, a discriminator is almost necessary, because otherwise there's no guarantee that this thing will come out as a natural image. So now, here are some examples just on sci-fi images. Sorry, the image is a little bit blurry because they are 100 by 100 pixel images. So on the left-hand side, so we have two columns, and on the left-hand side, you have the original images. For example, you have this ship, and you can ask the model, how can you make a dog out of it while changing it in a more semantically meaningful way? It's not just flipping a few pixels or just adding a noise image, but rather we are changing the overall semantics. So to a human, this also is more interpretable. So you can see why the model thinks that this is a dog, because the front of this ship became the ear of a dog, and the seats over here became kind of half of the face of the dog. So essentially, you have an array. You can generate an array of samples that lie on the cusp between a ship and dog. And then what you can do is you can say, okay, yeah, these are really critical samples, and we should be able to cover them as ship, because in self-driving context, it's slightly different. Anyway, I mean, these are mostly human interpretability. Is what we are aiming for here. And again, here, if you can, so here, changing a bird into a horse, right? The kind of tree branch became the neck of a horse, for example. So now, this is AV workshop. We need to apply this for self-driving cars. What does it translate to an application in self-driving cars? So here, we're looking at essentially testing at the behavior. And so this is nothing to do with perception. So everything is already a top-down representation. You can see, so how you look at these images is, this is a top-down map, right? This is intersection. You have the cyan agents are agents that are not really interacting with us. The black agent is ourselves, it's a self-driving car. And the yellow agent is what we are interested in kind of modifying. So this scenario by itself is not that challenging for the AV. It's just a regular intersection. The pedestrian walk through the crosswalk, and the car started driving. Now your question would, so what we're trying to do here is to say, how can we change the trajectory of the yellow agent so it poses a threat to the self-driving car? And ideally in automatic way, don't want to have really human involved in this. So what we can do, so as you can see here, right, so we essentially, the blue one is the one that we've modified. So what happened here is, in both cases, the generated agent is suddenly slower. So it's slowed down at the very start of the scenario. And that posed a challenge to the AV, because AV thought the agent would kind of walk through the crosswalk. So in these scenarios, the agent, the AV itself, is kept on rails. So essentially, in order to prove that we found a challenging scenario, we would feed these scenarios back to our simulator, where the AV stack itself is simulated as well. And that will validate if the AV indeed has some vulnerabilities in these areas. So here, yeah, similar example. the blue agent, the modified agent side is slower, and we need to make sure that the AV can handle it well. So the trajectories are not the only things that we can modify here. Technically, we can modify everything. We can even modify the map, although it's questionable if we're just driving in San Francisco if that's necessary. So here we are also modifying the initial condition of the scenario. So essentially, the blue agent now starts a little bit to the left of the right agent, which causes this, and it's walking off the crosswalk as well. So that creates this situation where the AV comes in fairly fast, and can the AV stop in time and react in the correct way? On the right sample, essentially the pedestrian is making almost making a 360 degrees turn here, and just dancing around in the crosswalk in the same kind of. It also poses a challenge to the AV stack. So something to note here is that finding a new unknown long tail scenario that the AV struggles with is so expensive and time consuming. So with this process, even if 1% of things we generate creates a challenging situation for the AV, it's still a win. So we are not really required to, some scenarios, you can modify it as much as you want. You will never create a true problem for the AV, but some of them will, and those are the ones that we are after. All right, so much to adversarial scenario generation. So we'll probably leave some time for questions at the end of the presentation, so I'll just continue with the next topic. So here, the next topic is about continual learning. So now you've found all these new long tail problems you want to solve, and you go collect data, you do everything right. You have to improve your model now, be it perception, be it prediction, be it planning. These days, a lot of machine learning components in our systems. So continual learning is about having a good starting point that has already worked well. Now you have to add new task or new data into this model while trying to not forget what you learned before, right? So in the literature, there are a few ways to do that. So the first way is through multitask learning, where you say, okay, I have a new task or new data. I'll mix it with my old data, and I'll just keep training the model. The problem here is that usually your old data is very large, and your new data is just a small part that you discovered. So that creates there's a strong imbalance in this training itself, and it's very difficult to tune the hyperparameters in a way that either the new data will dominate or it will be dominated by itself. So ultimately, a lot of times, if you do this, the new tasks are poorly trained because it's just so overwhelmed by the old data. And another problem with this paradigm is that you have to keep the entire old data, right? In self-driving, we collect so much data, we train the models with them, and then we can't really keep all the data forever. And a lot of research here in the literature has been to distill exemplary data from this large corpus of old data, essentially finding support samples, if you will. But still, it doesn't change the fact that you still need to keep the old data intact in order to move forward. And as time goes by, you'll always have more and more data to keep. So that's a problem. So then what people came up with is what they call model anchoring, which is to say, okay, instead of, I don't want to keep all the old data, and instead I want to just keep some old statistics, and that will guide my training and to make sure that my model doesn't deviate too much from the old, essentially the old model. So the problem here is that it's difficult to chain this multiple times. So a lot of time, because it's continual learning, it's not just once. You're not doing this once. You're doing it multiple times. So this is kind of somewhat undefined if you were to do it multiple times. And on top of that, this has a high bias, and it requires a lot of data engineering as well, because now you have to compute all those statistics, and you have to now compute these offline somehow, and then pipe them back to the training. So it's fairly complicated to have this system set up. And even then, as mentioned, it's kind of difficult to maintain because in order you can't do it in a loop. So essentially what people mostly do is just the simplest thing. People say, oh, this is way, everything else is too complicated. Let's just fine tune the model with the new data. And we just lower the learning rate to nothing. And we just train a little bit and fingers crossed that we are not moving too far away from the original checkpoint. So that then leads to, essentially forgetting, right? Even if you keep your learning rate low, there's really no guarantee that you'll kind of get to a good place that's not too far away from your original checkpoint. So let me just explain how this works. So the traditional fine-tuning, you start with a pre-trained checkpoint on the old data, take one step. On the new data, you take 2 steps, take many steps, and you end up here. And now you have to take one more step. Obviously, you compute the gradient, and this is the step that you want to take. But now you see the problem, right? There's really no, as mentioned, there's no guarantee. So this, essentially, the discrepancy between these new checkpoints and your original checkpoint, that leads to forgetting, because you are always moving away from your original checkpoint. Well, most likely, you're moving away. And as the more you move away, the more you forget from the original, the checkpoint. So how can we fix it? So we have created kind of a fairly elegant way to do it. And as mentioned, the key here is to just say, okay, we want to go here. So the new data wants to go here. But the old data, it's kind of requires something that we need to go back. So if this checkpoint is well trained on the old data, so going back is always a good idea, right? If it's a local minimum, then this Tn is not too far away. So going back is always a good idea. So now you have 2 good ideas, and that seems to be just very, this is another multitask learning problem. And there are a lot of literature to that, and one of them is what people call PC grad, essentially to say, okay, here I have 2 gradients, 2 directions I want to go, and in order to find the right direction, what I do is I first do a scalar product. If they have a scalar product that's larger than 0, I'll project my new gradient onto delta, and this is the direction I go. So you might ask, hey, yeah, we're doing multitask learning again. So how is this different than this type of multitask learning? So the difference is really in the keeping of the old data, right? So previously, we had to keep all the old data that we trained the original model on, and that just creates problems. And here, essentially what we do is we don't need to do that anymore, because the entire old data is essentially encoded in this model and encoded in this direction that we want to take a step in. In the interest, I'm already out of time. In the interest of time, I'll just go quickly over the results. So yeah, this is direction we want to move. And you can either move directly from N, or you can say you move from T0. And obviously, this is a little bit slower. But when you do fine tuning, typically you have very few data points anyway. So just the efficiency is not the most important thing. Just for example, quickly going over it. So we're trying to. So we have. So this is old data. So it's a 2D regression problem, and we are using a 3-layer multi-layer perception for this to estimate these functions. And the goal is to estimate the full data distribution. And if we were to just use the original data, obviously we don't have this pattern. If we were to do fine-tuning, we'll get something horrible. And really, this method can still generate something that's very similar to what we want. And quantitatively speaking, we are a lot a lot closer to the truth as well. So we can apply it for things like image classification, where the old data are the common classes, the new data is long tail classes. Here again, I'll go quickly because I'm out of time. But you can believe me if I say, okay, the green curve is better than the red one. So finally, we also apply this on motion forecasting, where the old data here is the prediction on cars, and the new data is prediction on pedestrians. So this way, again here the green curve is what we have, and the other curves are traditional fine-tuning models. So just to wrap up today, I covered two topics. One is adversarial scenario generation, one is continual learning, and there are still a lot of remaining challenges, especially in the generation side, where people these days really care about realism and fidelity. But I think one important thing, this also applies to the entire generative AI stories as well, is the modeling of the distribution. And that's what we really care about. Right? Having one scenario is not that difficult. Having a distribution of scenarios where you know the probability distribution over them, that's the true challenge. All right, I'll wrap up here. Sorry for being over time.
All right, thanks, Chai. Any questions for Chai? All right, okay, Luca, come here.
Hi, thanks for the talk. It was really great. I had a question on, I imagine in the example of generating adversarial cases for trajectory, where you showed the trajectories, you mentioned you want this to be risky. How do you define this risk? Is it something that leads to a collision? Is it something that leads to some sudden steering or bad behavior of the AV? And how do you make sure that you generate examples that are also somehow realistic?
Yeah, thank you. To the first question, the scoring function is kind of out of scope of this work because you can use any arbitrary score here. So here we use a combination of a lot of a combination of proxy measures like collision distance for the time to collision, comfort, some comfort score, some time to destination scores. So it's a combination of all of them. But technically, you can use anything as long as it's continuous. And collision is not that great because it's a 1-0. But anything else is pretty can be used. And this again, this is also of this work. You can use anything you want. The second question. Sorry, what was the second question?
I was more like, what can you do to check that these trajectories are actually realistic?
There's a discriminator, right? That's what the discriminator is for. Because just having the autoencoder itself, you most likely you'll get to a scenario that's somewhat realistic because the decoder learns to map the embedding into decoder into the scenario. But again, right, once the noise is applied, there's no guarantee. That's why the discriminator is there to further reinforce the realism.
All right, thanks, Chai. Please allow me to introduce our second speaker. Dr. Zhou is currently a senior manager and staff research scientist at Waymo, well known for their influential work on VoxelNet and contributions to Waymo Open Dataset. Prior to their current role, they spent over 3 years at Apple as a tech lead and senior AI researcher. Zhou.
Hello, everyone. My name is Zhou. I'm a senior research manager at Waymo. Today, I'm going to talk about label-efficient machine learning for autonomous driving. In this presentation, I will first introduce our auto-labeling and active learning technologies. These are the foundation techniques that would help us to scale up the semantic understanding of the open world. And then I will cover our recent works on open set perception and motion prediction, which are critical capabilities for autonomous vehicles to navigate through the dynamic open world. By developing auto-labeling and active learning technologies, we expect to reduce labeling cost and essentially improve the efficiency of model development. Back in 2021, we published our work, Auto-Labeling. This is a system that can leverage structured information in 3D space and temporal dimension. The system will produce high-quality bounding box. The core idea behind this work is that we can extract complementary information from different viewpoints when the autonomous vehicle moves by an object. By aggregating the object observations across time, we can essentially refine the pose and dimension of detected object, and then realize a more accurate auto labels. One important application of our auto labeling technique is motion prediction. We have applied this pipeline to auto label the Waymo open motion dataset, which is about 100 times larger than the perception dataset. As you can see in this video, the auto labels are quite accurate and stable, even in this highly complex scenario. If we were to use manual annotation for such a large-scale database, the cost will be easily off the charts. So now, a natural question is, how good are our auto labels for long-tail cases? So we have bootstrapped a object detector with a semi-supervised learning based on 13% of labeled data. And we found that on the overall metric, our semi-supervised detector is able to match the performance to the fully supervised detector training with 100% of labeled data. However, this semi-supervised detector indeed comes up very short in the long-tail large vehicle category. And to close this performance gap leads to our next work on rare example mining. In this work, we have developed an active learning framework with a new data mining criteria called rare example mining. Specifically, we developed a pipeline that can leverage a pre-trained detector to automatically triage incoming data samples into either regular ones or the rare samples. By doing so, we can feed only the rare samples to human labelers for manual annotation, and leave the regular samples for auto-labeling. As you can see, with this process, we can free up human labelers from repetitively label easy and common cases, and concentrate their attention on the long-tail and challenging cases. So what is the difference between rare versus hard samples? First of all, rare samples are infrequent samples in a training set, such as the construction vehicle, trailer, large trucks, as shown in the blue rectangle. On the other hand, hard examples are objectively ambiguous. There can be actually multiple factors cause a sample hard to recognize, such as occlusion, long distance, or the sample can be a rare example itself. In our experiment, we find that training with more hard examples does not necessarily help improve the model performance, but using more rare sample can actually targetedly close the data distribution gap and make a targeted improvement on the long-tail cases. So we have developed two rare example mining strategies. In our first approach, we consider rare objects to be uncertain objects, excluding hard ones. Specifically, we use a model ensemble to first discover all the uncertain objects which receive high variance with prediction scores. And then we remove those objects with very few LiDAR points, or they are far away. Because this approach is based on models agreement, we call this approach model-centric. In our second approach, we directly use the probability density to measure the rareness of data samples by using normalizing flow. On the left, that's a data distribution where you can see there are thin and scattered samples spreading out from the dense region, and those are the rare cases. The normalizing flow model is able to assign low probability score to these rare examples and assign cold color to them. And the model is also able to assign high probability score to common ones, and therefore assign warmer color to those common cases. In practice, we can actually combine the two strategies into a hybrid approach. In this work, for example, we can use first data-centric approach to discover all the long tail cases, and then use model-centric approach to filter out those super challenging ones by only preserving the rare examples. By doing so, we are able to largely close the performance gap and improve the long tail cases by more than 30%. The next question is, how are our auto labels compared with human labels? So we use 3D and bird's eye view average precision to evaluate the label qualities. First, we evaluate at the IOU equals to 0.7. This is a commonly adopted metric for object detection. As you can see, under this evaluation criteria, our auto label performs very closely to human labels. Then we increase the evaluation metric to 0.8. First, we notice that under bird's eye view evaluation, our auto labels is even slightly outperform human labels. But when we look at the 3D AP, we observed a wider performance gap. And we believe this is mainly due to the observation sparsity. And this leads to our next work on MODA. As you can show in the video on the right, the goalkeeper uses motion forecasting skills to help him save the ball. The entire process does not require the goalkeeper to look at the ball for the entire time. So in this work, we are motivated to study how can we leverage motion forecasting as a virtual sensor modality to help object detection. So before we dive into the technical detail of MODA, let's first revisit some challenging cases due to observation sparsity. Based on analysis, many of the errors made by the state-of-the-art detectors are due or related to observation sparsity. As shown in this figure, I'm using the green color to represent the ground truth box and the blue color to represent object detection output. And when the detector is seeing insufficient amount of LiDAR observations, it tends to generate false positives or false negatives. In the top row, I'm visualizing some of the completely wrong false positives, meaning there is no prediction at a proxy to the predictions. That means these predictions are completely wrong out of nowhere. And in the bottom row, I'm visualizing some completely wrong false negatives, meaning there's no prediction at all touching the ground truth box. If you remember, in the auto labeling framework, it is a system that can only refine detector's box into a more accurate auto label, a more accurate box. That means it comes short in fixing completely wrong object detection outcomes. So that indicates the object detector itself can become a performance bottleneck for the auto labeling pipeline. And to remove this performance bottleneck, we introduce MODA with the hope to enable detector to see better in occlusion and at long range. Now, I will show you how to create a Modular point for an actually captured point cloud. Suppose we are looking at the current frame of point cloud. What we can do is look at the neighboring frames with respect to the current frame. And among the neighboring frames, we can apply object detection and tracking and result object track for all the object within these neighboring frames. What I'm visualizing here is object track for a particular object at the frame T. Note that in a causal system where we can only look into the history, the frame T is always earlier than the current frame. That means the object track contains only history information. To realize optimal performance improvement, we can actually remove the causality constraint by allowing us look into both the future and history. And depending on the relationship between the frame T and the current frame, the object track can actually correspond to either history information or the future information. Okay, based on the object track, we can apply forward or backward motion forecasting and generate the prediction at the current frame. And then we use the center of the predicted box to represent the Modular point coordinate. And finally, we can concatenate the current point cloud with a Modular point into the augmented point cloud. That completes the Modular point generation process. To populate more Modular points, we can actually apply the same process from every neighboring frame and generate more, which will effectively generate more LiDAR points and fusing information from a lot of the neighboring frames. On the other hand, we need to realize that the motion forecasting itself in nature is a multi-model distribution. To recognize that, we allow each object track to generate a multiple motion hypotheses. What's shown here, for example, are 2 motion hypotheses. And in this work, we allow 6 motion hypotheses to cover a wide range of possibilities. Putting all the pieces together, the Modular points are generated from multiple frames and based on multiple motion hypotheses. I want to make a note here that the Modular points only constitute a small set of virtual points compared to the original point cloud. That means the extra computational overhead is very small compared to processing the original point cloud. So in our experiment, we found that associating point feature will usually lead to performance improvement. The point feature we used are box semantics, box geometry, and uncertainty information derived from object tracking, the probability score of each predicted trajectory, as well as the Gaussian variance with respect to each predicted trajectory. So now I will show you how to actually apply Modular for object detection. Here, the input is a raw sequence of LiDAR point cloud. Now, let's pick a targeted frame to generate Modular points by applying motion forecasting, as I just introduced. With this step, we will get augmented point cloud containing LiDAR and the generated Modular point. In this visualization, I'm showing the augmented point cloud in the generated in the offline setting, where the red and the blue points are the Modular points generated by forward and backward motion forecasting, and the green points correspond to the original LiDAR point. Based on the augmented LiDAR points, we can actually train a new detector and apply it on a test set that completes the the object detection. In this example, I want to show how effective it is of Modular in the heavy occlusion scenario. On the left is a state-of-the-art detector trained based on only LiDAR. As you can see, when the occlusion becomes really heavy, the detector loses power in detecting the object. On the right-hand side, by rely on the MODAR and LiDAR, the detector is able to consistently detect this object, even though the occlusion is really heavy sometimes. Our MODAR is also very effective in extending the detection range. As shown in this figure, the detector trained with the help of MODAR is able to locate objects that are really far away, almost as twice the sensor detection limit. Combining MODAR with our state-of-the-art detector called SW-Former, our new system is able to outperform our previous 3D auto labeling by a large margin. Specifically, evaluated under the L2 APH, which is the most challenging evaluation criteria, our new system is able to outperform the 3D auto labeling by 3.7% in vehicle detection, 7.2% in pedestrian detection, and 5.4% in the overall metric. Now I want to switch gear and talk about open-set perception. This is actually a very much underexplored topic in the research and industry community. So why we're interested in this? As we know, in modern autonomy systems, object detection and trajectory prediction models are trained with human supervision to recognize predefined object types, such as vehicles and VRUs. Here, VRU covers both pedestrians and cyclists. And to tackle the long-tail cases within these known types, I just presented our rare example mining work that can efficiently use targeted data to improve the long-tail case performance of the model. But still, this is not the end of the story, because there are simply so many unseen object types out there that constitute this open set. For example, the running dinosaur on the street and the airplane on the road. The challenge here is, how can we develop a scalable system that can handle all of these unseen categories of objects in an automated way? So one idea we had is, how about we remove the need of assigning explicit semantics to these long-tail cases? And by doing that, we can create a class-agnostic auto-label and train all the detection and prediction models. So based on this motivation, we developed a method and published it in ECCV 2022. The paper is called Motion-Inspired Unsupervised Perception and Prediction. The core idea behind this work is that we develop an unsupervised scene flow model that can automatically discover all the moving traffic participants in the scene. And that would then allow us to create class-agnostic auto labels for all the moving objects. One big advantage of our approach is that due to the unsupervised nature of this work, this whole process is human-free, and we can apply the process to the gigantic logged data and generate a massive amount of auto labels. And these auto labels are expected to cover various of moving objects in the scene that we have observed or captured in our log. So here is an overview of our pipeline. It takes raw LiDAR sequences as input and it produces 3D bounding boxes and tracklets as output. The bounding box will be used to train object detection models, and the tracklet will be used to train trajectory prediction model. The two key components in this pipeline are scene flow estimation and auto-meta labeling. Let's take a deeper look into each of these two components. So the job of the scene flow estimation is to estimate the velocity of each LiDAR point. And we take a divide and conquer approach by decomposing the scene into disjoint clusters. By doing so, we can efficiently compute the local flow between two clusters coming from two adjacent frames. Let me using this example to show you how the scene flow works. What's shown here is a point cloud captured at time t. As you would expect, when the dynamic objects are moving with respect to the autonomous vehicle, the point cloud will drift on the moving object. So if a scene flow model is accurate, then it should estimate accurately the displacement on the moving object. So that means the predicted point cloud should match the actual captured point cloud at t+1. As you can see here, the predicted point cloud in color green actually match quite well to the actually captured point cloud in color red. That suggests our scene flow model is quite accurate. Now, based on the motion information from scene flow model, we used automata labeling to generate a model box through a series of geometry processing from initial box proposal based on the visible cluster to tracking, and eventually going through the shape registration step. In this video, I want to show you the detection output, and the model is trained purely based on unsupervised auto-label. As you can see, the unsupervised detector is able to localize all the moving traffic participants, including vehicles, pedestrians, and cyclists. Our unsupervised pipeline is also capable of capturing objects that are mislabeled in the ground truth database. In our open dataset, we find there is such a case where a person is pushing a stroller. Unfortunately, there's no ground truth box created for this stroller. With the help of our pipeline, we are able to detect the moving and stroller are moving all together, and the system is able to create a faithful bounding box for both of the objects. And therefore, trained with our unsupervised auto-label, the detector is also able to reliably localize the person and the stroller altogether. So based on our Waymo perception dataset, we designed an experiment to mimic the open set setting. In this experiment, we assume when training the detector, only human label for one category is available for the detector, whereas the other category is considered unknown or unseen category. For example, if we are training a vehicle detector, then there's no VRU human labels available, and vice versa. In this experiment, we care for the mean average precision, that is a metric averaging the vehicle performance and the VRU performance. As you may understand, a supervised detector performs really well when sufficient human supervision is available, but it keeps a blind eye on the unseen category because it simply doesn't generalize. Due to its fully supervised nature. But when training with both human supervision and our auto labels, the resulted detector demonstrated significant performance in mean average precision. On trajectory prediction, we observe the same pattern. That is, a supervised model trained with only the known type does not generalize to the unseen category, and sometimes it may produce ridiculously large error. But with the help of auto-label, we can actually obtain open set trajectory prediction model with quite a reasonable performance. We have applied our approach to some real-world challenging scenarios that we collected during our operation. On the left is a pedestrian carrying a plywood walking slowly across the street, and on the right is a person pulling a dumpster backward, also at a very slow speed. At the very bottom, we can show that our system is able to generate high quality and temporally stable auto-label for both cases, and with a velocity estimated quite accurately as well. So my last topic today is multi-agent motion prediction based on diffusion model. This is a paper that will appear about 2 weeks from now in CVPR, and this paper has been selected as a highlight. So why we are interested in using diffusion model for such a task? The first reason is that diffusion models have proven to be very effective in capturing the highly complex image manifold. And in addition, many existing trajectory prediction models rely on hand-designed trajectory anchors or sophisticated loss functions, whereas the diffusion model only employs a simple L2 training objective, which is quite elegant. And last but not least, guided diffusion may offer a natural way for controlled trajectory sampling. I want to show you how our pipeline training, how our algorithm can be trained. So here we are using a transformer-based architecture to encode all the scene elements into a set of condition tokens. This transformer model is called a waveformer. This is a paper we just presented in ICRA main conference. In a parallel thread, we prepare noisy trajectories by perturbing the ground truth trajectories with time-modulated noise. And the model we train is a denoiser that, in this denoiser model will be trained to attend both the noisy trajectories and the condition tokens. And in the end, the denoiser model will produce the denoised trajectories. This model is trained end-to-end using L2 loss, comparing the predicted trajectories and the ground truth trajectories. At inference time, we employ the same scene encoder to summarize all the scene elements into a set of condition tokens. And we generate pure noise for the trajectories. And we use the highest variance that we have used during training. Based on the trained denoiser model, we iteratively apply it, and eventually will generate the predicted trajectories. Here, I'm using this visualization to show you how the denoising process works. On the top is the regular multi-agent motion prediction, and at the bottom is a guided multi-agent motion prediction, where the cross sign represents the final waypoint each agent has to arrive. As you can expect, when at the beginning of the denoising process, the predicted trajectories are random because we are feeding pure noise to the model. As the denoising process goes on, the predicted trajectories are more reasonable, and when the time reaches 0, the denoising process completes. When evaluating on the motion data set of ours, our motion diffuser model is surprised to achieve very competitive performance to a state-of-the-art model of ours called the Joint Future Prediction, JFP. Well, as a final note, I want to mention that our problem formulation is actually very general, and it can be applied for scene layout generation. In these tasks, what you can do is mask out some of the agent in the scene and use the diffusion model to reconstruct the original scene. This teaser is showing the generated agent in blue bounding boxes, whereas the gray pixels correspond to the untouched condition scene elements. You can see that the generated blue agent are quite reasonable in this space. Last but not least, if you are interested to try your own idea for autonomous driving tasks, please check out our open data set. Thank you all for the attention.
But there are any questions?
My question would be about auto-labeling for unseen objects which are static. What is your strategy?
That's a good question. So in this work, we have only focused on the moving object, but we can extend the train detector by removing the temporal component and to auto-label all the objects we have recognized in the scene. So that will transfer the knowledge from moving to static. And in our recent work, we have developed other methods that can leverage, the weakly supervised multi-model like GPT type of model to create queues for this task. And by that approach, we are able to address both the moving and the static object.
Hi, thank you for that great talk. My question is that if you do 3D object detection based offset data set, offset like categories, how many classifier head are you using? Like, do you assign the classification head for each category, right? But if you don't have any, if you use the open set data set, how do you design the classifier head for that case?
Okay, so the question is about how can we deploy such an open set detector on the real world, combining with our onboard model. Mm-hmm. So as I said, we create auto labels for open set in a class agnostic way. So that means we just create a other class for the detector. So there will be only one additional head predicting all the unseen categories as a whole. We're not trying to differentiate any of them.
Okay, so you just create a particular classifier head that can handle all kind of offset categories.
Yes.
Okay.
If you, let's say, if you have now already two known classes, vehicle and pedestrian, then you just add the third class, which is other class.
Okay, thank you.
Mm-hmm. Thank you.
Thanks for the wonderful presentation. I guess my question is about the molar points. I wonder if there is any insight about creating such a more explicit representation as a molar points into the current frame than some of the current common practice that just directly aggregate multiple frames and having a time offset for each point, and then just letting the model to be able to just trying to predict from these points from different frames.
Thank you. That's another great question. I think I can answer this question from two perspectives. The first is from the computation and memory usage. In our experiment, in our literature survey and experiment, we found you can have decent performance improvement by simply concatenating point cloud up to a certain number. But this certain number is rather small before you run out of memory. That really limits the temporal horizon you can fuse in your model. Right? But with this model, we are using very succinct representation of only a few foreground points added to the current frame. Like I said, we can fuse 180 frames. That is totally 2 orders of magnitude more than the traditional way of concatenating points. And the second perspective is that when we're concatenating frames, it's probably okay for a static object, but there will be drifting on the moving object. You will see, if you visualize on top of each other of the concatenating points, it will have a long tail effect that will stretch a short object into a longer box and cause some confusion to the model. But with this motion forecasting, we actually already warp all the moving object to the current frame, so the shape of the point cloud can be better represented. Thank you for the question.
I just have a question on when you compare the general other class with supervised learning. Did you try for the supervised learning? I saw your accuracy is 0 or whatever. So did you try to classify the results generated by the supervised model if it's below a certain threshold? Suppose your confidence is low and then just directly assign it to the other class. Will that be a more fair comparison with your new model with the additional class?
Okay, so you're asking about the open set perception topic. If I'm more tolerant on the supervised detector's output and keep all the low confidence predictions if that can generate some reasonable number. Actually, we have tried. Our detector is quite discriminative. When training with only vehicle labels, it always generates almost very low response on all other places. If we are able to reduce the threshold really low, that will not only pop up bugs for pedestrian, but also maybe on the buildings and trees. That is a very disaster outcome for this detector.
All right. Let's thanks Zhou again. So the next speaker is Bert. Bert is the founder and CTO at Segments AI. a startup working on data labeling for robotics and AI. Before that, Bert did a PhD in computer vision at KU Leuven in Belgium, focusing on ML solutions for scene understanding. He also did intern at Toyota TME and Google DeepMind. Bert, it's all yours.
Can I put my laptop on the stand? Just... Yeah, that should work. Hello, good morning, everyone. My name is Bert. I'm the founder and CTO of Segments.ai. Segments.ai is a data labeling platform focused specifically on data labeling for robotics and autonomous driving. And so today I'll talk about multi-sensor data labeling and the steps that we take to make this process as efficient as possible. I'll deep dive on some of the technology that we have today and also explain some things that we're currently working on and will be working on in the future. But let me first sketch maybe some context. So this is the ML data engine that you're all familiar with. You collect data, you curate it, you label the data, you train a model, you evaluate the model and you deploy it, and you basically keep iterating this loop to make your model better and better. At Segments, we are squarely focused on the data labeling part. And more specifically, our expertise is really in multi-sensor data labeling for robotics and for autonomous driving applications. So what does that mean? I hope that this video plays. Yes, on the left you see what like a typical customer would send us. It's raw, unlabeled, multi-sensor data, typically consisting of a LiDAR point cloud and multiple camera images from sensors mounted on a vehicle or on a robot. And on the right is what we send back to the customer. So it's perfectly annotated ground truth data, bounding boxes, segmentation labels, both in 2D, both in 3D, with consistent object IDs across all the different sensors and obviously also across time. And of course, for us as a company, the question is how can we label such multi-sensor data as efficiently as possible? And a big part of the answer there is that we obviously also use machine learning and AI for that. I'm trying to go to the next slide, which doesn't seem to be working. I'm actually seeing the next slide on my screen, but not on the Zoom call. Shall I try to reshare? That looks better. Okay, so let me continue. So most of you probably have experience like developing machine learning models for machine learning models that need to run on a robot or on a vehicle. And there's actually a few key differences when developing machine learning models that are used specifically for data labeling. The first one is that machine learning models for data labeling typically have humans in the loop. So they're designed to work in tandem with a human labeler. And that means that we need to design interfaces where humans and machines can interact in an efficient way. It also means that we prefer models to make mistakes that are easy to correct. For example, in a detection problem, we prefer models with higher recall and lower precision. So it's much easier, for example, to delete a detection that is too much rather than having to label a new detection from scratch. So we always prefer models with higher recall. Another big difference is that machine learning models for data labeling don't necessarily need to be real time. So they don't need to run at 10 frames per second on a robot. So in the speed versus accuracy trade-off, you can go all the way for accuracy. It doesn't really matter if the model takes a lot of time to produce a prediction. It also means that we can use slow models like diffusion models or NERVs that are typically too slow to run directly for real-time inference. And finally, machine learning models for data labeling are allowed to cheat. So for example, when making predictions on sequence data, you can actually have the model look ahead in the future, at future frames, and take those into account when making predictions for the current frame. That's obviously not something you can do when running a model in real time on a robot. So all of this makes ML for data labeling a unique and, in our opinion, a very fun challenge. Continuing to the next slide is, again, not as easy as hoped. Okay, so let me now take you through our process for labeling multi-sensor data. High level, it's a process that consists of 3 steps. There's auto-labeling, manual verification and correction, and cross-sensor projection. The first step is auto-labeling, and it's pretty straightforward. We basically run an object detection model on the 3D point cloud data to make automatic predictions. We use standard off-the-shelf methods for this, which we can also fine-tune on the data that the customer sends us. As mentioned before, we also tweak these models a little bit to have higher recall at the cost of lower precision to make sure we don't have many missing detections. And it's better to have a detection too many than one that we have to annotate manually. So in some cases, our customers also use their own models to generate these kind of pre-labels rather than us producing it for them. The next step is manual verification and correction of the 3D predictions that were auto-labeled. So this step involves humans, and it's important that they have the right tools to interact with the data in an efficient way, and also with the generated predictions. This is really a UX problem, and it's the bread and butter of our startup. I'll quickly highlight a couple of features that make the life of the annotators a lot easier. The first one is the synced camera feature. So this one, when labeling a point cloud, it's often very hard to see what exactly you're labeling and what you're looking at, especially for point clouds that are not very dense. So that's why we have this synced camera feature, which always shows the camera view and the camera image corresponding to like the location where your mouse pointer is hovering in 3D. We can also open a specific camera image and look at the overlaid point cloud and predictions on that specific view. So this makes it much easier to localize objects of interest, see if a blob of points is a car or a van or a truck, much easier when you have the camera images. Another very useful feature is the batch mode. Here you can basically zoom in on a specific object track and quickly adjust its cuboid throughout the entire sequence. So when an object wasn't detected in the auto-labeling step, that's also possible. We also have an ML-assisted object propagation feature, a cuboid propagation mode basically, and that's what you see here. So you just label the cuboid in the first frame, you press a button, and automatically the cuboid will be propagated to the next frames. Obviously, you can still make predictions and corrections and adjustments if the tracking is off. So this is very useful when labeling dynamic and moving objects. For static objects that are not moving throughout the sequence, we have a different mode, a feature called the merged point cloud mode. So if you enable this one, all of the point clouds across the whole sequence will be merged together or aggregated into a single view. And this gives you a much higher resolution view of static objects, so you can better see what they are, and you can also label them much more accurately. This feature is possible because in the backend, we are actually splitting up the point cloud into tiles, a bit like how Google Maps works, and we're only streaming the point clouds to your web browser that you're currently looking at. So if you're zooming in and zooming out and looking at a different part of the point cloud, then only those points will be streamed in from the backend. So these are just a few of the features that we have to make labeling easier. We're working on many more. For example, the ability to automatically highlight potential outliers and mistakes in the data, such that you can really immediately focus on these ones and don't have to go looking for potential mistakes. Okay, so far we've focused on 3D labeling, but most of our customers, they don't only want their point clouds labeled, but also their images. And they want the object IDs of all the objects to be consistent across the different sensors, across all the cameras and also across the point cloud. And so we do this by projecting the 3D annotations onto the 2D images, optionally followed by another manual correction step and a verification step. For bounding box annotations, this is a pretty straightforward process. If you have accurate LiDAR camera calibration, you can basically just project the vector annotations onto the images by doing like a matrix multiplication. It's pretty straightforward. It's something you can do in our tool with the click of a button to just project the 3D cuboids to 2D bounding boxes. But what about segmentation labels? So on our platform, you can also do point cloud segmentation, but how can we transfer these point cloud segmentations to the images, turning them basically into segmentation masks? It's not so obvious how to do that. And so this is something that we're currently working on and exploring a few techniques to actually help projecting the 3D segmentation labels to the images. What happens if you just naively project the point cloud labels onto the images? You get something like this. You get a very sparse segmentation of the image, only at the pixels or the points aligned with points in the LiDAR beam. So the question becomes, how can we get a full image segmentation from this sparse image segmentation that you get from the projection? And one thing to notice is that this looks very much like an in-painting problem. So we know the segmentation label at certain points, but we need to impute basically the missing values at the other pixels. And so this sounds like a job for a generative model, like a diffusion model. So this is something that we're currently exploring. As you know, diffusion models are a class of generative models that iteratively turn noise into data. They're most popular for generating images conditioned on text. For example, you all know probably Stable Diffusion. It's a model, you give it a prompt, a text prompt, and it generates an image like showing the text that you're describing. In our case, we instead want to generate segmentation labels, and we want to do that conditioned on RGB images. And so diffusion models are a perfect fit for this in-painting problem, because we can just keep the known pixels clamped, and we can iteratively apply the diffusion process to the missing other pixels. So that's something that we've been exploring. It's still very much work in progress, but you can already see some preliminary results here. We fine-tuned an adapted stable diffusion network on this task, and we're already getting some decent results. So one of the main challenges that we face here is to basically scale all of this up to higher resolutions. On the right, you see some first progress in the direction, but yeah, definitely we're not there yet. But we do believe that this type of diffusion models for image segmentation are extremely versatile, and we also have a lot of other uses for them in mind. Let's see. Do I still have some time? Yes. So as a side note, you may be wondering, why did we decide to first label everything in 3D and then project to 2D? You could also imagine like a different kind of workflow where you first label bounding boxes in images and then do segmentation on the images, and then use those 2D labels to somehow reconstruct the 3D scene. And the truth is that labeling in 3D is often much more efficient, even if you're just interested in the 2D labels. So a simple example makes this clear. Let's imagine your car is driving past a static object, for example, a traffic sign, and your car has multiple cameras, and as you drive past the traffic sign, it is visible in 3 of the cameras for, let's say, 100 frames. So that means that you'll have to annotate 300 2D bounding boxes containing the traffic sign. Now, in 3D space, labeling this static, non-moving object, it just takes one cuboid. You just draw the cuboid, and it stays fixed throughout the entire sequence. So even though labeling a cuboid takes maybe 5 times as much time as labeling a 2D bounding box, you still get a huge boost in efficiency from labeling in 3D and then projecting the cuboids back to 2D. And so that's why we take the approach to always start with labeling in 3D, and only then we do the 2D labeling. Okay, so now we've looked at the process for getting ground truth labels for both your point cloud and image data. So what's left to do? And one last topic I want to touch upon is that of voxel grid labels. So we see more and more customers experimenting with voxel grid representations, also often called occupancy grids. And they're also asking us if we can help them get this kind of ground truth labels for them. And so a voxel grid, also called an occupancy grid, is basically a 3D volume of voxels indicating both the occupancy at that voxel and the semantics, for example, like a semantic segmentation or an instance segmentation of that voxel. And why would you need this kind of labels? So more and more robotics and AV companies are moving from a late fusion approach to an early fusion approach. What does that mean? In a late fusion approach, you basically run separate machine learning models on each of your sensors, and then you somehow fuse their predictions together to obtain a 3D representation of the scene. In an early fusion approach, you throw all of your sensor data, all of your images and point clouds into a single machine learning model, and you try to make predictions directly in the 3D space, so end-to-end basically. And it's a more modern approach, and for example, something that Tesla has been doing and pioneering. If you follow their talks, you can see some examples of that as well. And so voxel grids are an ideal scene representation for this kind of early fusion approaches. Because they're so regular. It's basically just a tensor of voxels, so you can predict it directly from a neural network. Now, to get to such nice voxel grid labels, you basically need dense point clouds, right? It's not going to work well with a very sparse point cloud to generate such a voxel grid from it. And there's a few strategies that we're exploring to make sparse point clouds more dense. The first one is pretty straightforward. You can just aggregate or accumulate points across the different frames in your sequence. It's something that we also showed as a feature in our tool. You can also do this just to make the point cloud denser. Obviously, this requires very good ego pose parameters and calibration because your vehicle, like the objects that are static actually need to stay in place. And it only works for static objects. So you need first to filter out the dynamic objects before aggregating or accumulating the point cloud. Otherwise you get these kind of ghosting patterns like you see there on the bottom left. Now for dynamic objects we can do something different and try to leverage the camera images to obtain denser depth for the point cloud. This problem is known as depth completion or sparse to dense depth estimation. And it's basically, again, an in-painting problem. You know the depth at certain pixels in your image by just, it's just like the pixels corresponding to a LiDAR measurement. And you need to in-paint the missing values where you don't know the depth. So again, this is very similar to the problem with the segmentation maps that we discussed before. We can just do in-painting with a diffusion model here. So the same type of diffusion model that I showed in one of the previous slides is something that we are trying to apply to this problem of depth estimation and depth completion. And then finally, going even further, some customers don't even have point cloud data. They just have a robot with cameras. For this use case, we're looking at doing 3D reconstruction using nerves. We're in the very early stages here, and there's a lot of challenges to make this work well for large scenes, but we're pretty excited about nerves, and we're actually keeping a close eye on the research in this field, and we've been experimenting with some turning some street scenes into nerves as well. So yes, I think that's it for my talk. I hope that I convinced you that there's a lot of interesting applications and challenges in multi-sensor data labeling. Data labeling is often seen as kind of a boring part of the ML pipeline, but we're pretty excited about it. It's definitely far from solved. And if you would like to help us work on these problems, we're hiring, so definitely reach out to us. I also want to mention that we offer free academic licenses to our platform. So just check out the website for that. There's a form and you can apply for a free academic license. Thank you. That's it. Not sure if there's any questions.
Hey, thank you for the talk. So it looks a bit like you're focusing on labeling 3D data with 3D cuboids. Do you have any idea on how to label non-convex objects such as trees where persons might be standing underneath it, or maybe more complex building structures?
Yeah, we actually don't see that request often from our customers. They're not really like labeling individual trees or individual buildings. So what some customers are doing, we also have an interface where you can label in the top-down view of the point cloud with polygons. So you can annotate certain regions to exclude them, for example, like indicate an ignore region or a region where there's vegetation or buildings in the top-down view without really going very detailed and labeling each building separately or each tree separately. Yeah, so that's something that happens.
Thanks.
Thank you for your talk. And I want to know if it's possible to label the velocity of every point cloud or the velocity of every voxel in the grid map.
Yes, indeed. If you look at the Tesla talks, they are also predicting in the voxel grid like the velocity of each voxel. We haven't really experimented with that yet, but yeah, obviously, if you have the cuboid annotations in the point cloud, you basically have the velocity vectors of the pixels or the points and the voxels within those bounding boxes, right? So already for the annotated objects, you at least have a measure of how fast they are moving. But indeed, if you want to go further there, then you have to look into these kind of scene flow models that were also discussed in the previous presentation. We haven't really experimented with that yet, but it's definitely something that we're looking at.
Thank you.
How big of a problem is drift or noise in your ego motion, and do you do any sort of corrections for trajectories?
Currently, we're not doing any calibration. We're really squarely focused on the data labeling part, so we push that back to the customer. We just say, fix your calibration, it's on you. It's something that actually we see a lot of customers having troubles with getting proper calibration, so we are considering to also go a bit deeper there ourselves. But currently, indeed, all of the tooling that we offer, it works really best when you have proper calibration and when you have proper ego motion of your vehicle. Okay. Yeah. Sorry? Does it label dinosaurs in Stroll? We haven't labeled any dinosaurs yet, I think. No, and airplanes. I'm not sure, but maybe. Yeah. Okay. Thank you.
Thanks, Bert. All right, we're now having a poster and a coffee session. Please do check out the posters outside the room and come back at 11 for the second session of the morning. Thank you.
Welcome back, everyone. Our next speaker is Dr. Adrien Gaidon. He is the Director of Machine Learning at Toyota Research Institute and an adjunct professor of computer science at Stanford University. Dr. Gaidon's research focuses on discovering machine learning principles at the foundation of embodied intelligence. He has over 80 publications in key fields such as computer vision and learning for robotics, along with more than 80 patents and applications primarily in autonomous driving. Dr. Gaidon received his PhD from Microsoft Research in Ria, Paris, and has received multiple scientific awards at top conferences like CVPR and EURIPS.
Thanks, Verena. All right. Hello, everyone. So I'm here to talk about geometric foundation models, and my talk is about combining the old and the new, as you can see in the title. So geometry and foundation models. So as you all know, geometry is at the heart of autonomous driving, and more broadly in robotics, whether it's on the road or in the factory or in a home. And the same can be said for the other part of the title, about machine learning in general, which is increasing in importance, not just in perception, like in many of the talks you've seen here, but actually everywhere, in all parts of the stack. And this growth in machine learning is rapidly accelerating as foundation models are now rapidly democratizing machine learning. So cool, not to throw buzzwords around and hype, but like there's some precise meaning that I have at least behind foundation models, which is the definition that came from Stanford's Center for Research on Foundation Model. Do you know what the definition is? You can just raise your hand, I'll read it. So who knows what the definition of foundation model is? All right, we are the robotics conference. Okay, so I will define. Maybe you could have said maybe it's ChatGPT, I don't know. But the definition of it is a model that you train once, and then you can use it for many tasks. So at the heart, a foundation model is just saying that we found ways, or we're trying to find ways in machine learning to amortize the costs of learning, enable rapid development, right? Train once, use for many tasks. So you're just being shy because you're just coming back and the coffee hasn't kicked in yet. You all know ChatGPT, right? More than 100 million users. That's the current foundation models. That's probably what you have in mind when I say foundation models. And actually, there's plenty of uses already of large language models, or LLMs for short, in robotics already, as you know, for user interfacing, task specification, or even more and more for open world recognition. However, models like these are mostly limited to language right now, and images coming soon. So a natural question is to wonder why. Why are foundation models right now not really about foundations, but just about like language? The answer is easy, as always in machine learning. It's in the data, right? Whenever you ask a question about machine learning and you don't know the answer, you just say data. That's 90% of the time right. And so really, that's why we have large language models, is because that's the data we have. And that's been kind of the history of machine learning for the past 10 years. Using internet and big image data sets like ImageNet is really what's been driving progress for the past decade. And the data sizes have, increased now by 2 or 3 orders of magnitude to get to the current foundation models. But to get to foundation models that we care about in robotics, in driving, etc., to get towards embodied intelligence for these autonomous systems, we probably, if you want to take just a pure data-driven approach like this, require 2 or 3 or many more orders of magnitude to get there. And that's the problem here, right? Because can't keep scaling infinitely, right? And so that's the problem if we just rely on data alone. So we need to fill the gaps in our data sets with what we already know. And that's an approach that at TRI we have and we call principle-centric machine learning. And so luckily, as we work on embodied intelligence for physical machines like cars or robots more generally, people have already discovered many fundamental principles and widely used foundation models. So let me give you an example. An area, as I mentioned earlier, particularly relevant for robots on the road or anywhere else is geometry. So again, just to kind of keep waking up, I'm going to ask you questions. Who knows what this model is? All right. Okay, many more hands. Okay, cool. Nice. So that's the pinhole camera model, obviously. Okay, now a bit of a trickier question because your audience is a bit more savvy in computer vision. Do you know how old it is? Can you raise your hand if you know? All right. You don't know? You might be surprised. It's like thousands of years old. It dates to ancient China, I think like 400 BC, and even Aristotle area. So it's really like a very powerful model for understanding geometry, right? And understanding here is an important word, and not the machine learning way we use understanding, but the actual mathematical way we use the word. But the problem is it's not a model in the machine learning sense, right? We cannot train it to make predictions for us, right? Say about how far objects are in the scene, which is, you know, a fundamental problem that we care about in driving and robotics. And so a natural question we have now is we have like two very different types of models, or foundation models, right? And so how can we merge these two types of foundations? The data-driven transformer ones, the ChatGPT world type of models, and then human-derived principles like the geometry world. And so what we want is we want to learn this geometric foundation models, again, trained once and useful for many tasks. And so a very general way to do this is just like actually in NLP is self-supervised learning. But this time we're using geometry for 3D vision models instead of autoregressive language models that work with predicting the next word. So let me drive you through a little bit of how this works. So we start from two frames, let's say current frame and past frame. Taken from the same camera, moving camera in different time steps. This also works for just if you have two cameras, like different viewpoints. A depth network takes the current frame and produces an output depth map, as you see here, where it's color-coded, meaning brighter is closer to you and darker is further away from the camera. You also have a pose network that takes both frames and outputs an estimate of camera transformation between them, or we call also the ego motion. And with these two predictions, we can project information from the current frame onto the adjacent frame by projecting from 2D in one view to 3D, which you see here, this kind of point cloud, and back to 2D in the other view. Then a differentiable operation called view synthesis takes all these corresponding pixels and creates a synthesized frame. Now this synthesized frame will be an accurate reconstruction of the adjacent frame if and only if the depth and pose estimates are accurate as well. Due to the geometric constraints we use to formulate the problem. Again, that's the benefit of geometric models or geometric principles, is we know they hold in generality. So by minimizing the photometric difference between the current frame and the synthesized frame, we can optimize these two networks, the depth network and the pose network, without any explicit source of supervision. So it's entirely self-supervised. So as I mentioned, this principle holds in generality, and that's the power of geometry. And so it has been very successful for us, both scientifically and practically. So we've done many papers and many models, and actually transferred a bunch of them in the real world. And so let's just give you a couple of examples there, and to try to convince you that yes, we are actually talking about a foundation model in more the ChatGPT way. So here, for instance, what you see is that this approach generalizes across many domains, including very, very challenging ones, like the street covered in snow. And even more challenging ones, as is the case on the right with this extreme sports motorcycle. The funny thing here is that it's not even, like a part of the data sets or the benchmarks we use, etc. This is like a random Reddit user trying our models and making it work. So this is pretty cool. If you survive Reddit, you're tough. By the way, again, as I said, it's not a true foundation model if it only works in one domain, like driving. So going from driving to diving, we even find that our approach works underwater. And it's fairly complicated if you think about it geometrically, right? If you're trying to model this in a non-machine learning way, I mean, your brain explodes, right? Because water acts like kind of like a dynamically changing lens. Again, even further, we've been making efforts to generalize this model to other areas of robotics. What we find is that we can also apply the same principle and methods in much, much shorter ranges, as we did in this collaboration with the TRI robotics team, where, I don't know if you passed by our booth, but you might have seen some of the sensors that they developed. It's like a soft bubble sensor, which is a visual-tactile sensor. How does it model the deformation of the bubble? There's a camera inside, and we can actually run monodepth, also the same models inside, and estimate the depth, the depth changes as the bubble gets pressed. We also find that this approach works in other areas of robotics, like indoor robotics, as we show here in a supermarket reconstruction on the right. And now you said, wait, like you went all over the place. Why are you talking about supermarket now? Again, it's because it's important for ML to work across many diverse domains and tasks, because Toyota is not only the largest car maker in the world, but it's also a leader in robotics. And so if the video plays, which let's give it a little bit of time to load. And it looks much cooler not through Zoom, so if you want to see the cooler version, you ask me later, but at least this time the video plays. All right, let me play it for you. This is a robot made by our robotics team, led by Max Bajashaya at TRI. And so it works on a challenge task, which is like supermarket. So sorry, no, Toyota is not going to sell supermarket shopping robot. But it's a really interesting challenge task because it's very difficult. But also what we find is that the models that work, a lot of the algorithms that work for this robot actually transfer to more factory robotics, like what you've seen at the end. We have these huge arms that are used in making cars, and we find that a lot of the approaches we develop for driving have potential there for like just home robotics, the supermarket, and the factory. And so the reason why foundation models are such a big deal here, and what I've hopefully convinced you that it can really generalize really well, and that's the source of its democratization, is because they are decent at zero-shot generalization, right? If you are not familiar with foundation models and you think they're a little bit voodoo and weird, the reason why people are excited is really this zero-shot transfer. And by zero-shot, I mean the pre-trained models are already useful before fine-tuning or adaptation, right? They're not maybe working great or perfectly, but they're already useful out of the box. The weights themselves, right? And so besides data, which obviously is a big part of the picture here, right? That's you know, it's machine learning still, so it's still interpolation. We haven't solved extrapolation or crazy things, right? So you're only as good as your data, but you can be a little bit better than your data, because here, again, as I mentioned, we use principles, right, to go beyond the data. And in particular, as I mentioned, we leverage geometric principles. So we can go even further and leverage geometry even more. So far, we've mostly leveraged basic pinhole camera models. So basically what I teach an undergrad at CS131 at Stanford. Now, another thing I teach is this. Who knows what this is? Who knows what F is? Yes, and I hope you got the pun from the title. All right, this is the fundamental matrix indeed. Excellent. This is a 3x3 matrix, right, that encodes uncalibrated epipolar geometry. How to go from one point in an image to the epipolar line in the second image. Again, geometric principles are superpower. This is not dependent on the data. This is just a mathematical model, right? But this is the condensation of millennia of human intelligence in beautiful mathematical form. If you think about it, this is kind of like the ultimate pre-training, right? Like 2,000 years, boom, in there, right? So you want to use this pre-training. You don't want to start from scratch and spend 2,000 years rediscovering the fundamental matrix. So let's use it. So how do we do that? You don't have to throw away transformers. You don't have to say it's either that or deep learning. You can do both. And so this is what we did in our recent paper called the depth former. In the previous works I mentioned, we leveraged camera motion during training time for self-supervision. So the natural question is, why not leverage it at test time as well? And so there are a few challenges with that, which is why we didn't do it right away. But the main idea, just to make it short, is to use the epipolar constraint I just mentioned and transformers to predict depth by learning self and cross attention layers for matching along epipolar lines across multiple frames. That's a very sensible idea. You know, good luck trying to find out completely from scratch, but here we can guide the model. Actually, you can even be even more deep learning-ish if you want, and you can also use geometry implicitly, all right? Because the problem is that if your calibration is not completely correct, etc., your epipolar lines might be off, and now you're like, you have the problem of like, oh, it's biased and you cannot recover from this bias, the bias is bad. But actually, if that's the situation you're in and you don't trust your calibration, first, you're going to be in a lot of pain, and I'm sorry for you. But second, yeah, sometimes there's some mistakes, so you want more robustness. So you can do it implicitly, and this is what we did in our depth field networks, or define paper. where instead of restricting the search along epipolar lines, we use our geometric knowledge as input level conditioning, right? But not just that, we can use it also for 3D data augmentation, and we can use it also for auxiliary tasks here. And so all these transformers that I mentioned earlier can use geometry because we have an explicit model of it, right? The camera model typically, right, is needed, fundamental matrix, etc. But often, as I mentioned earlier, and this is why I talked about robustness, we don't know it perfectly, or even at all, right, if you haven't done calibration. So for that, you can once again marry the old with the new. It's kind of a bit the theme of my talk, and to learn principled camera models, whether, general extensions of the pinhole camera model I mentioned earlier, something like this, the unified camera model. Actually, what we use in particular is called the double sphere camera model, and it's a paper we published at ICRA last year. But what you can do is you can even go completely, again, deep learning crazy, and you can learn projection and unprojection operators, like functions per pixel, as we did in our neural ray surfaces paper presented a while back, but I think that paper is underestimated by a lot of people, so I kind of bring it up. I know 3 years sounds like forever, but it's a cool paper. And so what we have shown in these two papers is that these camera models can be calibrated end-to-end at the same time as the rest of the depth estimation network is learned. So if you have a moving camera, this is really a useful way to think about this. So a lot of the things I talked about so far is based on video, but you can go beyond video. And in the real world, in practice, I mean, we were talking earlier with a few folks, like in the world of massive scale, like Toyota mass production cars, I mean, there's 100 millions of Toyotas on the road. How many have LiDAR? Epsilon, basically. So we have to deal with single camera and video and stuff like this. But more and more, you have richer sensor suites for a vast array of applications, robotaxis, etc. But also in robotics, it's very common you don't have a single camera. If you have a single camera in robotics, I'm sorry for you. But we can go beyond video using these ideas and do 3D, like proper 3D foundation models for efficiently representing and generating, for instance, many shapes from 3D point clouds, which is our road model. We presented that Coral recently on the left, or RGBD cameras, which is our Chapeau model on the right. So of course, geometric foundation models are useful directly as is, for instance, for depth and pose estimation, right, what they're trained for, but also very effective pre-trained backbones for downstream tasks, as we have shown in several papers on object detection in particular, including DD3D, which I think is probably the most popular pre-trained backbone for object detection, and which we've improved and presented at ICRA with DD3D V2, and we actually have follow-up work we're presenting at CEPR soon. So in conclusion, I've shown you that there is a life beyond ChatGPT for foundation models. So now you know what foundation model is, and you know it's not just ChatGPT. And a part of the recipe is the same, right? Self-supervised pre-training on lots of data. But here, we can go beyond data by leveraging geometric principles in our losses, our network architectures, data augmentation techniques, etc. Be creative, right? But let me ask you a question. Do you think like geometric foundation models are enough just for autonomous and useful machines in the real world? I think clearly we want more than just geometry. So because we're in London, to quote a famous group of eminent British philosophers, I'll tell you what I want, what I really, really want. What we want is more principled, more general embodied foundation models, right? And I think here the same recipe of data plus principles continues to apply here, more broadly. And there are three big areas of focus for us at TRI looking forward, and I believe for the community at large. Of course, language. So talked differently than ChatGPT, right? Just to broaden the horizons, but obviously, language plays a big role, and we're investing in that and starting a team on this in my team, and especially looking at grounding there. We also need more than just language. We need proper multimodal embodied foundation models that integrate language with vision and action. And I'm super excited to see a lot of people here talking about this and making progress on this. It's, I think, really important. And finally, something that might be a little bit underlooked, but again, it's something that we care at Toyota a lot. Some people say too much, but I don't think you can care too much about safety. I think it's cutting across all the work that we do, and we want to ensure they are safely applied. And when you think about LLMs and all the controversies that are going on right now, is especially on safety, and that's just with LLMs that don't act in the physical world. So this is, I think, really, really important here. And so in summary, my team at TRI is working on embodied foundation models, which are general models that are trained once and useful for many physical machines and downstream tasks. And because we work with physical systems, we will never have enough data. Yes, I say this as a machine learning person, but there is hope we can complement it with principles, which is this approach that I talked about, principle-centric ML. And in particular, there are two big domains of embodied prior knowledge that we can leverage for sensory motor systems, vision and interaction. And this is why, in a good implementation of Conway's law, for those of you that are into management, we have two teams, one around each area, working together to build embodied intelligence. So all this work is the result of many people's efforts. And you see here the two teams that both Rajesh and Tom are leading in the overall ML organization, and we have many amazing collaborators across many universities. I think we have one of the largest university research program in the US. So all the code and the data is available online. We also have blog posts that explain things, you know, like also all the ICRA papers we've made or the upcoming CVPR papers. And of course, we are hiring because robotics, driving, all these things are still not solved. And one more thing, if I have one more minute, even though our research is more general than just for cars, we transfer our best results, including some you have seen today, to production vehicles. That's one of the benefits of working at Toyota. And we still do quite a bit of driving research, but it's a bit of a different kind, so let me show you what. And let's see if this sound's gonna work. It won't let me unmute, so imagine a vroom, vroom, vroom. In the real world, this car has 750 horsepower. It's pretty fun. All right, and I'm happy to take questions.
What do you think about an alternative when the model tries to imagine the future videos and basically learning a foundation model from imagining the future video stream?
Yes, so I think this is, so what about future frame prediction? If you think about, let's say Yann Lequin has been talking about this a lot for a long time. Yes, I think if you try the naive way, that's just a pure deep learning way without principles and just predicting next pixels, it doesn't work. And it gets very blurry, it's very complicated, and it makes sense from an information theory perspective or like pure deep learning perspective because you have many bits of many gradients, but you have to rediscover thousands of years of geometry and a lot of things there. I think objects exist. There are certain things we know about the world. We don't have to have machines rediscover it because it might take them a lot of effort. They might discover it in a different way or a non-interpretable way. So certain things we want machines to learn, certain things we want humans to teach machines. And so I think what you see here, we do actually future frame prediction, but we do it with geometry and deep learning together, right? So we're doing it, but in a more constrained way than just unconstrained predicting future pixels.
So
You showed a lot of results where learning with geometry helps to estimate better geometry, but I'm curious about the other aspects. Do you have, or I was expecting more results on how geometry helps you do other things. You name it, right? I mean, what tasks you want to do in the world.
Yep. So right now, there's some work in progress. So I've shown on 3D detection, so I don't know if you count that as like a geometric task or like, yeah, it's in between, I agree. We haven't done 3D to 2D yet, like to see, for instance, like, does it work better for video object segmentation or stuff like this? But what we are currently doing right now is for policy learning, pre-trained representations for policy learning, more for robotics applications, and we're finding in preliminary results that it does help also for these tasks. But so more to come soon. Here, I think.
Yeah, thanks for the interesting talk. You looked at geometry in a way that maybe is more optical.
Mm-hmm.
You look at that, and then you primarily showed examples from depth, which neglects a fundamental aspect, which is kind of compositionality of different objects, putting things on top of each other, putting things behind each other.
Mm-hmm.
Can you maybe comment on some of the principles that we're currently underusing in machine learning aspects coming from geometry in that regard?
Yes, that's a great question. So I think one of the major things that's missing in the work that I've shown is the notion of objects, right? And so the problem is that we have done some work. So there's a series of papers that led by Pavel Tokmakov in my team, so at ICML and a bunch of other conferences, which work to combine not just geometric principles or physical principles with cognitive principles, because objects, it's more a cognitive notion than a purely geometric notion. So we've combined the two with like motion segmentation and things like this, but at the heart, an object is like, is the mic an object? Is that part of the mic an object? It is, right? Is the holder of that? So it's essentially a semantic notion. And so a lot of the research we're using there, a lot of the principles are actually not geometric. They're cognitive and inspired by people like Liz Spelke, for instance, which has devised a theory of core knowledge. And so like notions like object permanence. And so we're combining these different principles, the physical principles and the cognitive principles, to go towards a more complete picture of the world, not just a geometric one. So that's a really good point. Yes,
this is going to be a bit of a more of an open-ended question.
Okay.
Geometry seems like the obvious examples of reusing something that we have learned over 2,000 years. But what do you think are the others? For example, what are your thoughts on like embedding what we learned about the physics of the world? Where do you see? Do you have any thoughts on that?
Yeah, so I think physics is way harder. So if you think about like dynamics, and before that there's kinematics, and before that there's actually geometry. So these are like baby steps that are already useful in of itself. One of the interesting thing, and one of the things that I'm excited about, like as broadening, diversifying the applications in my team from just driving to driving and robots in general, is that driving has a pretty boring version of contact, which is just minimize it, like avoid it, right? Like be far away. Contact is bad, is always bad with driving, right? Or it's with the road and you don't care, it's your tires. But in robotics, the picture is much more subtle, because there's some contacts, like some contacts you want to avoid, some contacts you actually want to have, right? Like grasping, etc. And so I think in driving, geometry brings you quite far. In robotics, you start to hit the need for modeling dynamics properly. And so basically I would say in the question that was asked before, you need a more complete picture. You don't need just geometry. You need the notion of objects. But then if you want to go to dynamics, you need inertia matrices and all this kind of stuff. And here the problem becomes that model-based control methods that are pretty sensitive to system identification, for instance. I think there's like cool work by Ben Resch from UC Berkeley that was showing with a simple LQR, RC car, just mass as a system identification. If you're off by 10 to the power minus 5, after a few laps, you're drifting. So that just goes to show that physics is way more complicated, and also because of like closed loop control problems. So yes, there's a lot of research to do there.
Thank you.
Hi, thanks for your great talk. So we all see a lot of great work from Toyota Research Institute. Is there any one of them be deployed on the production vehicles? Because we haven't seen anything on the Toyota vehicle now.
Yes, so I'll just say that there's a lot of efforts going on, and you'll hear about it more in the future. But yes, there's a lot of stuff going on. That's one of our motivations. You know, it's like eventually this needs to have an impact and be materialized, and we're you know, making progress there. All right, thank you.
Our next speaker is Dr. Fischer Yu. He's an assistant professor at ETH Zurich in Switzerland. He obtained his PhD from Princeton University and became a postdoctoral researcher at UC Berkeley. He now leads the Visual Intelligence and Systems Group at ETH Zurich. His works on image representation, learning, and large-scale data sets have become essential for computer vision research.
Oh, okay.
Okay, thanks for the introduction. It's a great pleasure to talk about my research at this workshop. So today I'm going to talk about our efforts to scaling 4D scene understanding with less hassles. So I'm sure this audience is no stranger to the dynamic 3D scenes. For example, in autonomous driving, our cars have to dealing with dynamic scenes all the time. We have to figure out where the cars are moving, where the people are moving, and where they may be in the future. So all this will require us to analyze the 3D scene from the sensor inputs and understand that the whole dynamics, semantics, shape, geometry information, all in one bucket in order to perform certain autonomy, for example for autonomous driving or assisted driving. And of course, dynamic 3D scene is not only on the street. We also have dynamics in the indoor environment. For example, if we want to have very capable home service robot or have a robot that can entertain and interact with humans, then we still need this capability of understanding the dynamic environment in order to interact and entertain properly in the environment. So the topic I'm going to talk about is scaling the 4D scene understanding with less hassle. In nutshell, it encodes several beliefs that we have been pursuing. The first thing is we want to build a model that can learn and benefit from large-scale data. And of course, we want to avoid the manual labels as much as possible, or manual designs as much as possible, such that the model can easily scale together with the data. And in the end, even though that we may want to learn from large amount of data, but we always want to learn from minimum human supervision, even though that data is abundant, but human efforts is always limited. So our goal here is to achieve very good performance, at the same time reduce the amount of required human labels. So in the end, our thesis encodes several concrete directions. Of course, the large model and representation learning has been very successfully demonstrated that the models can scale together with data, and the learning method is a major paradigm for us to achieve this scaling. And in this topic, on this topic, I'm going to discuss how we can learn robust 2D tracking and how we can, based on 2D tracking, to learn like high fidelity instance level representation. And of course, in the end, given the motion on 2D, we want to put them into 3D and really understand the dynamics and the motion in the dynamic 3D environment. So, okay, object tracking is a very basic problem in computer vision. People have been studying it for decades. And of course, in terms of autonomous driving, usually the topic we care about is multi-object tracking, even though there are also other flavors of object tracking. So in multi-object tracking, we know that the category, or usually we know the category of objects we are going to detect, and then we want to find the association of the same instance across the images. And usually when we perform multi-object tracking, we follow a fixed pipeline. We usually do like tracking by detection, which means that we will first detect the objects in each of the image, and then utilize certain motion models to propagate the objects from one frame to the other. And in the end, on the new frame, we will aggregate two types of information. One is appearance information, the other is motion information. Sometimes we even can safely assume that the object do not move. This can be a false assumption, but that assumption usually work very well. And based on those motion information and appearance information, we can do a joint optimization to figure out that what is the right matching between objects across frames. And usually this happens across adjacent frames. So one question we have been thinking here is, obviously people have been criticizing that the pipeline is so complicated and is also very fragile. So one thing we have been thinking is, when we do object tracking as a human, do we actually do motion estimation, or do we actually also do association optimization? Concretely speaking, when we're driving on the road, do we really try to estimate the motion or try to estimate the speed of the other vehicle? Or on the other hand, when we try to follow the car in front of us, do we really care about all the other 20 or 30 cars on the road in order to figure out what is the right correspondence? So the answer is actually not. It seems that we can do some simple study and realize that like human can actually associate objects very accurately without any of those motion or location information. Only by looking at the images or looking at the objects themselves, we can like reliably figure out like the correspondence or association of objects across frames, even in a longer time span. And therefore, the question we have been asking ourselves is, why doesn't the appearance provide enough information in current model? Of course, we did some experiments and figured out there are actually some problems in the most popular appearance learning method. And in the end, what we propose is called quasi-dense matching. The basic idea is actually very simple. When we have the ground truth labeling between frames, usually in the basic method, we learn from this pair of correspondence. For example, in this case, we learn from the ground truth label of these two cars. However, what we do is, instead of only matching or learn from the matching of these two ground truth cars, we try to extract all the possible regions of objects on the frames, and then try to match between all the possible regions instead of only the objects we label on the image. And of course, if you are familiar with the object detection pipeline, this is very similar to the region proposal network. Basically, from the object detection, in the two-stage object detection, we will usually first detect the objects or the possible regions of objects using RPN, and then do like a further classification of each possible region. And not surprisingly, we can follow a similar structure to do our quasi-dense matching and learn from this matching. Basically, we extract all the possible regions of objects from, say, two frames, and then we use contrast learning to match between all the regions. So this also provides more supervision for our association models to learn the association of objects. So usually, say, on this driving scene, we may have 20 objects to train the association. But when we consider all the possible object locations, we can easily scale up our annotation to 100 or even 300. So, and then we only use this embedding learn embedding to do association. At the test time, we can just use nearest neighbor to look for the similar objects across frames, just similar to how humans perform tracking on images. And here is a demonstration of the model result. You can see that on this very complex scene, even though there are many people walking around, and there are like very complex occlusion patterns, but our model can actually perform quite well, even though it's only rely on the appearance information without turning to the motion models. And of course, another criticism of multi-object tracking is usually we test on very small scale data. And the one thing we did to address this problem is to propose BD100K, which is a large-scale open driving video dataset. It can cover many different types of scene, different weather, and different time of the day. And especially on this dataset, we established a new tracking benchmark, which is like 10 to 100 times bigger than the previous ones, depends on how you measure the size of the tracking benchmark. So thanks to the large-scale dataset and also our flexible appearance-only tracking model, we can do quite reliable object tracking on this on those videos. For example, on the highway scene, you can see that we can track the like fast-moving objects, and even in the dark scene, which is even challenging for human eyes, you can see that our model can also perform like very well. Again, thanks to the large-scale model, that our model cover very different type of scene, our data cover many different type of scene, and also our model can directly learn from the data. Another thing is we are also evaluating our model on Waymo Open Dataset. So this is Waymo. This open dataset is also very large scale, and unfortunately the field hasn't like tested this a lot. We do want to have a shout out to encourage people to test your like best 2D or 3D tracking methods on this dataset. We can indeed discover many interesting problems on this large-scale tracking scenario. And one thing we found is you can see, even though that our method is very simple, but it can achieve very dramatic improvement compared to the previous method when we say release this model around 2020, 2021. So basically, the result shows that the appearance-based tracking can achieve very good performance without turning to motion or optimization. And another interesting property of doing appearance modeling is we no longer need to rely on tracking labels, actually. So for example, given a single image with a bounding box labels, we can easily scale or rotate the same image and form another image to train the tracking. Basically, in this case, because we know the ground truth transformation, then we can say find the cross correspondence between objects and then like use that to train our appearance models. So even though that this model, the data is really synthetic and does not reflect the true motion of the real world, but we actually found that the model can actually still perform very well. For example, on a small scale MOT17 dataset, we find that the performance is basically similar with a fully supervised data, fully supervised model. You can see that those are the two results. It's very hard to tell the difference, like which one is trained with the tracking label, which one is not trained with tracking labels. And another interesting property of like appearance-based tracking is also more robust to the speed of the video. So, for example, on MOT17, which is a very popular dataset, the original frame is in 30 frames per second, and you can tune your motion model to be suitable for this like high-speed video. However, we did some experiments. Say we downsample the frame rate of the videos, like say from 30 frames per second to 10 to 2 or even to 1 frame per second. So you can see that because the 2D motion is actually, when we downsample the videos frames, essentially we are speeding up all the objects, and the like motion-based method or the method rely on motion can like degrade very rapidly, but the appearance-based methods can still retain good performance. So another dimension that we are exploring in object tracking is not only tracking the common object we see on the streets, but also on tracking like every objects. Basically, we want to consider all the objects in the long tail distribution instead of only the 10 or 20 objects on the, we commonly see in our daily life. However, there are some like very interesting challenges when we consider the larger set of objects. So usually when we consider object tracking, we will first use classification of the objects to filter out the matching candidates. For example, when we try to do object tracking, track cars and pedestrians on the road, if we know that this is a car, that is a pedestrian, then there is no way that we want to match the objects of a car to a pedestrian. If they are two different categories, then there's no way that it can be the same object. However, when we consider tracking every object in the long-tail distribution, then the classification signal may not be as reliable. And therefore, the object categorization is no longer a good signal for filtering the association. So, but at the same time, we also find some interesting insight to solve this problem. So in order to have this same filtering scheme to figure out that what are good candidates for object matching across frames, we actually do not need to know the exact category. We only need to know that whether two objects are of the same category or not. So this is a very interesting angle. And we can say that instead of only matching cars to cars, people to people, we can say that, okay, we have some abstract model that it doesn't tell us which object which category it belongs to, but it tells us that whether two objects will be the same category. And we find that actually a much easier task and easier to generalize because now we are kind of training the model in the open world sense. So based on this insight, we design a new tracking pipeline. So we first have a called class exemplar matching module. Basically, this model using idea of exemplar classification. Given image, given two pair of image, we basically want to classify whether this image is the same or same category or not. And then based on this module, we can plug this into the tracking pipeline. Given a sequence of images, we will first localize our objects. And here we are only localizing the objects that we can potentially interested in. In other words, this is more like a class agnostic object detection. We found that, interestingly, even though that the object tracking can be object classification can be quite challenging, but the localization can easily generalize into new concepts. And then after we localize the objects, we can classify them into different groups, and then we can track within each group. And what's another interesting thing here is after we have many examples of the same objects across the temporal sequence, then we can come back to classify the objects based on the whole track of objects. Because now we have more samples of the same objects than only single image, then we are able to more reliably classify that object. And we found that this method can basically help improving the tracking performance for many different types of tracking methods and on several data sets. So even further, we want to push this into the open vocabulary setup. Basically, in the everything setup, we have limited examples for many categories, and we do have some example for the category we want to target. In the open vocabulary setup, we have basically no examples for many categories, and we want to generalize for the seen categories to the unseen categories. So in terms of classification for open vocabulary, basically we turn to some a common fashion. We plug in the clip models and basically distill our image head, so that we can predict the category of those unseen, predict the name of the category that we haven't seen in the tracking, in the training time. And people have done this for object detection or classification as well. But for association, we find that there can be something even more interesting. So in the previous slide, I talked about we can use data augmentation to augment single images and generate synthesized labels for training tracking. But now we also have AGC, or in particular diffusion model to generalize realistic images. And we were thinking that whether we can use this same idea or same model to generalize new data, which can be more realistic than just doing data generalization, data augmentation on single images. And we found that this can actually be quite helpful. So what we did there is, for example, given an input image, we have a description, and then we will retain that single image and basically paste that on an empty image. Say we have the elephant, and then we crop out the elephant of that particular object and paste it on a new image. And then we pass it into a diffusion process. basically in this diffusion, the difference here is we want to retain that particular object at the same time to generate the context, the background. And this is very similar to, say, using diffusion model for in painting, but basically the inverse fashion. We have the object, and then we want to paint the background. Then in this way, we can paint a new image, and then because we are retaining the old object in the image, therefore we still know the ground truth matching between the original image and the synthesized image. So in the end, we can use this type of model to train open vocabulary object tracking, and train this model based on this data set generalized by diffusion. And we found that without turning to any of the video supervision, we can achieve actually better performance than the supervised learning method, mostly because we are able to benefit from the clip and diffusion model, such that we can, say, have more powerful augmentation. And especially in the open vocabulary case, we do not have many examples for the many category anyway. So, well, a brief summary. So we have been working on appearance-only tracking, and we find it easy to scale to diverse environment, easy to generalize to new concepts, and robust to different motion patterns, and can even be trained with only images, and there are more ways to synthesize the data. And we have also been trying to scale up the tracking to instance segmentation, because of course we want to have high quality instance level information as well, instead of only bounding box. And one thing we were focusing on is how we can get high quality mask. And one thing we propose here is, so when we do the instance segmentation, usually we put the object into a very coarse mask, and therefore the segmentation quality for each instance is usually not very high. And what we propose is we basically iteratively break down the image into finer granularity and predict that which region we need to further refine, and then build a called tree structure on the image, such that we can still have the fine prediction on the image, but at the same time we do not have to pay for all the computation that we need to do for each of the pixel location. Let me skip the diagram. And here are some refining process. You can see that our results are quite encouraging based on the iterative refinement. And also compared to the previous method, our model can also perform very well. Another direction we are extending this is, of course, we are interested in 4DC understanding, which have to be predicted based on videos. Therefore, we also use the same idea on videos, and we find that our model can automatically attend to different frames and try to learn to aggregate information from different frames in order to refine each segmentation of each image. And for example, in this case, you can see that we predict, compared to the previous state-of-art method, our method can predict very fine boundaries of the objects in the video. And of course, on the driving scene, we can achieve the same results. And we can, for example, for this person, we can get much better segmentation than the previous method. One interesting thing we find is our method can sometimes actually generate better boundary or sharper boundary than human annotation, which is understandable because the model can look at many data and then it can aggregate information from many different annotations. But at the same time, it's always very cumbersome for human to label the data, and sometimes it's just at the cost of the annotation quality. So therefore, we further extend our work to think about how we can avoid all the labeling masks altogether. One thing we did here is basically we consider based on current image-based instance segmentation and extend that into the video domain. And basically, we consider using temporal consistency for the videos as a loss to train the segmentation. So our idea is very simple. Basically, we try to extract patches across frames, and then say that if the two patches are very similar, then they should have similar segmentation across frames as well. So you can see that, for example, compared to the previous image-based segmentation, our methods can perform much better and more consistently across videos. Okay, it seems that the frame is not synchronized. Okay, here we go. And here is another video demonstration of the results. So it's worth emphasizing again that here we generate those video segmentation without using any mask annotation. And we are only using bounding box annotation on images to learn how to segment the instance in a video context. But we do learn from videos like in the self-supervised fashion. Okay, so now we have all the tools to analyze objects in 2D. We have appearance-based tracking, and can be very robust and can scale to large-scale dataset. And we also have high-quality instance segmentation. So on 3D, we have also been thinking about how we can basically alleviate the 2D prediction to 3D. One thing is, of course, obvious direction is to seeing depths from single images. And the one thing we did there is, instead of directly predicting the depth at each pixel, which is quite challenging, we will first learn to group the pixels together, and so such that our model can learn interactive bags for each group, and which turns out to be easier than learning on each pixel. And it's worth mentioning that here, when we're talking about grouping, we are talking about like automatically discovered grouping from only depth supervision. Our model do not rely on any instance segmentation or like a semantic segmentation in order to do the grouping. So this, as you can see, that grouping here, basically we can put the different sofa together, and this grouping is automatically discovered by the model itself without any supervision. Well, if you are interested in the model, here it is. But in the end, we find that our model can achieve very good performance. And for example, in this case, on the outdoor scene, you can see that our point cloud predicted by only single image is actually very similar to what we can get from LiDAR. And so all the geometry information seems to be retained, and at the same time, we also have denser prediction because, of course, image has more information or more scan lines than LiDAR. Okay, so here is another demonstration for the top-down view for the same prediction. And of course, the method can also work in indoor scene, and we find that the same procedure can also benefit for the indoor depth prediction as well. And of course, in the dynamic 3D environment, we are not only interested in the pixel level of 3D prediction, we are also interested in like object level 3D prediction and how they are moving in the environment. So we find that by combining everything we have done together, we can build a very simple baseline, basically to do the object detection on 2D images, predict their 3D property on 2D images, and then track them together. And when we have more images, we can use 3D information to, say, connect all the objects. And again, this is the results on WeMo dataset. So even though that we had a very simple like tracking model, not very fancy, but you can see that the model actually performing very well, especially in this very complicated scenario. On the left, we have the perspective view of all predicted 3D bound box, and on the right, we have the top-down view. And of course, WeMo datasets also have many like net scene data, and we can also, our method can also benefit from a large amount of data in the net scene and track the object reliably in this challenging scenario. So finally, we realized that when we want to do 3D object tracking, especially for autonomous driving scenario, we are not only having single image, we actually have surrounding view. And what's the difference between the surrounding view and the single like frontal view is on the panoramic view of on the car, the object will never disappear unless it's occluded by something else. That's actually provide us some stronger cue on how to associate objects together. So we know that if an object disappear from an image, very likely it may appear in another image. And therefore, what we did is we first track objects across different views, and then try to associate the tracks across different views, across different time steps. Basically, we have this two-step tracking, and we find this method can work much better than single view, than tracking objects on each view individually. And of course, if you do not have a panorama view, even if you have multiple views that can be stitched together, then the method can still benefit, still be benefited from the data. And in the end, we find that in terms of 3D object tracking, we are witnessing like very fast progress. Like in around 2021, we are able to achieve like much better performance than the previous baseline, called center track. And this year, we are able to achieve, or last year, we are able to achieve another very big improvement. So, and now we are also seeing that by basically here, all the results are running on Res 950. But if we can switch in like a bigger backbone, like say Convex or like a bigger, say, foundation model in computer vision, and of course the whole performance can be further improved, and we are seeing a converging effects between the camera-only results and LiDAR-based results. Okay, so that's basically concludes my talk. So here I hope that I convey that we can, by designing like a proper learning, representation learning method, we are able to scale our methods into large-scale data sets. And also we can achieve this with fewer and fewer manual labels. And we can do this from different components like 2D tracking, segmentation tracking, and 3D object tracking in order to achieve whole 4D scene understanding. If you are interested in details of our projects, so you can always find out the information on our project webpage, vis.xyz. And we also have all the code available online. Okay, so that concludes my talk. So we can have some questions, guys. Or probably we can discuss whether we will have sandwich or some other thing, something else today for lunch. Yes.
Maybe one question that comes back to what we discussed earlier. What is an object to track? When do objects separate, and when do you consider something as one object? Yeah? So for example, you showed the elephants, if they walk in a line, kind of like in a train, is that the train of elephants, and do they then separate? Or when you think more about robotics applications, I have a tray with something on top, and that's carried so it moves consistently, but there are actually several objects on it. How do you think one can unsupervised learn the concept of object? Yeah? So what's separable, what's not? What can you pick up without moving all the rest?
Yeah, that is a very good question. So far, when we consider object tracking, we are basically driven by a particular data set or application. For example, if the data set is for autonomous driving, then we know that usually we care about the cars instead of the wheels or the car windows. And we care about the pedestrians as a whole instead of, say, only tracking the human head or like human arms. So that is one aspect. So basically, there are different domains, and on different applications, there are different definitions of the objects. And what we do is we want to define a general learning method such that whenever you plug in your object like concept, then the method will still work, and such that it's not tuned to a particular type of objects. And this is also the advantage of doing this, say, appearance-only like tracking. So because now you can just only tell me that appearance of your target objects without telling me that, without me assuming how the object will move. Then I can just check the objects across the frames. So I think in a bigger picture, of course, there is this very large-scale study on segment anything. And we are also quite interested in this to see that whether we can have some, say, code foundation model for tracking to see that whether we can just simply track every object, and then we can make the decision online at the inference time to decide that, okay, which one we want to track. In this case, no matter what the human point to, then we can always track them across the frames. Yeah.
Thank you for showing all your exciting tracking work in such context. I had a question. What's the dependency of complexity of some of your top methods on the amount of movement the object can do between frames. So you said, okay, maybe you can track with one frame, or like how expensive is it? Often, object in the camera can move significantly, especially if they're close to the camera. Just curious.
So usually because our methods are only depending on the appearance of the object. So no matter how fast the object moves, then it doesn't change the complexity of the method itself. And in terms of concrete matching, usually our complexity is just like incremental compared to the detection model. So we add, based on our tracking methods, we only add a marginal cost on the object detection itself, without, adding like a huge amount of computation to analyze the whole sequence. And our methods can be done online, and also without turning to the post optimization. Then only using nearest neighbor search, the method can actually perform quite efficiently.
So you mentioned that you're kind of disregarding motion models in this pipeline, but do you think that you can take the same representations and plug it back into an original classical pipeline and use motion models, or is it kind of in contrast with that?
Yes, so in principle, that is possible. We actually did quite some studies on that. And what our conclusion is basically for a lot of classical motion models, like just common filter or IOU tracker. So if you have a lot of data, usually the appearance-based only methods can provide basically all the tracking performance you need. Adding a motion model may give you another 0.5 motor, but of course give you additional complexity may not be worthwhile. And you're especially in the long tail distribution or open vocabulary tracking. So the motion becomes so complex, we cannot even find a baseline to model the motion. So in summary, yes. So if you know that you have particular information about your target objects, then you can still plug in our appearance. After all, it's just you can always treat it as the appearance module of your overall pipeline. But we find usually that appearance only can give you most of the performance you need. There's another question.
Okay. Hello, Professor Yu. So I want to ask a question for fresh PhD student. So there are so many neural network learning based method every year, and for you there are maybe 10 new papers every year. So for new students, how can they follow your work? How can they go into this area among so many papers?
Well, that is a very tough question. Well, I would say for sure, the reason you are asking this question is because there is no, concrete answer or absolute answer for that question. It's same as what is artificial intelligence? How do we define the artificial intelligence? So those are the type of questions that it will be very hard to give you a definitive answer. But usually what I will encourage people to do is to at least at the very beginning, you can try some problems to figure out what is your true passion is and what is the problem that you are most interested in, such that you are quite motivated to dive deeper into it for the coming years. And I believe that is the most important for PhD students. And another important aspect is I believe that PhD study is about what is unique perspective you can contribute to the field. So, and in this process, in the process of research study, or especially in the early stage of acquiring research skills, you probably will realize, okay, something you can see or you can think of is usually missed by the others. So just as a common analogy, so even though we all have human eyes, we all have eyes and we can see things, But in terms of neuroscience, every one of us is actually seeing different things for the environment. Like it's not like every one of us is seeing the same reality. So in truth, it's actually every one of us is seeing slightly different version of reality. So it's the same for research. So every person is using their own thinking and using their experience to try to solve their concrete research problems. And the important thing is how you can contribute your unique perspective such that we can have collectively deeper understanding of the problems. Okay.
So Dr. Anka Dragan is an associate professor in the EECS department at UC Berkeley, running the Interact Lab, which focuses on human-robot interaction algorithms. Her work spans diverse applications, including assistive arms, quadrotors, autonomous cars, drawing from numerous disciplines such as optimal control, game theory, reinforcement learning, and cognitive science. As a co-founder and steering committee member of the Berkeley AI Research Lab and the Center of Human Compatible AI, Anka plays a significant role in AI research.
Hi, everybody. I'm Anka Dragan. I'm excited to share a little bit with you today of the latest work we've been doing on human models, human prediction, learning good, robust human prediction models for use in autonomous driving, as well as in other interactive applications. And the focus lately for us has been on how do we robustify these models by really improving the representations on top of which they're built. And so I think in an autonomous driving workshop, I don't really need to motivate that it's very useful for robots that interact with people to have predictive models of their behavior. So we want the robots to have this mental model of pi h, the human's policy. And I can't write this down. So of course, this is something I want to be able to learn from data. And so, the easiest thing is to build some sort of black box policy that conditions on state or history of state actions and produces a distribution over what the next human action might be. And this type of work has been really great at capturing interesting nuances in human behavior. So, here's a very simple one. So it's actually on the LSTM from back in the day. And it's, it's kind of tracking exactly where the person will go. And everything's great as long as we're querying this on inputs that are in the training distribution, right? So if we induce distribution shift, kind of all bets are off. And so here you see the ground truth, the prediction. We introduced a kind of a new exit that the person is going to that wasn't in the training distribution. And now the model is kind of going all guns blazing, being very convinced that the person will kind of turn to the right. That's not even an exit. That's sort of the entrance part. And then after we pass that, it's starting to get convinced that, the agent will kind of turn around and kind of plow through the middle of the intersection. And so distribution shift is tough for these models. And of course, we don't just see that in driving. Here's a little benchmark task that we put together that's a while ago in 2019, actually, that's called Overcooked. It's inspired by the game Overcooked that we used to play a lot. So this is a kind of, you have two avatars, it's going to be two human players, and they're working together to cook onion soup or tomato soup or whatever it is. And so there's sort of these places where you get onions, you get plates from here, you go and, boil onions and so on, and you make soup. And then you deliver over here in the gray zones. And here's humans playing together. So this is a recording of two humans controlling their avatars, playing together. And you see kind of its, beautiful coordination. They figure out which way around this place to go. They each get onions, blah, 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 put them there. One's going for the plates, one's going for the onion. It's working together very nicely. And indeed, when we learn when we use behavior cloning, imitation learning, to learn a policy for human behavior based on this, it does pretty well. So here you see two sort of learned policies playing together. And And as one is sitting with an onion, the other one goes and grabs the plate. One is delivering, the other one is grabbing more onions. So it's working. They're making onion soup. They're actually coordinating beautifully with each other. Everything's great. But then you take a plate and put it on a counter over there on the left, and you run the exact same policy. And they're going through the motions, but what they're doing, if you look closely, makes no freaking sense whatsoever. So the one on the left is just wandering around with a full plate of soup, not really delivering it. This other one on the right delivered it to the counter instead of to the gray area. So it's all of a sudden this whole notion of, we're making soup and we're delivering it out the window because, oh my God, there is a plate on the counter, which, probably never happens in data, or if it happens very rarely. So it's totally new state, cannot make sense of it. And this kind of brittleness is not something we can really tolerate, especially in sort of, situations where the penalty isn't just, the robot doesn't predict accurately what the human is doing, so what? But in sort of in self-driving, where you actually need these human predictions to be pretty good if you're going to rely on them. And so, it's no news that high capacity models can fail on their distribution shift. What I find interesting is that in interactive situations, we're sort of asking for distribution shift, right? So here's a driving setup that Durst and I worked on back in the day. And you see an autonomous car in orange needing to merge into the left lane, and there's a human-driven vehicle over there. And what Durst and I were thinking about back then was that if you just make these predictions about the vehicle in white kind of in isolation, as sort of the case in the literature back then, you'd sort of predict, okay, the person will keep going forward and you'll be stuck sort of either merging behind the person if there's enough gap in traffic, but if not, you'll just keep on waiting for that gap in traffic to open up and maybe sort of miss your turn altogether. And so we were thinking, well, hold on a second. Actually, we need these autonomous cars to understand that their actions end up influencing the actions that people take. And so we did all this work on how, you can actually model the reaction that people will have to the actions that the autonomous car is planning on taking, so that you enable the car to understand that if it starts nudging into the person's lane, chances are the person will slow down, and then it'll be able to kind of create that gap in traffic for itself. So why is this important for human models and distribution shift? Well, basically because if I learn a policy of how the person acts, now the robot, as it's acting or planning how to act or learning how to act, it changes the state, which can very well, through its actions, essentially end up changing the distribution of the inputs for the human policy. In other words, when I do planning or RL up against the human model, I'm really stress testing that model and perhaps querying it on hypothetical actions or plans that are very much outside of the training distribution that we saw in sort of human-human interaction that we trained the model on. And so high capacity models can fail on their distribution shift, and I think planning an RL in response to these high capacity models for human behavior, it tends to really induce distribution shift. So that's a problem. It's a problem for driving, it's a problem for interaction in general. And so it's natural to ask, well, how do we learn more robust models? And the idea that I'll explore in this, or the kind of the high level view I'll explore in this talk, is that a key to learning more robust models is being very careful about the representations these models are using. So I want to turn the notion of how do I learn more robust models to kind of the sub-question of how do I build more robust representations for these models? What does that mean? And I wanted to share with you two works we did in this space very recently. The first one is inspired by what's happening in language. So if I have a sentence like the kid was eating a cake, before GPT was Bert, and what Bert was doing was sort of, okay, we tokenize these, and then we take a sentence like that or a piece of text like that, we mask certain tokens, And then we train a model to predict them, conditioned on sort of the tokens that we didn't mask. Okay, so this was this sort of infilling, this kind of randomly masking parts of the input and predicting them. It's sort of a kind of this big breakthrough in natural language processing that made the shift from, you know, LSTMs and such to RNNs to for generating text to transformers, and that's what GPT models are based on now. And so language is this sort of sequential task, but in a sense it's made out of just like one action after the other, the words. Behavior is a little bit more complicated, but it's very much a sequential task as well. In general, whether we're interested in human models or not, in the most general sense, you can think of behavior as you're in a state, you take an action, you receive a reward, maybe you get to see that, maybe not. You're in a new state, S1, you take an action, you receive a reward, and so on and so forth. So it's a sequence, not of words, but of state, action, rewards. And naturally, you can start asking, well, what happens if I were to start masking some of these and use a transformer to predict what I masked? What if I train behavior models in this way? And in particular, focusing on this current prediction, this current inference that the slide is showing, this current query that the slide is showing, what I'm doing is I'm taking S0, A0, S1 and trying to predict the action A1. So I'm looking at approximating the probability of A1 conditioned on S0, A0, S1, which lo and behold is basically one of the inferences you need in behavior cloning, right? So in imitation, that's the kind of question we want to ask. The person was in S0, took action A0, then they were in S1, what will they do next? That's the kind of thing I need to be able to predict. And so, with behavior cloning, you can, once you've trained such a model, you can say, well, in S0, what's going to happen? You observe that, you condition on it, you observe that you transition to S1, what's going to happen, and so on and so forth. And so you can unroll this. And each of these queries, right, corresponds to an inference. The first action, and so on and so forth. So, and more generally, if you think about other masks, not just the ones that I'm showing on the slide, they each correspond to an inference task. And it turns out many of these inference tasks are useful. That was my student Micah's observation. So behavior cloning corresponds to a bunch of masks where I've observed some state action so far, and I'm asking what the next action would be. Offline array reward conditioning basically is I'm in S0 and I'd like to get really good reward. What do you do? Go. Goal conditioning is I'm in S0 or this is what happened so far and I need to reach this state ST. What do I do? Waypoint conditioning, where we say I'd like the agent to pass through these points, kind of I want to model human-like behavior that passes through these points. That's a different mask. Past inference, where I'm driving, I might say, here's a state where there's an accident. What naturally might have happened? What sort of states might have naturally led to that? As kind of a debugging tool. Future inference, which is the forecasting problem of just predicting a full trajectory going forward. And then you can also, make inferences about forward dynamics or inverse dynamics. And so what's cool about masks is that they correspond in behavior much more so than in language to very natural tasks you might actually want to do with a model. And by thinking of all these different tasks as masks, you can actually, it kind of naturally leads you to this idea of let's have a single model flexibly represent many different tasks that we're interested in. And so if we want to do behavior cloning, right, if we want human models, well, we could do behavior cloning in the traditional way by basically training as a behavior cloning thing. Or Micah thought we could train on a bunch of different tasks. Or we could even train a model on random tasks or random masks, because every mask is equivalent to some possible inference you might want to ask to make among these different sort of pieces of behavior. And so Micah said, well, instead of training on just behavior cloning, maybe we should be training on multiple proxy tasks or even random tasks. And going back to the question of robustifying models and building more robust representation, the idea Micah had was essentially that pre-training on a diversity of tasks ends up extracting a better representation out of the same amount of data. So if I want a robust model, yes, I could do behavior cloning and call it a day, or Micah proposed I could train on a diversity of tasks, and then maybe with random masking even, and then I can fine tune. For instance, I can fine tune for behavior cloning. So I could use a zero shot, but I can also fine tune to increase performance further. And from that perspective, what sort of the training on random masks or multiple tasks does is it really helps you get to a good initialization, or you can think of it as a really good starting representation for the task, which sort of really improves, we think, so the power of what you can get out of the data. And so, if you do this, you get a single model that can do many different tasks. And I'm actually going to skip this. There's just a bunch in mini-grid, a bunch of different examples of here, you can condition on the goal, you can do backwards inference, you can condition on it getting exactly 3 reward, and so on and so forth. I think this slide is more interesting. So here, we're saying these are 3 waypoints for time 0, 3, and 6. And you can start asking the model, well, what might have happened at S4? Given that you're already by that door, probably what happened at S4 is that you're either one of those 2 blue cells. It's pretty convinced that at S5 you were right before that. At S1, you probably went forward, you might have gone left, who knows, and so on and so forth. And so we looked at how this compares to specialized models. And we've noticed a few interesting things. One is that random masking with then fine-tuning for the task example behavior cloning is actually better than specialized models. It's just sort of in line with our hypothesis that this provides kind of a good representation to build the fine-tuned model on. And then random masking pre-training zero shot is actually about on par with specialized models, which I think is also a pretty interesting observation. And so that was the idea, that we can squeeze more out of data if we're really careful about what tasks we use, and sort of what we can borrow from, foundation models, blah, 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 is this idea of pre-training and then fine-tuning. And it really matters what tasks you use for pre-training. So even if you want to do behavior cloning, if all you want to do is imitation, it seems to be helpful to be actually pre-training with a diversity of tasks and forcing the model to understand how to do backwards inference, how to do inverse dynamics, and so on and so forth. So that was idea 1 for building more robust representations. And it really had nothing to do with people, right? We're just here's how you can squeeze more out of your data. Idea 2 has a lot more to do with people. So idea 2 is that if we try to model humans, so far, we've been kind of talking them as black box policies. But humans are not arbitrary. We don't just take any possible action. The space of actual policies a human would take is probably much more restricted. And the reason is that humans act the way they do because they make decisions, because they're agents who are driven by intentions, objectives that they're trying to pursue. And so a way traditionally we've captured this is to say that, humans are driven by some reward functions, goal, and that they're trying to maximize, and that sort of explains its behavior. Of course, that in itself is not enough. So you can do inverse reinforcement learning based on data, extract the reward function, and model people as approximately optimal on that reward function using something like Boltzmann rationality. And if you've seen previous talks of mine, where, we did 50, 60 papers on this topic, and we're not the only ones to have explored it by any means. It's a useful model, but the problem is it doesn't actually predict human behavior very well in some situations. So this is the lunar lander task where, people are trying to land in between the flags, and you can see that they're not really optimal. They might be Boltzmann rational for like a very low rationality coefficient. And in Overcooked, which was this collaborative benchmark we talked about, in Overcooked, the crazy thing is that this is a graph that shows loss for behavior cloning, the checkered, the hashed pattern, versus the sort of Boltzmann rationality, people are approximately optimal. And you see that people are approximately optimal is a model that's basically on par with random. And so people aren't random in Overcooked, but they're suboptimal. They're so suboptimal that assuming that they're Boltzmann rational doesn't really get you very far. And so if people aren't arbitrary and they're intent driven, but just kind of assuming they're reward optimizers doesn't actually cut it, then what can we do? And what we've been thinking lately is something in a sense very obvious, which is that maybe the rationality assumption is not useful as like a way to build a model, but it's useful as a way to build a good representation. So similar to sort of before, we're thinking that retraining, in this case, with optimal behavior, so to imitate optimal behavior, ends up extracting a useful representation that then when you fine-tune on human data, you end up doing better. And that's what Masoud and Micah explored. So this is a workshop paper, but basically what they did is they took Overcooked, they trained agents through self-place to kind of approximate optimal behavior. So these agents would be sort of near optimal playing with themselves. And they didn't say, well, that's a good model of human behavior, because that's also a terrible model. But what they did is they said, this is a good initialization to then run behavior cloning on top of and imitate human data. And they found some pretty good results. I won't go into the details here, but they found some pretty good results with that. And then, oops, how do I get my mouse back? Whoops. Nope. Never mind. So, and then Cassidy, an understudy of mine, took this even further and said, we can do even better if we're just a little bit more careful about what we mean by an optimal kind of behavior prior. When we say, well, just kind of pre-train with optimal behavior, then fine-tune, that's sort of the kind of the most naive idea. But Cassidy thought we have to sort of revisit what we mean by optimal behavior, and we can get a prior that's actually much more useful, much more representative of human behavior. And his observation really relied on this notion of systematic suboptimality. So Cassidy said, look, this is Overcooked. If you see the person, what's optimal for the person might be to go counterclockwise. If you see the person actually go clockwise once, they're probably going to do it again and again and again. They're not just going to like turn around and start doing the task counterclockwise, right? So people have these biases, but they're somewhat systematic. So if they make a mistake, they kind of tend to repeat it. If you go to the left of the pole, usually you're going to go to the left of the pole again, even if maybe to the right of the pole is a little faster. The challenge with just assuming people are approximately rational is that, we're treating a trajectory as being proportional to the exponent of the cumulative reward. And if you're trying to ask, well, what's the next action going to be? You only need to know the current state. The history completely disappears. And so if you observe the person being suboptimal once and go and say to the left, that's not going to influence at all what you're going to predict in the next state. Or even if you see them in the exact same state again, that history is going to be completely forgotten. Boltzmann doesn't care. Boltzmann is going to always say, to the right is slightly better, so the person's more likely to go to the right. And so Cassidy thought we're never going to capture systematic suboptimality if we're predicting distributions over trajectories or distributions over actions conditioned on state. Instead, we really have to go beyond trajectories and couple action choices over time by predicting distributions over policies. Okay, so if you think about what a full policy is a full mapping from state to action. And that is the object that we should assume is approximately optimal, not the trajectory. So what does that mean? We created this Boltzmann policy distribution. So instead of a Boltzmann sort of trajectory distribution, now it's a policy distribution that says the policy return in expectation is, proportional to the exponent of the expected cumulative reward. The probability of a policy is proportional to the exponent of the expected cumulative reward of that policy. And so instead of looking at cumulative reward of trajectory, you look at expected cumulative reward of the policy, and that sort of gives you distribution over policies. And so now when you're trying to run an inference, like what's the next action going to be? Well, the previous actions that the person took actually matter. The only complication here is that it's really difficult to maintain a distribution over policies. And Cassidy had a really cool idea, which is inspired by how you train GANs, and it's to condition a policy on a latent vector and do implicit variational inference. So basically to train this such that when the latent vector is sampled from a normal distribution, the policies are sampled from the Boltzmann policy distribution, and then you can run inference online as you observe actions and change the distribution over that latent, essentially changing the distribution over policies. So lo and behold, even without any, we haven't yet tried sort of like taking this and fine tuning, but what we tried was you train this without any human data, and then in an episode online, you observe human actions and you infer a posterior. And so with a ton less data compared to behavior cloning, you see in the orange bar here, you're getting almost on par performance with behavior cloning, which is so cool. And so by just doing this change from distributions over trajectories to distributions over policies, you end up with a lot less human data almost matching performance of behavior cloning. And so I'm excited to take this further and think about sort of the ideal combo of the two and really maximizing what you can get out of a lot of human data as well. It also works better in collaboration. And if you put a plate on a counter, you've trained with this Boltzmann policy distribution, and so stuff doesn't break. It's amazing. Okay, so how do we learn more robust models? I think we focus on more robust representations, and I've shared two ideas for doing that today. One is to just pre-train with multitask or diverse tasks or even random masks, and then fine-tune to get what you want. And the other one is to kind of leverage somehow the fact that people are not completely arbitrary and not use optimality as the definition of human behavior, but use it as a prior that induces a good representation to then build your model on. So thank you for listening, and thank you to my collaborators. I especially want to call out again Micah, Masood, and Cassidy, who were the main authors on the work that I talked about. Have a good rest of your day and enjoy London.
Hello everyone, welcome back to our third session. Hope you had a good lunch. We had a small change in schedule. Our next speaker is going to be Dr. Alexander Amini, who is a postdoctoral associate at MIT under Professor Daniela Rus, and is also the co-founder and chief scientific officer of Themis AI. Alex holds a PhD from MIT, and his research focuses on developing autonomy and safe decision-making for autonomous agents. And his vision involves adapted autonomous agents that can learn to navigate complex and uncertain scenarios. His work covers learning end-to-end control for autonomous systems, modeling confidence in neural networks, mathematical modeling of human mobility, and inertial refinement systems. And his expertise spans the realms of AI, autonomy, and mathematical modeling to enhance agent performance. Please join me in welcoming Alex.
Thank you so much. Let's see. Excellent. So good afternoon, everyone. My name is Alexander Amini. I'm a postdoc at MIT and CTO of Themis AI. And today I'm very excited to share with you a bit about our research in developing an end-to-end learning solution for robust and scalable autonomy. So like many of you, my dream is really to achieve or to have autonomous systems that can scale and be seamlessly embedded, working together with all of us helping us in our daily lives. And today, technologically, we're at a really exciting place because we're starting to see these little pockets of autonomy start to appear in society already. But what we have not reached yet is really this scalable vision that we really dream about. And that today is what I'm going to try to focus a little bit on and really try to nail down on some of the fundamental challenges that I think that we still face for modern AI in autonomy. So namely, today's systems are very, very vulnerable to these unexpected changes and edge cases, and they need to be able to really handle these dynamic scenarios and the ability to handle diverse sensing modalities that we want to ultimately integrate together. Now, in our research, we are inventing new AI solutions that are capable of scaling autonomy to the next stage by achieving this extra layer of robustness across every single stage of the learning lifecycle. And essentially, what I want to tell you about is how this requires a bit of rethinking in how we structure the foundations of intelligence for autonomy and how we structure the autonomy stack for an autonomous agent. And that starts all the way from the data that we train our autonomous agents on, to the models that we learn on that data, all the way to the algorithms that we deploy with. Now, in today's talk, I will share 3 stories about how we are, or some of our recent efforts in how we're working towards this vision of robust and scalable autonomy across this learning life cycle, right? Beginning first with a new data-driven simulator that is enabling this real-world transfer automatically from synthetically generated perception data. Then I'll share work in designing new robust learning algorithms and learning models that are actually capable of fusing multiple modalities of sensory data so that we can achieve added layers of robustness, and we'll show how that can actually lend very nicely towards scaling these systems. And finally, I'll close this pipeline by addressing how we can scalably deploy in practice autonomous systems through very uncertain and risk-aware scenarios. Now, it all starts with the data that we build from, and in autonomy, we face some very difficult decisions in how we collect our data, right? Because we're ultimately going to be deploying in the real world. This data collection phase is ultimately a very critical phase in the pipeline. Now, simulation, as many of you know, has emerged as this really exciting avenue for training these types of AI models. But the challenge is that most model-based simulation engines fail to effectively enable this real-world transfer into society due to this infamous sim-to-real gap. Now, on the other hand, data-driven simulators are fundamentally different, right, in that they are built and are modeled entirely from real data of the real world as opposed to predefined models of the world. So in contrast to the very well-studied sim-to-real problem, our simulators are what are known as real-to-sim. Instead of sim-to-real, they are now real-to-sim, and pave a new path towards really this robust and scalable autonomy by leveraging these massive data sets that we already have access to at our disposal and using them to scalably build very large-scale simulation engines and brand new synthetic worlds. So we have built this very powerful new data-driven simulator called Vista that enables this advance and moves us closer towards robust and scalable autonomy and transportation systems as a whole. Now, Vista is very unique in that it is fully data-driven, which means that it can harness the power of real data that we're able to, use and therefore synthesize brand new data in a very, very high fidelity and scalable fashion that includes, simulating or synthesizing these harsh edge cases, which are too expensive or simply too dangerous to collect in reality. Now, we can also train autonomous control agents directly within Vista, and we have open source Vista becoming the first data-driven simulator for mobility. Since its release, it's actually amassed over 9,000 downloads, independent installations with about 100 independent installations coming every single week. Now, I want to give you an overview of how Vista works and how it actually operates. So Vista leverages, like I mentioned, this real-world driving data set instead of pre-modeled scenes to simulate brand new data. So within Vista, you can train a machine learning model to learn control policies end-to-end entirely within that simulation engine. And the goal would be, after we learn these models, ultimately to achieve direct deployment into reality, into the real world. So we can start with raw data that we collect, which you can see on the left-hand side of a human driver just driving down a highway. And then the goal is going to be to achieve the simulation or the synthesis of a brand new perception sensory data, which you can see on the right-hand side, of a brand new car, not driving straight down the highway anymore, but now oscillating down this road. And using our simulator, we can actually synthesize this brand new trajectory, here you can see it on the right-hand side, of this same road, but now of this virtual agent. Now, to step through how this works in the case of camera data, this is just a very brief overview of the technology. Let's start with a very simple example, and let's start firstly with a single RGB example of a video frame that we collect from a camera sensor mounted on the dashboard of our car. For every pixel in the scene, we can also achieve some estimate of depth. Either this comes from a monocular depth estimator or from a LiDAR sensor, which we can densify and get this depth information from. With this combined information, we essentially now have a measure of both color as well as depth, and we can project every pixel into our image, from our image into this three-dimensional Cartesian space. And in fact, from extrinsics, we also know exactly where the camera was within this space as well, so we can even visualize it in this space. And we can take out the original camera, we can place in brand new cameras into the scene, brand new virtual agents, if you will, and synthesize their views as they move through the scene as well. And with this framework, we can also now simulate, very high fidelity, data-driven perception of brand new viewpoints for brand new sensors and brand new agents that are being deployed in the scene. So we can really achieve this very highly scalable approach to enabling the generation of thousands of kilometers of synthetic data at a time from all of the data sets that we already have access to. Now, like I mentioned, Vista is data-driven from the ground up, which really means that it combines real data with concrete physical properties and the laws of sensing that we have in all of these different sensors, like cameras, LiDARs, and so on, to achieve this type of high fidelity modeling. Now, this includes, like we already saw, the camera sensor, but what's really exciting is that we can also do this with other types of sensing modalities by modifying the approach of how these physical sensors operate in the real world. So as opposed to cameras, which passively take in light rays from their environment, LiDARs operate slightly differently. They actively project out rays from their source and measure time of flight, essentially, to their distances. And we can also simulate these in a data-driven fashion as well. Event-based cameras are also an extremely powerful source of data. These measure asynchronous light differentials, basically very fast changes in light in your pixels, in your camera data. So in comparison to cameras which roughly operate at a scale of 30 hertz per second, event-based cameras operate at tens of thousands of hertz per second. So they're extremely fast, they're extremely robust, especially in high dynamic range situations. And in Vista, we've actually achieved the simulation of these types of sensors as well. Now, these diverse sensing modalities are actually only one of the key benefits and aspects of the tunability and modularity of Vista that I want to tell you about. We can actually extend this framework and this data-driven philosophy, if you will, to the environmental level, beyond the physical level of sensing, all the way into the higher level of environments, allowing us to rapidly scale simulation across tens of thousands of kilometers in a variety of weather conditions, lighting conditions, geographic conditions, and so on. So for example, here you can see basically even multiplexing those different types of environments together to achieve an even greater scale of the different types of places that we may want to test our autonomous vehicle in. And here you can see, the same scene represented in two different types of weather conditions. Here simulating, using generative techniques, different types of flora in the environment, shadows, weather, and weather artifacts in these settings. And this is very powerful because we can really assess the generalizability of our systems and also create different versions of the same base environment that we collect. Now, the one last point is that in Vista, we can even build these data-driven models beyond perception data all the way into behavioral data as well. So here you can imagine, taking these very large-scale open traffic data sets, and oftentimes these are labeled with trajectories that we can extract, train machine learning models on, and then use these machine learning models to sample brand new trajectories in a data-driven fashion that we can simulate, an infinity of different types of scenarios that we may want to test our vehicles in. And this gives us a very modular way of testing both behavioral effects with these types of data-driven behavioral models combined with the perceptional systems and the perception backends that I showed earlier to create a very, very powerful data-driven suite. Now, the core of Vista is really in its physical sensing modalities and spans these three modalities that I mentioned earlier. And because it's an entirely data-driven engine, we can now think about this unification of all of these sensory modalities by using the structure of the underlying physics of these different modalities in their own right. Now, the ability to perceive these multiple modalities and sensors is actually critical when we talk about scalably deploying an autonomy stack into the real world, because all of these sensors provide a level of redundancy in the wild. Modern autonomy stacks are heavily redundant and equipped with multiple of these sensors. Here you can see three very commonly used sensors and talked about in the industry as cameras, lidars, and radars. And each of these sensors provide a very unique benefit, pros and cons when deployed. And you'll see many of these stacks not only being equipped with multiple types of sensors, but more importantly, multiple copies for redundancy and added robustness. Now, the fundamental technical challenge now is obviously, we have all of these sensors. How can we effectively harness all of that data that comes in very different forms from these different types of modalities so that we can process it in a robust and scalable way? Now, the problem here really arises from the fact that these view discrepancies between these different sensors. For example, camera features are oftentimes in the perspective plane, right, captured in images. However, LiDAR and radar features are oftentimes represented in a three-dimensional space, or at least a bird's-eye view, two-dimensional geometric space. So finding a shared representation from a learning perspective that we can build a robust model that can leverage both of these types of features is a very critical task. So the shared representation, there are two key points that we want to keep in mind here. Number one is that shared representation should be very easy to convert all sensor types into. And number two, it should be able to do that conversion in as little informational loss as possible. And finally, it should be very suitable for a variety of different tasks, whether those tasks be end-to-end driving, like we focus on a lot, but it could also be other types of modular tasks like object detection or path planning or semantic segmentation or whatever the task may be. Now, one common approach is to actually take all of these sensory modalities and try to, map them into one of the other shared spaces. So for example, if you're dealing with cameras and lidars, you may take the approach where you try to take a camera-centric fusion and you try to map your lidar points into the frame of the camera. The resulting LiDAR depth map, if you will look something like this. And it's a very sparse representation of the scene, right? Where different colors represent the different depths into the future. And once you have this LiDAR depth map in the two-dimensional perspective plane, you can basically use this data. And you can use this, this new image that you have shown here on the right and concatenate it with your original RGB image, and you can basically feed this into any two-dimensional computer vision pipeline that you already have in place and process it. Now, the problem here is that this conversion is inherently geometrically lossy, right? Here you can see 3 examples of circles, but this is just pointing out this problem that points in this shared space that may be very close to each other in the image could be actually very far away from each other in the real world. So this loses geometric meaning about the space, and this results in ultimately a loss of information that makes it much harder for the model to effectively learn and overcome these geometric redundancy or geometric inconsistencies. So instead of projecting the LiDAR to camera, you can also take the opposite approach. You take the camera and you try to project it onto the LiDAR data. This basically looks like trying to paint your 3-dimensional point cloud with colors that come from your camera. The problem here is that, ultimately, the number of points that effectively get mapped onto a color value, especially for modern LiDARs, is extremely small, maybe only 5% of the points. So you lose a tremendous amount of semantic information when going from the camera colors onto a LiDAR point cloud. And this loses massive amounts of the semantic density that's really critical for doing some tasks that require semantics in our environment. For example, end-to-end driving or scene understanding. All of these tasks require a tremendous amount of not only geometric information that we get from LiDARs, but also semantic and color information that we get from cameras. So instead, what we do is we can actually adopt this bird's eye view way of thinking as the unified representation here. So this view is friendly to almost all types of autonomy and perception tasks, because oftentimes the output is also in a geometric or bird's eye view representation or bird's eye view space. More importantly, this transformation from the original sensing modality to the bird's eye view can be done in a oftentimes lossless way, and it keeps both the geometric structure from the LiDAR as well as the semantic understanding from the cameras. And this model looks roughly like this. So given these different types of sensory modalities, and in this project, we actually deal with 3 different types of sensors. We go from cameras, as well as LiDARs, and now radars as well, which are much cheaper than today's LiDAR systems, but still provide a tremendous amount of value if you can harness it in the proper way using approaches like this. So the first step is to basically feed all of these sensors through their own independent encoding pipelines. At the end of this encoder step, all of your sensors are going to be represented as features in the model, but they're still going to be represented in their original space, right? So all of the camera features will still be in the perspective view, all of the LiDAR features will still be in the 3D space, and the same will be true for the radar features. They will also be in the 3D space. So the task is really how can you combine all of these features that are in different spaces together with each other. The transformation process for cameras is actually the most complex, so we'll talk about that one a bit more in depth in the next slide. But for LiDARs and radar features, the transformation can actually be very simple. Basically, we can simply flatten along the height axis, the z-axis, and once all of those features have been transformed to the bird's eye view, we can now stack them together, right? So combining features in a shared representation is the key here, and then applying bird's eye view encoders so that we can fuse them all together. And then ultimately in the final step, we want to apply these task-specific heads to the fused bird's eye view maps, right? These task-specific heads on the right-hand side can be anything. They can be end-to-end control for driving. They can be semantic segmentation. They can be object detection. Right? This approach is focused on learning more robust features that can scale to as many sensors as we desire, and having that be a very robust scaling process. Now, projecting an image into this 3-dimensional space can actually be very challenging because every point in your image is intrinsically going to be represented as an infinity number of possible points in the 3-dimensional space. So we need to disambiguate where exactly this point lives in the 3-dimensional space. So here, to address this issue, you can basically try to explicitly model, what is the depth of every point in your image. So you can start with basically doing a discrete depth distribution of every pixel, which essentially represents every single pixel as a probability distribution in the depth space. of where it might be. So in this example image, you can see that there are 3 pixels on this image, A, B, and C, and their associated features, which you can see on the right-hand side, right? Every 2D pixel has an associated 3-dimensional ray that is basically projected out into the 3-dimensional space. We can predict the likely depth along this ray to achieve a probability distribution. And then now we can scatter that original learned feature that we get from the image space into this 3-dimensional distributional space, where every original feature therefore gets basically split into this ray that gets cast out into the 3-dimensional space according to where we think the distribution or the depth of this pixel is going to be. Now here we're not constrained with inaccuracies in our depth because we get some approximation of depth all along the ray, and the feature actually gets spread everywhere along the ray. This results in actually a super dense bird's eye view representation, where now you have roughly for these types of images, after downscaling the image to a workable amount, you have about 2 million points in this point cloud from your image because it's very dense all along the ray. This is orders of magnitude larger than what we might see from a LiDAR point cloud, so it presents a lot of information. So now that we're in the bird's eye view space, we can seamlessly fuse all of these sensors in the space and apply these task-specific heads. And here's a demo of running this bird's eye view fusion algorithm on the new scenes data set for 3D object detection as well as semantic map segmentation. And this method has actually ranked #1 on leaderboards for these tasks on 3 different data sets, Argo, Waymo, and new scenes. And the code is open source for use. Now, the importance of fusing these sensors is really critical towards the goal of scaling autonomous vehicles for real-world application and making them compatible with the large numbers of sensors and the large amount of redundancy that we ultimately want in our sensor suites. And every sensor here provides a unique lens into the world of our environment, right? Now, for example, poor lighting conditions are oftentimes very challenging for camera sensors. Cameras struggle a lot. Camera-only models struggle a lot to deal with, low light conditions, for example, what you might see at nighttime. So here, our bird's eye view fusion can actually significantly improve just automatically by achieving this added layer of redundancy with an additional sensing modality, which is even larger than the improvement that we would naturally see in the daytime, demonstrating the significance of including these geometric cues when the camera sensors fail. Now, on the other hand, you can also think about this from the LiDAR's point of view. LiDARs are a little bit less robust in rainy conditions or foggy conditions. So LiDAR-only models are going to struggle in these settings as well. But thanks to the robustness of camera sensors, these approaches will actually, under different weather scenarios, improve and close the gap between different types of sunny and rainy situations. But I really believe it doesn't end, here with building a robust sensory or multi-sensory model of our learning engine. In order to truly scale autonomy into, the real world and scale it to, millions of miles operating every single day, our models need to be intimately aware of the long tail edge of possible failures. Now, what do I mean by this? As an autonomous agent that's being deployed into society, we must be able to, those systems must be able to robustly identify these unexpected edge cases, these unexpected events that may be encountered. And these could be failures, right, in the sensory data that we encounter basically every day. These are things like sun glares when they come into our camera, or even rainy conditions when, a LiDAR sensor is presented to it. Or it could be less common situations like out of distributional events that may have never been seen prior to deployment. Now, these can be particularly safety critical in nature and very high stakes in nature. So the goal here is how can we safeguard our autonomous systems so that in these scenarios as well, these most high risk scenarios, they can be able to be equipped with this understanding to not only recognize that they're in these scenarios, but also overcome them when they're presented. So to scale autonomous systems to perform in this long tail of types of situations, We want to build these systems that are not only robust and can understand, when they are uncertain and when they're in these situations, but also very importantly is, what are these situations that are being presented and how much uncertainty or how far out of distribution, how far away from what they are comfortable with are they presenting, right? Now, this is a very nuanced understanding to this very complex problem, and we can actually distill this notion of, uncertainty into 3 subtypes. Now, many of you may actually know the 2 most common types of uncertainty, but probably this third one is going to be much less known by the audience. So there are 3 main types of uncertainty. There's epistemic uncertainty, which measures what the model doesn't know due to limited data. There's aleatoric uncertainty, which measures basically the noise inherent within the labels or the data itself. And then there's finally vacuity, which reflects a lack of evidence or a lack of training data for this particular type of situation that hasn't necessarily been seen before. Now, to make this a bit more concrete, let's consider a few example images where we're performing semantic segmentation. Here you can visualize both the ground truth, the prediction, as well as the 3 different types of uncertainty. Note here there's very subtle differences between these different types of uncertainty and how each one provides very unique information to diagnose the particular problems that these systems are facing. Now, specifically, that vacuity captures a lack of evidence or a lack of information from training data, and this poses actually an upper bound. You can think of this really as a strict upper bound to the amounts of epistemic uncertainty, right? Now, epistemic uncertainty, just to remind you, is the lack of model understanding. That lack of model understanding can come from 2 sources. It can come from a lack of training data, which vacuity measures, but it could also come from, just a lack of capacity in the model. The model maybe is not large enough or is not representing this type of information. So epistemic captures both of these things. Oftentimes, vacuity, even though epistemic is far more popular in practice, and maybe many of you have heard of it already, vacuity is actually far more practical of a type of uncertainty measure for actually scaling these types of autonomous systems, and is far more useful in practice. So today there are many different types of distinct algorithms that can estimate these different methods, many of which have complex mathematics that I'm not going to talk about today, from the theory of evidence to conformal predictions to model ensembling. But really the summary and the reality of the situation is this, that all of these different methods require very different implementations that are oftentimes ad hoc, they're oftentimes labor intensive to engineer, they're oftentimes knowledge intensive to understand, to be able to engineer, and require actually processing and building and deploying these, uncertainty aware or risk aware AI pipelines. Now, even worse, actually, before I get to this, even worse is that the modern autonomy stack is highly complex and contains many different types of models, not just one model like we say in end-to-end, but actually many types of models. And really what you want to do is actually understand all of these uncertainties, not for the entire system, yes for the entire system, but also for every single one of your modules, so you can propagate uncertainty through the entire system as a whole. And this basically blows up the amount of complexity of this problem even more, because you have to re-engineer every single part of this system to be uncertainty aware. So instead, what we really want is a model agnostic approach that is capable of basically what I like to think of as wrapping any existing AI model with the abilities to estimate uncertainty without the need of understanding how any of these complex methods or mathematics work. So if you could simply wrap your model, and this could be any model in your AI stack, you can then try to augment it such that it's not only able to predict its original answer, but now for every prediction, it will also generate a scalable and calibrated measure of all of these different types of uncertainty. And we've developed a solution, which here you can see is called CAPSA, which provides a wrapping framework that is both data and model agnostic, enabling the achievement of uncertainty-aware variants of any neural network model that you're building automatically without understanding a lot of the low-level details in mathematics of those uncertainty methods or re-engineering your models. So CAPSA automates and accelerates the development and deployment of risk-aware AI solutions by providing this, this software library that interfaces directly with TensorFlow, Keras, and PyTorch. Here's a very brief code example defining a model in TensorFlow. CAPSA enables basically directly and automatically wrapping that model to create a risk-aware variant. You can basically choose the type of risk metric that you want to estimate. For example, here, using a Bayesian wrapper, which is one example of a type of way that you can estimate this type of uncertainty. But you can also choose from a very large library of different types of wrappers. Without re-engineering and re-implementing all of your model from scratch, you can just wrap the model, and it gives you all of that capability at your disposal. There's also this very exciting notion of auto-wrapping, which I'm particularly excited about, where we have these high-level objectives that you may care about when you're wrapping a model. A lot of these methods are very computationally expensive and require a lot of memory or compute costs to run. Now you can actually provide priorities. Maybe you want to have an uncertainty estimation method that estimates only epistemic uncertainty but prioritizes the speed and the compute cost of that method. CAPSA will basically take all of your parameters and your priorities into account and design a tailor-fit uncertainty estimation pipeline that will automatically wrap your specific model and give you back your model without understanding a lot of these nuances of the highly varied and mathematically dense algorithms for performing uncertainty estimation. So this layer of abstraction, we hope, confers an enormous amount of power, greater power for deploying these autonomous systems. And because CAPSA really automates this conversion to be risk-aware or uncertainty-aware, what you can now readily deploy your applications and your developmental stack into reality while being aware of all of these risks and deficiencies of your model. So importantly, this extensive library contains estimation of uncertainty across all of these different forms, like we talked about before, many of which are less explored in literature, as well as different types of methods as well. However, all of these methods have their own relative advantages and disadvantages, which must be weighed and carefully understood, right? Now, we also have created this new method in-house, which we call Mercury, which addresses the limitations of existing approaches, which are largely that they're extremely unscalable for real-time applications like we often care about the most in autonomous driving, and is actually able to achieve both very high performance, which you can see on the left-hand side, as well as scale very, very well with computation. Comparing here to ensembles and dropout, you can see the incredible memory and computational footprint of these types of models over the state of the art, where they are almost incurring almost zero extra memory and computational overhead. So CAPSA provides this very flexible framework to enable autonomy to scale through robustness and risk awareness. And this can take many forms, from the ability to automatically identify data missingness and then curate data to label and fix noise in your data sets, to even identifying anomalies and guiding your learning process through those anomalies to build more robust and scalable deployment pipelines. So you can really think of CAPSA as this powerful toolkit that will enable autonomous capabilities and scalabilities by automatically transforming any autonomous modular system or module within an autonomous system to be a risk-aware variant that can detect and report back its own uncertainties and failure modes. So CAPSA can really empower, in my opinion, all of your AI models in the autonomy stack to be unlocking this capability of scalability by estimating the long tail of failures. So in summary, we're advancing the scalability of autonomy by building robust AI solutions for all stages of the learning lifecycle, from data all the way to deployment. We provide code for a lot of our solutions. You can see links here on the bottom right. As well as for CAPSA, we're doing an early release very soon, so please be in touch and reach out if you're interested in being a very early user of CAPSA. And yeah, that's it. I'm happy to take any questions, and thank you so much for your attention.
Thank you very much. I think we have time for one question. Anyone?
Actually, I have two questions. The first one is about the LiDAR model in vista simulation. So I'm wondering, is the LiDAR model ideal model or can also simulate some noise distribution? The second is about the trajectory dataset interaction. How the traffic rules are considered in the modeling of the interaction? Thanks.
Yeah, two great questions. So first on the LiDAR data, so it's not an ideal modeling at all. In fact, we learn noise directly from the data, right? So taking these large LiDAR scans, we actually learn, like all of the noise parameters and kind of like drop rates of different LiDAR beams in different types of reflective situations, different types of environmental situations. So it kind of scales, and changes depending on what environment you're in, what types of, reflective properties the beams are bouncing off of. All of these things are kind of modeled by a neural network learning-based approach. And you can kind of capture all of these in the simulation as well. The second question was about behaviors, right? Yep. So yes, traffic is also not hard-coded into the system here, right? So here we're just trying to learn kind of a behavioral model of the different types of agents. And that's kind of, again, purely data-driven from the ground up. It's trying to take just a large-scale data set modeling approach, not trying to, constrain the trajectories based on traffic rules, even though we may constrain the simulator and the final policies on traffic rules. So the goal for that step is really just to understand large-scale behavioral patterns in data sets. Thank you.
So I think while Rowan is setting up, maybe we have time for one more question.
Sure.
If there is any, yeah.
Hello. Yeah. Thanks for your presentation. I have a question regarding whenever we talk about uncertainties, we always talk about uncertainty in our perception for segmentation, regression, or anything. And this BV fusion model generally tries to fuse things in a feature space, right?
Yep.
What do you think about actually uncertainties in feature space of a model? How can we go towards there? Because until unless we are talking about late fusion or something like that, we need some kind of sense or notion of uncertainty, right? So is there anything you can shed some light on? That would be nice. Yeah.
Yeah, excellent question. So this is actually something that we think a lot about. I think is extremely important for doing the fusion task is, weighing the different sensory modalities. Not all sensory modalities need to be uniformly weighed in the fused representation. So you can actually use uncertainty as a way to actually encode which sensor needs to be paid more attention to in the fused representation. And this can be done by basically wrapping all of your encoders prior to fusion, right, with some uncertainty estimation capabilities. If you have uncertainty in the feature space, right, typically like you said, we think about uncertainty over the output space, but now we have uncertainties over the feature space, and this can be easily done, with things like CAPSA. Instead of wrapping the whole model, you just wrap the encoders, right? So it's very modular. Now you have uncertainties over the features. You can use those uncertainties to basically say, okay, if this sensor is more uncertain than this sensor, maybe I should, weigh its contribution a bit more so I learn more from this type of information in the final representation. Or you can take other types of approaches as well. But this is definitely a very important question.
But with this CAPSA, we use already existing algorithms, right? But they are kind of, I believe, if it's not sampling based, they are focusing on the output uncertainties. I still wonder, if it's a sampling free methods, how they get the sense in the feature, do they backtrack towards the feature, or encoder somehow learns, okay, this, I tried to visualize some outputs from camera, from BV fusion, and they don't correlate well with the LiDAR, for example.
Right.
So I just don't know what is the notion of uncertainty there. So,
Yeah, no, you can actually do these types of uncertainty estimation methods not over the output space. So actually a lot of the known methods you can also do over the feature space as well. They are not sample efficient, they're taking a long time. So in Capsule we also do a lot of sample free approaches as well. So you can kind of drop those in, you can play around with different types of uncertainty methods. But the key is, the main point is, you can take it such that you don't wrap to the output space, you stop the wrapping at the feature space, and then you use the uncertainties over features however you would like.
Mm-hmm. Okay, thank you so much.
Thank you. All right. Sounds good. Thank you.
Let's please thank Alex again. So our next speaker is Rowan McAllister. Rowan is a research scientist at Waymo in California, where he focuses on autonomous vehicle planning. Rowan has a rich academic background, including a PhD in machine learning from the University of Cambridge under Carl Rasmussen and a postdoc with Sergey Levine. Rowan has worked at Uber ATG. He's a co-founder of Light Blue Labs, and he also led a research team at the Toyota Research Institute. He has organized multiple workshops on autonomous driving, and his key interests are autonomous vehicles, reinforcement learning, Bayesian statistics, and cycling. And he continually uses his passion and expertise to advance the field of autonomous vehicles. Let's please join me in welcoming Rowan.
Cool. Thanks very much. We're just switching laptops.
Yeah.
So you should have it there. Oh yeah, you got it. All right. Yeah, thank you, everyone. So my name is Rowan McAllister. So I'm a research scientist at Waymo in Waymo Research. And we're all about how do we incorporate machine learning models into our autonomous vehicles to make them safer and smoother. So yeah, thank you very much to the workshop organizers. I know it's a lot of work putting these things together, and it's great to see so many people here. Unfortunately, because we had the laptop switch, there's a lot of videos that will be blocked. But I'll just tell you that they're really cool, and I'll try to make up with it with my explanations of what we're doing. All right. So Waymo is Alphabet's autonomous vehicle company. And there's two categories that we're really interested in here. First is moving people through a service that we call Waymo One. This is a ride-hailing service like you might expect with many of the ways in which you get around today. And then also another service for moving commercial goods, and this is called Waymo VS. This is often trucks and other, or lorries in the UK, things like that. And so this is what it looks like. You can download it on your phone. So if you're in San Francisco or Phoenix, you can download this today. Much like you would expect, you basically put in your destination and then it will call up the vehicle and come pick you up. And so this is an image, I think, from Phoenix, where we've been operating autonomously since October 2020. And so this is this is what it looks like. The newest versions of the Jaguar I-Pace vehicles. It's an electric vehicle, and and since I think March 2022, we're also now operating in San Francisco. Okay, so here's all the cool videos that we can't see. And basically these videos are kind of us or the vehicle driving around San Francisco and seeing a lot of edge cases. I've got some images later on that will load that we can see. Or here's a GIF. So here's an example of the vehicle running around in San Francisco. We've got a cyclist coming out. They were on the wrong side of the road, so you know, drive on the right-hand side of the road in the US, and the cyclist was in the left-hand side of the road. It may seem like an edge case, but this happens every day. And so these are the types of things that we need to watch out for, like occlusions, you know, for all sorts of behaviors that we need to be able to anticipate and stop for. Okay, so yeah, the recent updates is, San Francisco is now offering fully autonomous rides for the public, and this is 24/7, day or night. Phoenix, we've expanded our territory to 180 square miles, and this includes Sky Harbor Airport. If you fly into Phoenix, you can call up a Waymo One vehicle. And then also, recently we've started autonomous testing in LA. Okay, so I'll jump into some of the modeling part of the kind of technical talk for today. And I was going to talk about 3 papers to do with behavior prediction and also planning. So this is the area that I'm most interested in and concerned with at Waymo. So, okay, so modeling others' behaviors. It often looks something like this, where we have some kind of world state. A lot of us here are familiar with. Maybe we've got many agents and, you know, the history that we've logged so far, what the traffic light state is, and other aspects of the road network, like, you know, where there is a stop sign, where there is a crosswalk, and so forth. Can often embed that into, or encode that into some kind of neural network to make some kind of a prediction. So here, for example, I'm showing what the multipath paper does. So this was a Waymo paper back in 2019, which predicts for n agents, k trajectories per agent, and then also the time steps, predicting x, y heading trajectories. And so this might look something like this if we predict up to 8 seconds in the future, where green is current time and blue is 8 seconds into the future, and the more opaque the trajectory there is in the GIF, the more likely it is, and the more transparent, the less likely. Okay, so this was popular, and work continued with multipath. And so the story of multipath from up until the multipath plus paper more recently is one of hard work and artisanal crafting of different modules using a lot of domain expertise. And so this was something that we were very proud of at Waymo. Basically, it was a state-of-the-art system that kind of hit the top of the leaderboard, at least at the time, for WAMD and Argoverse. And so we were very proud of this, but as you can maybe start to see here, it does look a little bit complex. And so this can be a bit of a problem when it comes to things like tuning the model, or trying to figure out, you know, is there any knobs in which we can easily trade off things like capacity with latency and accuracy of the model for our needs as things evolve. So this made us ask the question of, like, you know, to take a step back a little bit from maybe more complicated designs and layering on the complexity even more, to think about, you know, what do we really want in our behavior model design space, and kind of go back to first principles. So the things that we were aiming for here was simplicity, which basically means accessibility. So, you know, can we leverage a wider pool of machine learning experts, for example, in a way that we're not really requiring heavy domain expertise in this particular problem. And then the second is whether it's tunable, so kind of related to what I said before, can we tune the model to our needs in terms of accuracy, latency, things like this. And then third, the topic of this workshop is the model scalable? So can we give the model more data? Can we give it more capacity if we're able to, if we have the compute off-board and on-board? And can it do better and better with more data? Okay, so what that might look like is something that's a little bit more homogeneous. And one of the things that we were thinking about here is that, it should be ideally agnostic to the input modality type. This is something that we may not want to do in the low data regime, but in the large data regime, we can start moving towards. And ideally, the model should have a compact description. It shouldn't be too complex, meaning lines of code shouldn't be too much for any one person to basically look through, read, and understand, ideally. Okay, so the key idea questions here, the key design questions here is, well, if this is what we want, then what are the basic building blocks? And how can we fuse these different types of input modalities, like the road graph, other agents, our own trajectories, so forth? And how to model the interactions between all of these modalities. Okay, so surprise, surprise, transformers here are the kind of model of choice. They're incredibly useful, as a lot of people here know, in all sorts of things like vision, speech, NLP, robotics. And so this is basically the direction that this paper called Waveformer started moving towards. So how can we take all of these things and maybe project them somehow, put them into an encoder, and then decode using this building block here. And there's different ways of doing this, and the literature is actually quite rich on how to combine different modes for transformers. We kind of broke down the problem into kind of three categories that I'll describe just here. One is called early fusion. So this is basically concatenate everything into one big long vector. The way in which we describe all of these histories and road graph, traffic lights and everything like that, and then do an attention encoder and try to output predictions, maybe like the n times k trajectories that we saw before. Another one is late fusion. So maybe this is a little bit more common in the literature, where we come up with some bespoke encoders for these different things, and then do a concatenation layer in our encoder. In the transformer. And the third option here was to do both things here. So we've got an intention encoder for the different input modalities before we concatenate all of them together and do an intention encoder across the modes. Okay. There's also some other design questions in how we want to come up with this model. So one is, how do we want to fuse the different modalities through time and through space? So we can fuse across the different scene elements, the different vehicles, the different pedestrians and traffic lights and so forth. We can also do that through time. And then there's the question of what order do you do that in, or do you just do everything at once and just have one big kind of matrix here of attention. Okay, so these are the kind of different models that we tried here: interleaved, sequential, or just this multi-axis attention. So this has resulted in Waveformer, and I think I saw Rami in the audience, maybe. So Rami and Nigma were the kind of main authors on this paper, and so this is really kind of looking at, how should we bring transformers into behavior prediction when we've got these different choices. And so it was looking at these different choices on like early, mid, late fusion, or temporal spatial multifactorization, and sequential interleaved or multi-attention. And so the paper is chock-a-block with, the different types of trade-offs that you might want to make. But basically the hierarchical, or I'll show one here, the hierarchical version of fusion, where we had 2 layers, was something that we kind of consider the default, which is it finds a nice compromise between distance error when we make predictions about the vehicles in the scene, and also the latency, how long it takes to make this prediction. So it might not seem like a lot of time, but in real time, with real-time constraints in a complex system, there's a lot of different components vying for time, and so that is obviously important as well. Okay, so this is what it looks like on the Waymo Open Dataset and Argoverse. So we've got the 2 different versions here with the multi-axis and the factorized way of doing attention. And so whilst it gets mostly good scores here, the main win, I think, for this paper, or the main message, is that you can remove the domain expertise if you have enough data, and if you choose the right combination of how you apply attention to the behavior prediction problem. And because of the model's simplicity, it makes it much easier to kind of trade off speed and quality, by kind of augmenting, the layers at different points. There's not too many points in which we can go in and change things, so that makes tuning much simpler. And it also scales with increasing data and compute. So we haven't really restricted through our domain expertise how things encoded in a way that can't escape our assumptions by applying that domain expertise. Because we haven't done that, this model should be able to kind of capture more subtle events the more data we have. Great. So this is an example of what the waveformer might look like. So green is kind of early predictions, blue later predictions, 8 seconds into the future. If things are more opaque, it's more likely. So here we've got if you can see, we've got like we've got a slightly unusual intersection here where it's not quite a 90-degree turns, and we've got these kind of nice bimodal predictions where these cars, they may be doing a U-turn, or they may be kind of turning left over here. And here's another kind of interesting one where there's this pedestrian over here that starts to turn, and then we quickly, the waveform algorithm quickly kind of works out that they're probably going to jaywalk between these vehicles here. So this is probably dangerous in any country, but yeah, jaywalking is even a bigger no-no in the US. But we still need to be able to predict for it. And here we have another car that's kind of waiting, that we predict will correctly wait for the oncoming traffic to pass before it is then able to turn. Okay, great. So that was the waveformer, and I know we're 2 minutes over my scheduled time, so if the organizers want to give me a wave, if there's 3 minutes left, I can wrap up. Carry on? Okay, great. So let me talk about a second case here. So we saw some slight edge cases like that. That pedestrian jaywalking across multiple lanes of traffic. It doesn't happen all the time, but it does happen. And so with collecting kind of larger data sets, we do get to see some more of these like really interesting edge cases. And so I'll give you a flavor of some of the edge cases that we've seen at Waymo. And then talk to you about like what is it that we can do about it from the sake of planning. So I'll just make it clear, no one was hurt in any of these videos. This first one is really interesting. You may have seen it before. I'll go through some other ones that you may not have seen. First, a slide, which is to talk about the long tail, as we heard about in the previous talk. So most of driving could probably be described as boring, typical, just going down the highway, nothing's really happening. And then, we have this problem in the autonomous driving industry of there's these tail events that are often really hard to predict for and anticipate. But, a lot of humans use kind of common sense to be able to kind of deal with them online when they're in the situation. And that's something that we also need to be able to do, obviously, as well. So, and this is particularly a problem for any kind of company like Waymo that's operating in the L4 space. You need to be able to handle every single kind of instance, everything that you're confronted with. So here we've got a really, I think, just a crazy example of, in case you missed it, it's a motorcycle coming down the highway, but it's only a motorcycle. There is no person on the motorcycle. So something must have happened further up, but this thing comes down, no one was hurt, crashes into a hot dog trailer, and this is very difficult, right? So humans might be able to say, well, okay, if there's no human on it, it's probably not going to make an intelligent decision, but momentum still exists, physics still exists. So I'm probably trying to, might try to get out of its way and so forth. So this is a really difficult thing for our algorithms to be able to deal with. Some other fun examples are we've got a barbecue kind of falling off a truck here. So now this is like a sizable metal object. It's not just a plastic bag that we may want to be up, that we could drive over. It's something that does warrant a braking, even though there's other cars, there may be other cars behind us traveling at high speeds. There's also this case where it appears that there's a road sign walking across the road, but it's really a construction worker that's holding it from the other side. So this is very confusing. We've got cases where people just pull out and we have to throw on the brakes. So even though they were off the road, we still need, a vehicle off the road, we still need to be able to anticipate their movements. And here we have a house on the road. So this is maybe a bit more common in North America, where you have these prefabbed houses and then transport them across the country, and often very wide, and you need to kind of get around them. It's a bit of an unusual thing to see, but you do see it. And then even things like vehicles on fire. So there's a lot of things that we need to be able to reason about, and so this paper here by Ye and Liu was really trying to tackle this problem by saying, okay, imitation is very useful. Humans already know how to drive if we can copy their data. Many companies do this, and it's a natural thing to do. But it doesn't always help us in these real tail events. That you may only see, maybe once in a lifetime or 10 times in a lifetime, from a human's point of view. So here, what this paper was proposing here was is there a way to, intelligently combine imitation learning with reinforcement learning, and what are the benefits of both, and can we get the best of both worlds? So imitation learning, it bakes in behavior realism. There's all sorts of things that humans will do that we don't explicitly know, but they are, providing to us, in terms of what constitutes good driving, including smooth driving, and what does smooth even mean? It's hard to pin down, but it exists in the data. So that's the real benefit here, is that there's no reward design. It's very hard to, as everyone here probably knows, it's very hard to write down the general reward function of what good driving means. But there is still, but reinforcement learning can be helpful in some of these tail cases where we know that even if we've never been in this situation, collisions are still bad. And that is easy to specify what that means when we're in our planning space. And also, maybe going off the road is also a bad thing, regardless of the situation that we're in. It's not an infinite cost, but it's maybe a high cost when we're trying to consider what constitutes good planning. So this kind of prior knowledge can be really useful for these tail events that maybe the imitation learning won't be able to help us with because it just has no data on. Okay, so the method here is quite simple, but I think also quite elegant. Basically, it's just a combination, a weighted combination of saying the thing that we want to optimize is the expectation of rewards, however rewards are defined, which I'll talk about in a second, and then also this kind of behavior cloning loss here. So when we're in distribution, what happens is the planning algorithm will take into account both. So this expectation here is over the data set. So I've encoded in blue here, this is where we've seen most driving between the two dotted lines. And so anytime the ego vehicle is inside that region, it will have been trained on a loss from data in that region to basically optimize how the human is driving, were they driving smoothly, and so forth. And by contrast, when we're outside of the distribution that we have no data for, we can at least fall back to this reward as opposed to falling back to nothing. So, what should this reward be? Well, actually, that is on the next slide. But this slide is basically saying the algorithm that we chose here was the soft actor critic algorithm. So, yeah, I guess some might consider it like one of the default algorithms to use for reinforcement learning, especially for continuous state and actions. Yeah, here we have SAC, where the critic is untouched. So we've got we're trying to minimize the Q error here using the Bellman backup together with this regularization term from the soft actor critic algorithm. And then the only change that we've provided here is the actor objective. So there's the regular actor objective together with the entropy term from SAC together with our behavior cloning loss over here. And so the reward is for our experiments was to just look at the collision and the off-road rate. So this doesn't constitute everything. It has no concept of what a smooth ride is, but it is taking care of the most important things when it's out of distribution. So don't crash, don't go off the road. 2 minutes? Okay, I'll wrap up in 1 or 2 minutes. So this is what those two rewards look like. Very simple, but they can be effective. So here we've got a collision cost, which is basically this function here. So it ramps up as we start getting within about a meter of another vehicle. And then we've also got this off-road cost. And again, kind of ramping up as we get within about a meter of the edge of the road. Okay, so this is a bit of a smooth signal. That's why we kind of ramp up so that we can basically have a nice trade-off between these things, as especially with like narrow streets and things like that. Okay, and so the results overview looks something like this, where we're down below. What we've done is we've actually, I won't go into the details, but we had a look at what was the most difficult snippets that we've seen. So like from a particular scene, how difficult is this scene to be able to plan safely forwards. So over here we've got the 50, the kind of more easier examples here, and then over here is the 99th and 100th percentile. So this is the kind of the most difficult cases. So we've compared against MGAL, model-based scale, and just straight behavior cloning, and so we can see in the kind of general case, there's not that much improvement. In fact, MGAL is doing a little bit better. But the story here is like in these tail events, the really difficult ones. So this is where the failure rate, or meaning collision or off-road, under our simulation, we didn't really crash cars here, but under simulation, this is where the algorithm comes in terms of providing benefits. And I'll wrap up. I'll try to wrap up in 30 seconds. So we've got some results here, basically showing if we train on all of the data in this top 1%, kind of similar to the bar graph before. The the failure rate can be a lot less, since it's a little bit more tuned into those particular fail cases. So I'll show you one example just here. So we've got, on the left is MGale, and we've got a kind of car parked and a pedestrian here getting out of their vehicle. And so just by kind of mimicking data sets that we've seen before, it maybe gets a little bit too close to the pedestrian as they were getting out of their vehicle. Whereas over here, it's the same thing, it's behavior cloning together with this RL cost. So we kind of give that pedestrian a wide berth, even if we haven't seen this data point before. And I think I'll end it there. Thank you.
I'll start with a quick question. I think one interesting thing about these models that learn from behavioral information is how well do they scale geographically. For example, now that you deployed in multiple cities, do you have any insight? Is it very important to have local data to fine tune on, or is it better, or they just gracefully generalize from one place to another?
Well, Drago, do you want to answer this one? I don't want to say anything I shouldn't say.
I mean, generally we find that these models have good generalization capability and capacity. So with the amounts of data we have, we find that a single model does very well across many different settings and potentially even vehicle types and so on.
Maybe we have time for one more question.
I have a question about the waveformer. I see that you operate on some abstracted representations, which potentially do not include some subliminal cues, like whether someone's driving a BWM or BMW, sorry,
yeah,
or the gaze or indicator lights or whatever. You can all put them in, but it's a lot of work. So do you plan to go forward to include sensory information directly, or do you think this will be enough?
Oh, so if I understand the question correctly, do we add in features like, you know, what was the vehicle type and so forth? There is for this work, I don't think there is any plans to. There is separate research that is interested in the kind of the video input question. But yeah, I would say, yeah, unless Rami knows different. Oh, okay, Drago's gonna give a better answer.
This is research, right, published on a research data set, which has certain simple set of representations. One thing that we did this year, if you followed, we released LiDAR point clouds for this behavior data set for 100,000 sequences. So you can explore what happens with at least the cues present in LiDAR.
So compared to imitation learning, you said that reinforcement learning has the advantage of closed loop feedback. So the realistic simulator is required.
Yes, that's correct. And
also consider offline reinforcement learning.
Yes, yeah. So that's another area of research. So yeah, with kind of similar but slightly different benefits from kind of imitation, at least if the imitation algorithm can tell you when it's in or out of distribution. It is nice to be pessimistic, or at least in some way fall off to another algorithm like the RL algorithm or some other kind of safety system. So offline RL is definitely of interest in Waymo research. I think, and to your point about realistic simulators, yes, this is actually a huge this is a huge topic inside Waymo research, and a lot of people. There's a lot of people working on exactly that, on how do you come up with simulators that are statistically indistinguishable with what we see in reality.
Yeah, let's please thank Rowan again. Our next speaker is Kashyap Chitta, who is a PhD student at the University of Tübingen in Germany in the Autonomous Vision Group under Professor Andreas Geiger. Kashyap's research revolves around data-driven solution for decision-making tasks, particularly focusing on self-driving vehicles. And his work explores how autonomous agents can employ attention-based deep neural nets for safe navigation. And Kashyap is also interested in constructing data-driven simulators for robust policy learning. Let's please welcome Kashyap. This a little bit out of the way, and then you can have your mic. I'll tell you when 5 minutes up.
Okay. Oh, I have a technical issue. 1 second. Yeah, I think I may need to reboot. Maybe I can try like that. Okay. Yeah. So I have a weird setup here, but let's see how it goes. So yeah, I'm going to talk about end-to-end driving with attention. And I want to start with sort of like breaking news fresh from archive. It's from 2 weeks ago. A team of researchers from Baidu proposed autonomous driving system with an MLP, like a 2-layer MLP, which was trained on new scenes, just taking in the last like few seconds of the ego history, this ego state thing as an input, and a high-level command, predicting a future trajectory for a certain time horizon. And like the really crazy thing is that this model is the state-of-the-art open-loop planning model on new scenes. So the 5 papers on the left are all published at CVPR, ECCV, ICCV over the last 2-3 years. And those all incorporate some end-to-end input. So they have either cameras or LiDARs as some input information. But this model at the bottom, which was from this work here, actually got a much lower displacement error and lower collision rates on new scenes. And the method doesn't take any perceptual input, just has this ego states as its input. So what does this mean? So I think like this kind of emphasizes a point which is probably well known to a lot of people here, but it's that open loop evaluation is flawed for planning and for self-driving stacks when you look at the complete stack. So there's many reasons for this. The main one being that planning is multimodal. So if you have a data set where the white car is you, maybe you observed in the data set this red trajectory where you merge into the lane a bit later, but it turns out your planner predicts this white trajectory, which is perfectly reasonable, but very far away from the endpoint of this red recorded trajectory. And so what that means is if you measure the performance of your planning systems based on only the predictions of your model in states that were observed in your data set, your evaluation is going to be flawed and you will end up with weird results like what we saw on the previous slide. So this kind of motivates what we do. Our experimental setup for testing end-to-end driving systems, planning systems, is through closed loop evaluation. And specifically, like, we work with an open source simulator because it lets you benchmark and compare things across the community. This is called Carla. And the task in Carla is to kind of drive from a start point, which is this little green thing, over a long route, which may be like 2-3 kilometers long, where you intermittently get these checkpoints along the way for how to travel along this route. And these little exclamation marks are kind of manually designed dangerous scenarios that are mined and designed by the simulator team. It's not ideal, it doesn't capture all the dangerous situations you will see in this long tail that we've observed in the last few talks. But at least it gives a way to evaluate models for the actual driving performance and not a distance on an observed data set. So specifically, like how you evaluate in Carla is that you run your trained driving system over a number of routes, that's the N here, and you multiply two things, the completion, which is how far you got to the end of the route. So getting to the end is a 100 score there, so it's a percentage. And there's a penalty for infractions. This is a multiplier that's applied every time you make an infraction like colliding, running a traffic light, and so on. Each time you make an infraction, your score gets multiplied by a number less than 1. So with that as a background, I want to talk about some of the ideas where we have worked on parts of end-to-end driving systems to improve their performance in this closed loop evaluation setup. I want to start with some work on sensor fusion. So there were some great talks on why it's good to have redundancy and have lots of sensors. So a very quick recap is that images and point clouds are complementary. Images have very dense inputs, and you include information there like traffic light states, which you need to drive, the semantic information basically. But they do not have a very large field of view, and 3D information is not super reliable in there. So that means if you want a pure image-based system, you're going to need a lot of cameras and a lot of compute to process all these cameras. And point clouds, they give you very high field of view 3D information, but again are not enough to solve the driving task by themselves because they're sparse. And in order to process these sort of complementary sensors, the most well-established way of fusing them is through geometric feature projections. I think BEV fusion, which was covered in one of the earlier talks, is a very popular way, or like any common feature space, and projecting these different sensors into a common feature space is a very popular way of fusing information from multiple sensors before processing it with the rest of your network. So I'm going to talk about a small disadvantage of geometry-based fusion. Consider this scenario. There's an intersection. You're about to enter the intersection, and you're seeing this camera image and this LiDAR sweep. So what happens is that if you do geometry-based fusion and you have a method that's like good at associating the camera and LiDAR, the features that you extract from these green traffic lights in the image, which is shown in this yellow box, are going to be mapped to the features that you extract from this blue area in the LiDAR. But what gets missed, and what another part of your network then needs to figure out, is that there are vehicles actually that you can see in the LiDAR here. These are the edges that you see in this red box. These vehicles are going to be affected by this traffic light and start moving into the intersection. And since the traffic light for the ego vehicle is also green, if you don't know about these vehicles moving, you're going to enter the intersection and be in a dangerous situation. So in these sorts of dangerous scenarios, like unprotected turns, it would be useful if your feature fusion can do some kind of global reasoning as well, and not just do geometry-based mappings between your different sensors. So the first idea I'm going to quickly talk about is how you can use attention to do this feature fusion in a way that captures this global context. Yeah, so This method, it's an encoder for multimodal inputs, which we call transfuser, which is a simple idea. You have CNNs for each modality that extract these features, but instead of doing a geometric mapping between them, you use transformers, like everybody's favorite building block these days. Transformers basically tokenize the feature maps at different resolutions in your CNN encoders and concatenate these into a sequence and residually sort of add back the global context encoded features before going to subsequent blocks in the architecture. So with this, we kind of built a end-to-end driving stack. So that was just the encoder, which is now compressed onto the left half of this figure. We train with multiple loss functions. We use perception labels for supervising the features of the image and LiDAR branches to contain like rich task relevant information like how to predict the map, how to detect vehicles, or the depth and semantic segmentation in the case of image branch. But the main loss that sort of we focus on optimizing is through this decoder in the middle, where we're going to use a GRU to predict a set of waypoints, so future positions that were recorded in the data set, conditioned on a goal location that you want to reach in a short horizon. So this is trained end-to-end on a single data set with all the objectives, and then you can use a controller to steer throttle brake basically in your simulator for evaluation. So we set up this architecture and we started looking into it more deeply, and we found that there's actually a very interesting little detail. So I'm going to show some visualizations of the predictions you get from this model. You see the inputs, which are the image on the top and the LiDAR point cloud on the bottom. And I've also overlaid the ground truth map onto the LiDAR, so you can see where the road and lane markings are. The model's predictions are these blue points, the waypoints. And this red dot is the thing which I called the goal location, which was input to this model's decoder, which tells you how to drive. It's meant as an intention signal of whether you have to turn left, right, or go straight at an intersection, for example. So interestingly, we found that if you perturb these models, if you put them like far outside the center of the lane, maybe you face them on the sidewalk or in between the lanes, they always extrapolate their predictions straight towards this goal location input that was given to them. So specifically because we did testing and simulation, it's very easy to have like small localization errors, and these goal locations are very accurately in the middle of the lane. So it turns out that these sort of models just learn a shortcut that if the goal location is close enough, I should just drive straight into it. And this is the best way to stay within the road and get a good driving score. This is not just true of this transfuser model I presented. We went over nearly all the state-of-the-art methods in Carla. So on the left, there's a method called LAV, and the right, there's a method called TCP. And since all of them adopt the same sort of architecture where this goal location is kind of fed into the network really late in the architecture, and all the perception goes through these very big network encoders before being processed by the decoder. Even though they differ in terms of like how many waypoints they predict or some other details like what input modalities they have, all these methods are susceptible to kind of driving straight into the target location. And on the right, you can already see a problem that might happen because of this. If the target location is far enough away, like behind a turn in this case, the model's prediction is to kind of drive into the opposite lane because that is the path towards this target location. So we had a hypothesis that there is a problem with the encoder features which is causing the model to focus on this goal location unnecessarily for making its final prediction. So we made like a minor modification to how one specific aspect of the network architecture worked, replaced it with attention in order to preserve spatial information in the encoder features. I'll go over what that is and how it works quickly. So this is the same architecture as before. I've just flipped the image and BV branch so that it's easier to visualize. What we did is we replaced this MLP that we had coming into the GRU decoder with a transformer decoder. So again, we see here the usefulness of these attention-based representations. What we do is essentially like instead of predicting waypoints from this pooled feature, so before you would have like this 8x8 feature grid coming from your network, do an average pooling, so you have a feature vector, and then feed this into your GRU decoder to predict waypoints. We used a transformer decoder where you learn a query that you have like one query corresponding to each waypoint you predict, and you use these queries as the initial features for your GRU instead of having a single feature coming from the encoder. So why was this idea even like in our head? Why do we think this makes sense? I'm showing here again a similar example for our transfuser model where you have the image on the top, the goal location is behind a turn, and the model is predicting a set of waypoints that drive into the opposite lane and would crash. What this figure shows though is that instead of showing the actual map, I'm showing the prediction of the map that the encoder generates through this auxiliary head of BV segmentation here. You can see that the overall architecture has learned where the lane center is. The segmentation of the road seems correct. So the model knows that the lane it needs to follow is actually straight, but the waypoints still bias like the prediction towards this very sharp cut. And what that means is that the encoder features are powerful enough to include the information about the center of the lane, but the decoder is not able to access this, which is why it's relying on the shortcut of the target point. When you use this transformer decoder, you have the output then becoming what you see on the right, where you now see that the model is staying in the center of the lane. And this is mainly because the decoder can now learn to prioritize information from certain tokens in this bird's eye view feature map that basically preserves the spatial information in the feature and acts as a stronger correlation so that the network doesn't use the shortcut but uses the true causal reasoning for predicting the waypoints in the scene. We also, this is a minor point, but we found that another way to make these models robust to not cutting lanes and just directly following the target point is to use a lot of data augmentation. So this was an idea that was quite popular before the most recent set of Carla papers, where if you have your simulator and you have the sample on the left where you're driving normally straight through the center of the lane, you can generate additional data by simply rendering images and LiDAR point clouds from slightly offset positions to with shifts and rotations, and compensating the waypoints through a geometric transformation. So that was the two ideas that I just talked about. Now I'm going to show some results. So Carla has this logistics benchmark, which is quite challenging. You have lots of weathers, long routes, and the metrics I talked about earlier. The completion is just how far you get to the end of the route, and the driving score is after multiplying these penalties for colliding and running traffic lights, for example. You see that The first idea I proposed of using global attention-based feature fusion over geometry was responsible for giving a huge boost in this driving score metric. So you don't actually drive to the destination much more, but you avoid many more collisions, and specifically because of these scenarios where you need to associate things between the image and the LiDAR, which are geometrically and in terms of modality very far away from each other. And the other change, which was adding the transformer decoder and the data augmentation, is responsible for another decent, like 45% improvement in this driving score to 71. The important thing is that this is actually a pretty big step forward in this field. Some of the most recent work, like over the last 3-4 conferences, have kind of saturated at a score of 60 on this benchmark. But like through just understanding the weakness of these like end-to-end models, these biases in them, we got a pretty big boost here to 71. All right, so I come to the summary now. So the main takeaway, if anything, that I would really hope everyone gets from this is that open loop evaluation is flawed. So until we have better simulators, I think working with the simulators we have is a good solution for end-to-end driving research and for research and planning. The attention-based sensor fusion idea is good at capturing global context, which can be useful for tasks like planning. And the attention-based feature pooling we introduced mitigates these shortcut learning mechanisms where you have very low dimensional inputs like this goal location contributing heavily to your model outputs. The code for all of this research is publicly available. You can find it at this link. We also are releasing a follow-up to this very shortly. I also want to quickly mention that end-to-end driving is a very rapidly growing field. So since 2016 or so, when it was kind of rediscovered in the deep learning age, there have been like over like 200 papers doing end-to-end learning, and one of the main things driving this is Carla. We've had like very rapid progress on the Carla benchmark over the last couple of years, and now there are new open source closed loop simulators like a second version of Carla and something called NuPlan, which we also are really interested in, but unfortunately I couldn't talk about today in detail. Yeah, I'm done. So I would say like this is like really exciting, and like given the other data-driven simulation approaches and improved simulation approaches we are seeing, I would really look forward to basically new solutions and new ideas over time. Yeah, so that is it. I wanted to thank all the team members who are on this project and everyone here for listening. Yeah, on the right you can access my website where we will be releasing like some new work in this area and also on the NuPlan benchmark that I very quickly mentioned. Yeah, so that's it from me, and yeah, thanks. Take any questions now.
Hi, thank you for your talk. So have you ever considered to project your image from the 2D to the 3D first, and something like the BEV, and fuse the BEV format with LiDAR, something like BEV fusion? Have you ever considered this kind of architecture, and why not choose this kind of architecture?
Yeah, so we implemented a very popular recent architecture, actually an ICRA paper called Simple BEV, which basically does exactly this. It projects each 3D voxel basically into the image and interpolates the features based on where they land up in the image. I think we always had the same problem that it was worse at avoiding collisions than the transformer-based fusion. Another like slightly technical but like important issue with the 3D representation of an image is that it occupies a lot of memory. You need to generally have like some voxel representation before you splat it into BEV, which interfaces between 2D and 3D. And this voxel representation, where you have a feature in each voxel, is usually occupying like half of your GPU memory during training, which kind of really limits the size of the rest of the architecture you can use. So this was like one sort of technical reason why I think like these methods, though in principle they could be very strong, like you need to put in some engineering effort to actually make them like perform at the best of their ability.
Thank you for the talk. For the your transformer decoder, you mentioned you use some queries, and I wonder if there's anything special about them. Like, what exactly are the queries? Are they like reference paths or? Yeah.
So there's nothing special about them. It's the same idea as in DETER or like any of these recent transformer-based object detection prediction architectures, where you learn an embedding as a query instead of extracting a query from your input. Then you have a fixed number of such queries, which are common for every sample in your data set. So we use the queries basically with one query for each waypoint we predicted. So if we predicted 10 waypoints, we had 10 queries, and each of them extracts features from the sensors, from the like bird's eye view, that are specific to that scene and that waypoint.
How are you thinking about interpretability with N10 models and validation?
Was it interpretability? Yeah. So we have actually some other work on interpretability, and one tool that we like really found useful for not only showing interpretability as an end product, but for debugging our own solutions as we develop them, was visualizing the attention weights of all these transformers that we now put into our architectures. So this whole global context thing I showed in the beginning as a motivation, we actually observed post hoc after training that this is what the model does in these scenarios. It kind of has some attention heads specifically dedicated to cross-sensor fusion, and some that do local reasoning, some that do global reasoning. The details for this are in the paper if you're interested. We visualized those. We also had a similar approach for planning, like where we used a transformer for the waypoint prediction directly instead of having the GRU decoders. There, if you look at the token that is responsible for prediction, you can kind of see which vehicles the model pays the most attention to while it makes its predictions. So I think like these attention mechanisms, though they aren't like the end, they are a very useful step, and we definitely found them very useful.
All right, let's please thank Kashyap again. We will resume in about 20 minutes at 20 to 4. So, see you later.
Thanks everyone for coming for our last session today. Our first speaker is Dr. Marco Pavone. Marco Pavone is the Director of Autonomous Vehicle Research at NVIDIA. His main research interests are in the development of methodologies for the analysis, design, and control of autonomous systems, with an emphasis on self-driving cars, autonomous aerospace vehicles, and future mobility systems. He is currently on partial leave from Stanford University, where he is an associate professor of aeronautics and astronautics. At Stanford, he is also the director of Autonomous System Laboratory and co-director of the Center for Automotive Research at Stanford. Marco is presenting today with Dr. Peter Karkus, a research scientist at NVIDIA. Let's welcome Marco and Peter.
Thank you for
the introduction, and thank you for being here for the last part of this workshop during the last day of the conference. So I will begin the talk jointly with my colleague Peter Karkus, and this talk is really a good segue with respect to the previous talk when we talked about the benefits of end-to-end architectures, and also relates quite well to some of the questions that were asked at the end of that talk. In particular, I'm going to talk about system architecting problems. What is the best way to architect an autonomy stack in terms of how we decompose it into different components, how do we design interfaces, and so on and so forth. Now, broadly, there are two main architectural paradigms. On the one hand, we have highly modular architectures whereby an autonomy stack is decomposed into a number of different modules such as detection, tracking, prediction, planning, control, mapping, and so on and so forth. Advantages of this architectural paradigm are numerous and include interpretability, reusability of the different components, amenability to safety analysis. But of course, this architecture introduces information bottlenecks, and it gives rise to integration challenges. At the other end of the spectrum, we have monolithic end-to-end architectures, typically implemented through a neural network that, loosely speaking, map raw inputs into control actions. Of course, one of the key advantages of this architectural paradigm is that we do not have information bottlenecks by design, and so one could argue that such architectural paradigm might achieve a level of performance that is unattainable by a modular architecture. And of course, an end-to-end monolithic architecture is well poised to scale with data. Now, empirical evidence seems to suggest that end-to-end monolithic architectures deliver a performance that vastly surpass that is achieved with modular architectures. For example, considering the Carla driving challenge, the top performing methods are indeed monolithic end-to-end for the most part, and also their performance has improving quite quickly, quite rapidly over the years as more data has become available. In contrast, modular architectures have been lagging behind, and even worse, haven't really been benefiting from the increased availability of data. So this forces us to wonder whether it is indeed true that there are some fundamental limitations of performance that are implicit in a modular architectural paradigm. And the answer, this is a little bit messed up, but it should be still understandable. The answer is not quite. And so actually, it's not really true that there is something fundamentally wrong in a modular architectural paradigm. And to illustrate this point, let me first consider a relatively simplified setup, whereby the problem is a standard decision-making problem where we want to control a system with a state x of k, and I'm sorry that here the slide is a bit messed up. But the problem is so common that you should be very familiar with. So we want to control a system with state x of k by selecting a control action c of k based on observations that are possibly noise corrupted at z of k. We define an information vector I, which is basically the history of measurements and controls up to the current time. And we consider closed loop policies that map the information vector into control actions. The problem is a standard decision-making problem where we want to find a closed-loop policy that minimizes average performance with respect to a cost function that is described by the functions g sub k, subject to the dynamics described by functions f of k. Now, it turns out that the conditional state distribution, the distribution of the state conditional on information vector, is a sufficient statistic. So you can write the optimal control policies as a mapping from the conditional state distribution to the control actions. So explicitly what this means is that, at least theoretically, you can always, in a nonlinear setting, in a stochastic setting, decompose an optimal controller into an estimator, which is your conditional state distribution, P of S k conditional I of k, which is an estimator that updates the conditional distribution of the state given a new observation and a previous control. That's the first part. And the second part is a policy that basically maps such a conditional state distribution into control actions. So this interpretation has led to, of course, a variety of designs that separate a priori estimation from control. And then designers typically try to design in a suboptimal way each component. But the key point here is that the suboptimality stems from the suboptimality in the design of different components and not by the fact that we have introduced such a separation between estimation and control. But this is theoretical. So what we did to gather more empirical evidence about this hypothesis was to go back to the Carla driving challenge and now implement a modular stack that is more aligned with the state-of-the-art models for the different components. So for example, we have implementing transformer-based architectures for detection. We have implemented SOTA 3D multi-object trackers, and then from the prediction side, we've been implementing multimodal interaction-aware prediction algorithms. And the results are quite striking. So when you actually design the modules with more state-of-the-art components, and we go back to the Carla challenge, and we look at the standard local closed-loop challenge evaluation, now the modular stack outperforms basically everything that you have there by a large margin. So for example, if you look at the driving score, 80%, so the modular stack is the one depicted with the green bar. We call it SMS. SMS, not a great acronym, but anyway, Safety Enhanced Modular Stack, as we wait for a better acronym. Anyway, so the point is that the modular stack, now with the modules that are much better designed, significantly outperforms the end-to-end stack. So actually the claim that necessarily the modular architecture is suboptimal with respect to a monolithic end-to-end architecture is not quite true, at least based on this theoretical reasoning and empirical evidence. And if we actually consider the setting where we have access to privileged information, just a thought exercise, so basically we use privileged information from the simulator to have a perfect state observability, then we achieve actually perfect performance. Okay, so it seems that actually there are benefits to modular architectures, but now the elephant in the room is how do we scale then these modules with the data? As I said before, one of the key advantages of monolithic end-to-end architecture is that it's very well poised to scale with data. Modern architectures do not have anything fundamentally wrong, but of course, practically scaling them on data, with data is much more challenging. And with that, we'll go to the core of the presentation that will now be given by Peter.
Thank you. Hello, everyone. Yeah, exactly. So just as Marco argued, or at least showed some evidence, that modular designs can actually perform very well as long as we design all the modules very carefully and we define all the interfaces carefully and all that. But of course, this is very hard in practice. And exactly as Marco was just saying, it's not that straightforward to scale these modular systems with data, right? Because the different objectives for these modules are not directly linked to the final performance, right? So just because I have more data does not necessarily mean that I improve my stack. And the appeal of the kind of end-to-end monolithic type of approaches is exactly that they can scale with the data. Although in that way we have to give up all the benefits of modular things, just as reusability, interpretability, safety guarantees. So in this part of the talk, I will talk about how we can, whether we can find some compromise between these architectures and design the autonomy stack in a way that is modular, but at the same time scales with data and end-to-end training. And to this end, what we are looking at is to develop these differentiable yet modular autonomy stacks that basically take all the existing components of a modular stack, make them differentiable, and that this way allows joint end-to-end training over multiple modules. The key to do that is basically to use a differentiable computation graph to represent both neural network type models and algorithmic model-based components of a stack. And because of the differentiability, we can now do backpropagations through the modules and train more than one modules together, directly optimizing upstream modules for downstream tasks. And so maybe I imagine it might be surprising to some of you that we can also do this for analytic algorithmic components. Of course, the neural networks are differentiable. They're designed to be differentiable, so we can backpropagate through them. Now, a growing body of work has also explored the idea of differentiating through existing algorithmic computation. And again, kind of like, it's not magic. It's really just to say that we express an algorithmic computation as a computation graph, and that we can treat it the same as a neural network. We can compute gradients of the outputs with respect to learnable parameters of that module, or gradients of input with respect to the input, as long as all these operations of that computation are differentiable. And in fact, of course, in these algorithms, not all operations are differentiable. So, for example, max or sampling from a distribution. So, fortunately, in the past years, there has been a number of works that address this problem and introduced various ideas, such as replacing max with softmax. So, this kind of like approximations for differentiable approximations. You can do reparameterization for sampling. And that there are much more complex ideas that analytically compute gradients for larger computation blocks as well. And so using this set of ideas, there's a growing literature on differentiable classic robot algorithms. So these include, for state estimation, we have these differentiable Kalman filters, particle filters, and so on. We have differentiable planners for MDPs, PoMDPs, the graphs, and we have differentiable controllers, modular predictive control, and other kind of convex optimization. Now, we not necessarily argue that we need to use these particular modules for autonomy stacks, but we do have the option to use them, and which means that we open up the design space between, just a fully end-to-end neural network monolithic architectures and entirely modular classic algorithmic components. So what we are looking at concretely is how to build on this literature to build these modular yet end-to-end differentiable autonomy stacks. And we did a first step towards this, a first exploration in this Coral paper from last year, where we looked at the prediction, planning, and control modules. Now, these choices of modules we find them interesting not only because of the importance of these modules, but also because in a typical stack, the prediction model is typically a deep learned model, whereas the planning and control modules are oftentimes classic algorithms. What we did concretely is that we used this recent prediction model, Projection++, as our prediction model. We had a planner which consumes these predictions. In this case, this planner is a sampling-based planner. It generates a set of ego trajectory candidates, ranks them with a handcrafted cost function, and chooses the lowest cost candidate. Now, this trajectory candidate then further optimized with a controller. In this case, is an iterative LQR type model predictive control algorithm. Now, what we did normally in a standard stack, you would train your prediction model to optimize some sort of predictive loss, and you would handcraft your planner and the control modules. Now, what we did in the differentiable stacks that we keep these exact algorithmic, all of the components, both the predictor and the planner and controller, but we make them differentiable by essentially in the planner relaxing the mean argument operation with sampling, and in a controller we use this differentiable MPC from the past work. Now, what this allows us to do is that we can now train our prediction model not only to give accurate predictions, but also to optimize some downstream losses at the planning and control level, right? So we chose appropriate losses for each of these modules, an elbow loss for the predictor, and appropriate losses for planning and control. We can come back to the details here if you are interested later. And then in experiments, what we compared is a standard stack that essentially only trains the prediction model for a standard prediction objective and has the planners and controllers handcrafted, and the differentiable component that also still only trains the prediction model, but it trains them for a combination of prediction and planning and control objectives. Now, what we then compared is the prediction performance in terms of average displacement error, and the planning performance that here for which we use a difference to an Oracle planner in terms of a percentage. So here the Oracle planner essentially means that it's a planner that has access to the ground truth future of trajectories of other agents that we don't know at the planning time. Right, so what we see here is that although the two stacks perform very similar in terms of prediction performance, but the differentiable stack performs significantly better in terms of planning performance. Right, concretely we reduce the gap to the Oracle from 28% to 17%. Now, how is that possible? That is because not all prediction errors are born equal, right? So if I'm saying that I predict somebody, a pedestrian stepping in front of the ego vehicle, is a 1 meter error, say, is not the same 1 meter error that if I predict it wrongly to move, just in the distance of 1 meter off. So the same prediction errors can have vastly different consequences on the downstream planning, right? And by having the ability to train the prediction model directly for downstream objectives, we inform this model about what really matters for the overall task of driving safely, right? And so we kind of saw these in concrete examples of how this happens, basically removing these kind of spurious predictions that would hurt planning. Now, of course, these were just a very first step. Our longer-term vision is to build entirely differentiable full end-to-end stacks, including detection and tracking components for the perception side. And we believe that this would open up various exciting opportunities. The one, joint training, was what I have been talking about so far. But beyond that, it would also allow us to start relaxing maybe some of these rigid interfaces, start learning these representations in between modules, and similarly propagate uncertainties between modules and learn to use those uncertainties by the subsequent modules, right? So on the high level, why we are really excited about these differentiable stacks is because, not necessarily because they mean that we can keep the same modular structure, but because they really open up the space, the design space between fully modular classic stacks and entirely end-to-end monolithic neural network type architectures, right? And it only requires us to think in this kind of common representation of the differentiable computation graphs. Okay, so far I have been talking about how to kind of scale up a modular architecture with more labeled data. Now, of course, labeling large amounts of data in the driving domain can be extremely expensive, as a lot of other speakers have argued before. And so we are also looking at how we can scale autonomous stacks or modular stacks with unlabeled data, right? And specifically, we are looking at learning scene representations from large amounts of unlabeled data. Why do we need to learn representations? Well, the most common predefined interface for autonomous stacks are bounding boxes. Now, the bounding boxes have a lot of limitations. Maybe the most important one is that the way that we come up with these bounding boxes, of course, is like these learned detectors. And these learned detectors are going to struggle with rare objects, right? And if we don't have for a certain category of objects a sufficient coverage in the training data set, then these bounding box estimates can be arbitrarily bad, right? And beyond that, it's also kind of difficult to represent objects with arbitrary geometry as bounding box, like a crane overhanging the road, things like that, or a dinosaur. And we also have information loss from these bounding boxes, right? The sensors contain much more potentially useful information for decision making than just a box. All right? So we are looking at something kind of like an interesting alternative to this, that is learned occupancy representations in voxels, where we would augment an occupancy voxel with learned features, right? These have a potential to overcome some of these challenges. We can expect that the voxels are better at generalizing to unseen objects because they are not about bounding boxes but only space. Also, they might be, when we augment them with these learned features, they might retain more information coming from the sensors. So the key to the approach that we are looking at is a generalizable neural rendering or volumetric rendering. And so I believe many of you have heard of these volumetric rendering ideas coming from computer graphics originally. You might have heard the name NeRFs or many of this implicit representation learning. So the key idea here is that you represent the scene by a set of learned features organized into a voxel. And then you will do differentiable rendering in order to reconstruct 2D images from any viewpoints in this 3D space. And so this way, you can supervise this state representation learning just from images. Now, in the original setup, you typically learn a scene representation for a single scene. But to make it useful for autonomous driving, we want to make these generalizable, so that what we learn it can be, they also work in an entirely new area. So concretely, this is a work that is very much in progress, but that I can share kind of like the high-level ideas here. The architectures we are looking at takes in multi-view images from onboard cameras, and then pass it through some feature encoders, which could be just transformers or ResNet or something like that. Then we lift these 2D features into 3D space, essentially by a separately learned depth estimator. Then we project back during training from 2D to 3D through volumetric rendering, so which means essentially doing a small neural network that maps from these learned features to colors and occupancy density values. And the differentiable rendering can then generate a 2D image from arbitrary viewpoints. So, of course, one main advantage of this is that you can train this in a self-supervised manner. So now to train, we don't need label data. All we need is a sensor streams coming from images. And in addition to that, kind of like an orthogonal idea that we are kind of experimenting with is to also try to distill foundation model features into these representations. Whereas we specifically clip features here, so we ask these learned latent representations to be able to also reconstruct some pre-trained features coming from some foundation model. And I will show you very soon why that could be interesting. So these are some very preliminary results. Here on the top you see that where we start from a set of fixed images, which are the input to this scene representation learning technique, and we then ask it to generate new images from a moving camera. Okay, and the first row is the RGB images, the second row is the depth, and the third is some mapping of the latent features. And these results are kind of encouraging in the sense that although, of course, the video on the top gets blurrier over time, but the depth and feature map remain kind of spatially more or less consistent. Now what we can also do, thanks to these clip features, foundation model features, is to do open vocabulary scene manipulation. So here what we are doing is that we ask this representation to keep only the cars, or keep only the road, or discard the vegetation from the scene representation. And we can achieve this quite simply by basically looking at the clip language features for the language query input here, and doing some nearest neighbor search in the feature space of the learned representation. And this way we can do this kind of like an open vocabulary scene manipulation. Now, of course, these are so far only learning these representations on their own. We are also, of course, now looking at how we could connect these to the differentiable stacks, downstream modules, so that they can also kind of be useful for downstream prediction or decision making. Now, one kind of like a side topic here, depending on, I still have time for this. I wanted to mention a few tools that we are developing that could be kind of useful for the broader community. So first, this code base we have called Traj Data, or is a unified trajectory data loader. So the motivation for doing this was actually to make our own life easier. There are lots of open source data sets available on trajectory level driving data that all have their different interfaces, their map APIs are entirely different. So it's quite difficult to have your model trained on one data and test it on another one, or train on multiple data sets and so on. So what we kind of put out here in this open source code base is some joint wrapper around these data sets that specify a single unified representation both for the trajectory data as well as a map API that allows you to do kind of also the prediction, run prediction models as well as a planning on top of them. And it also comes with this visualizer that kind of neatly visualize that data. Another kind of code base that we are developing, this is still kind of not yet released, is this full stack, modular stack code base that will basically have an easily configurable state-of-the-art modules, both for perception, prediction, and planning, and that is compatible with many of the open source simulators, end-to-end simulators, Carla, NewPlan, and also NVIDIA's own simulator drive sim. So we achieved this basically by making this kind of code base compatible with the open MM3D MMCV library that contains many of these open state-of-the-art perception modules, map them to this Tredge data interface that, which then allows us to kind of use a large set of, make it compatible with a large set of prediction modules and the planning components. So these were all the tools. I want to end with recapping all the main points that we try to make through this presentation. So Marco has been talking about the benefits of modular stacks and the fact that actually modular stacks can work very well as long as we design each of the modules carefully. And we showed this in this case by new state-of-the-art results on the Carla benchmark. Now I have then talked about how can we scale up modular stacks with more labeled data, and our answer to that is this representation of a differentiable yet modular stacks, where we kind of can keep both neural network components and algorithmic components, make them all differentiable, and this way we can kind of train more than one module together. It does not mean that we want to keep necessarily all these modules, but this really allows us to have all sorts of architectures in between the two ends. And finally, we talked about how we could potentially scale modular stacks further with unlabeled data. And for this purpose, I introduced this learned scene representations using generalizable neural rendering and the foundation model features. Okay, so with that, thank you very much for your attention, and I'm happy to take questions.
Could you comment on the performance of this volumetric rendering approach, self-supervised training approach on distant but moving objects?
Distant with moving objects. Well, I suspect that they will not do that well. I mean, this is just a very early exploration, so we don't actually have qualitative results on anything. I suspect that they will be harder to model there. But this is a very quick thing that we put together, and it's already showing very promising results, so that kind of encourages me. Now, of course, more broadly, I would hope that we don't have to stick to necessarily exactly this type of learned representation. Personally, I think that another kind of advantage of this thinking of the stacks in terms of these differentiable computation graphs is that they really allow you to kind of combine the different modules and potentially different representations. So I could envision an architecture in which you would still kind of maybe keep the bounding boxes that are augmented with this maybe learned scene representation, for example. Yeah.
Thanks a lot for this excellent talk. It really resonates with a lot of things, I think, in the community. You have these individual modules that you want to train jointly, and the initial approach you showed, you had a loss on each of these modules. Ultimately, I suppose you want to get rid of these individual supervisions, right? When you do that, do you think there needs to be a strategy to make sure that the module that does detection remains doing detection and detection only, and the functionality stays in the respective modules, so that you keep your modularity of being able to replace one part with the other, for example?
Yeah,
because otherwise you'll end up with an end-to-end system that you started out from individual component and then trained.
Yes, yes, absolutely. Do you want to answer? I can. Yeah, yeah. So, yes, absolutely. I mean, very good question. I mean, I think architecturally why I like this again is because it's not necessarily that I need to commit to one or the other. I mean, I conveniently say that because I'm not, developing an actual car that he needs to drive tomorrow. So I kind of leave it to the designer in some sense. Indeed, you could remove more and more of those losses, and this way you kind of like get closer to a monolithic neural network architecture. So in some sense, this is a design decision in my mind. Now, in practice, I think it can be quite useful to keep those labels. And this last section about learn the scene representations, I think is one way that allows you to not have to have a large amount of label data for detections, for example, or predictions, all that. But you probably still need some, I suspect. So the interesting thing here would be how to combine them, right? So if you have these learned representations that mainly are trained from unlabeled data, then you can kind of connect them into this differentiable stack, and perhaps together or in a second training stage, you can then train them to be more useful for what you are trying to use them for. That is detection or planning performance. I don't know if that makes sense.
Imagine training this with losses on every module is super expensive because you need consistent labels, right?
Mm-hmm.
Through the entire stack, whereas previously you would just have labels for detection and some for planning and some for prediction, but they could be different. Here you need sort of the entire scene label throughout the stack.
Yes, so that's true. I mean that also. I mean we actually it's not necessarily the case that we want to have all these different modules and all these different losses and necessarily train them together from the beginning. It is also possible that you just want to train a subset of these modules. Say I want to train my detector and a tracker together, or maybe for the majority of the training time. And then maybe I can do like some smaller amount of joint training just to make sure that, they're more aligned with each other. And that this kind of like, even our early results are somewhat surprising that how much you can gain from doing that, right? So yes, they become more challenging to do so, but potentially you can gain a lot from it.
Okay, does this kind of modular stack allow to replace some of the components with something that is not learning based? Say you want to use a traditional controller, or you want to compare your old planning with a new learned one?
Yes, absolutely. And that technical idea there is this concept of differentiable algorithms, right? Which in this case, what the results I showed for was actually exactly like that, right? I had a learned prediction model, but I had this fully classic handcrafted planner and MPC, iterative LQR controller, right? And the key requirement there is that we can make these algorithms differentiable. Now, it turns out that we can make many of the standard robot algorithms differentiable, or very well approximate them in a differentiable manner, while keeping exactly the same kind of computation, right? So that potentially we can do this. And of course, we might want to replace some of these modules with machine learning-based models, or we can keep some of these modules. And so both of them has pros and cons. But we definitely can do that, yes.
Yeah, the main point here is really to open up the design space and try to be a little bit more quantitative and rigorous in how we discuss different architectures. Many times there's more abstraction calls and we're a bit dogmatic in which type of architectures we want to commit to. The idea is that to automate how we trade off different architectural paradigms.
Thanks for your talk. And I would ask one question about the third one, unsupervised training. So if you use unsupervised training to train it, how to guarantee the 3D structure, how to guarantee the geometry? Because basically you from the 2D image and training back to the 2D image, the 3D structure may be totally wrong, right? So how to keep the geometry? Do you use multiple frame or not?
Yes, exactly. So, I mean, firstly, you don't really guarantee anything, and it's a learned representation, but how you are trying to enforce that is through these reconstruction objectives through time or through different view angles. So in practice, what that means is that you might have a sequence of sensor data from multiple cameras, and that you are asking this learned representation to come up with a voxel, an occupancy grid, that when I render an image from a different new viewpoint, I get the image I want, right? And that is usually only possible if I got that geometry more or less correctly, right? So this is similar how like a nerves come up with a 3D space. Yes, multiple time, and not, I mean, potentially multiple through time. Even if you try to reconstruct something just from a new viewpoint at the same time, you can achieve the same potentially. But I suspect that training this over time would actually be even more helpful.
All right, let's thank Peter and Margot.
Thank you.
Okay, please allow me to introduce our last speaker, Jimmy Shotton. Dr. Jimmy Shotton is a leader in AI research and development with a track record of incubating transformative new technologies and experience from early stage research to shaping product. He is a chief scientist at Wave, building foundation model for embodied AI to enable safe and adaptable autonomous vehicles. Prior to this, he was a partner director of science at Microsoft and head of the mixed reality and AI labs, where he shaped fundamentally features including body tracking for Kinect and the hand and eye tracking that enables HoloLens tools, instinctual interactive model. He has explored applications of AI in autonomous driving, mixed reality, virtual presence, human-computer interaction, gaming, robotics, and healthcare. Jimmy Shotton, it's yours.
Thank you very much. Good afternoon, everyone. I realize this is the end of the day, the end of the week, so I will try and keep the energy levels up. Thanks for joining. Thank you for the organizers for putting together this fantastic program throughout the day, and all the other speakers. I've really enjoyed those talks. I'm going to be talking a little bit about some of the work that's going on at Wave, just a sort of flavor of some of our research. Of course, there's a huge team working behind the scenes on this, and it's my privilege to present on their behalf today. So thank you to all of them for the work that they are doing. Okay. So, this is the kind of driving environment that we are facing here in London. As you may have experienced yourselves, it is a very complex, unstructured environment. You have, small, narrow roads, few lane markings visible in a lot of cases, very dense traffic, lots of unstructured undertaking by mopeds, buses coming down the wrong side of the road, etc., etc. And so from the outset, thinking about how would you go about actually solving an autonomous driving system for an environment like this, Wave has been pioneering the idea of treating autonomous driving as an embodied AI problem. And I'm going to spend the majority of the talk explaining a little bit about what I mean by that. And what we're building towards is something we call AV 2.0, it's adaptable and scalable driving intelligence that can quickly generalize to new cities, countries, and driving cultures, that's largely vehicle and sensor agnostic, and that learns policies that align with human driving. Last year, we took our models on the road across the UK just to see what happened, right? Our hypothesis is that if you learn from a sufficient amount of data, you can generalize quickly. And lo and behold, that's what we did. So we took our models that have been trained only on data here in London, across different cities in the UK, Cambridge, Coventry, Liverpool, Leeds, Manchester, and with no additional training or fine-tuning, we were able to see near enough identical driving performance to what we saw in London. More recently, we've been extending from our first car here, the Jaguar I-Pace, to a van to help us with our grocery delivery pilots. And again, we wanted to see what the performance of this was going to be and how we can generalize. So we got different, the sensors in very different positions, but we were able to show that we could combine the training data from both car and van and drive better for both the car and for the van. They can learn from each other. And so here's a little sort of test run we did around London with the van following the car. And it's exactly the same neural network driving both these two vehicles. More recently, we were privileged to have Bill Gates along for a ride, and here's a little short snippet of the fun that he had along the ride. Do watch the full video on YouTube where he goes to pick up some fish and chips. But we took him on a ride throughout very central London where we hadn't, again, it's not our main testing ground. We hadn't trained on these particular routes and encountered some, remarkably complex scenarios as you sort of see here. And navigated it pretty reliably. On the back of the core driving technology we are working with our partners, Okada and Asda, and as of a few weeks ago, have live grocery delivery pilots here in London. Of course, this is just one possible application, and we're exploring many others beyond this in the future. But that's just a quick introduction. I want to spend the majority of the time more on the tech. And I'm going to start with a little bit about what's been going on in AI. And I think, nobody in this room is blind to the incredible progress that has been seen in the community over the last few years, and certainly the last 2 or 3 years. It has just been mind-blowing. Here's just a few things that happened along the way. This slide is, I've stopped bothering updating this slide because it gets out of date before I, give the talk. But there is just so much progress in the community. And it's interesting to sort of step back and think about what's underpinning this, where this is coming from. And so I divided it into a few categories. I don't think this list is going to be exhaustive, but hopefully indicative. So first off, large training data sets and benchmarks, right? These are things like ImageNet or large language corpuses that are available from the web. And these have allowed the community to start moving beyond toy problems, bring in the sense of competition in the community and through these benchmarks, and rapid feedback cycles so that you can get a number and, let's try something else. We get some gradient. Next up, you have games and simulation. This has underpinned a lot of the stuff that DeepMind has done in particular. You get interesting things like self-play, where you can, you can play the game against itself. Again, very, very fast, rapid iteration in here, that fast feedback cycle for specifically decision-making tasks. More recently, we're seeing self-supervised learning really coming to the front. And here, the key is that you're able to learn from effectively unlimited quantities of unsupervised, of unlabeled data. Foundation models, sort of building on those self-supervised models, especially in language, are, as we heard earlier, right, allowing you to learn these task-agnostic models that can then be fine-tuned or prompted to do particular tasks that you care about, and giving lots of efficiency when it comes to learning, but also generalization from one task to another. To improve both. Scalable compute, obviously the general purpose GPU compute and the explosion of that has underpinned a huge amount of progress and allowed us to scale up models and data. Furthermore, the architectures underpinning those, especially transformers, have allowed us to start plotting scaling curves and really extrapolate out and predict before you actually do the experiment what things are going to look like, and giving you, furthermore, some often emergent properties that you get with scale. Multimodality is also underpinning a lot of the very recent breakthroughs, particularly vision and language, but other modalities too. And the idea that you can learn from one modality about the other, grounding concepts from one to the other, and do so in a more efficient way. And we'll come back onto this later on. And perhaps most recently is this concept of alignment with human goals, preferences, and this allows you to take those foundation models, which are trained from these enormous unlabeled corpuses of data and incredibly noisy and don't contain, and left to their own devices will spit out hate speech or whatever, and then to fine-tune them to a particular application and a safety envelope. And so that's the list there. That you could throw in a few more. I'm sure things like open source could easily live on this list, or archive as a way of quickly getting publications out. But I wanted to stick to 8 for the slide. But this is to me what I think are the big things underpinning AI. And so coming back to this slide, I think we've seen all of this apply to these various domains here, and I really believe that embodied AI, robotics, autonomous driving, etc., is next in this, next to reap the benefits of what we've seen elsewhere. So I'm going to dive into sort of 4 topics today, all very briefly, and we'll explore some of the work that we're that's going on at Wave, aligned with those breakthroughs that we've seen so far. So let's dive into simulation. And of course, simulation is very much in our world around these benchmarks and potentially training data as well. And why is this important? And we saw in the talk earlier just how bad open loop testing is for what we're doing. We need these closed loop simulators. Of course you need to go and test on the real road. This is of course a critical component of any autonomous driving stack. But that doesn't scale very well. It's expensive, it's slow. You can't easily test dangerous scenarios. Simulation offers a potential path to get over that and to give you this scalable, closed loop, repeatable simulation technology. But of course, you've got that sim to real gap to worry about, which is not just about the visuals, but also about the behavior of the agents that you see in the scene as well, and many other things. We've been working on what we call Wave Infinity Simulator for a while, which is a model-based simulator. As you see here, underpinning it is a sort of model of the world, and we can render that. And because we are doing end-to-end learning, we need this simulator to effectively be this end-to-end simulator that can go, from pixels to and understand the whole stack. This is, one of the things underneath this is the ability to procedurally generate diverse training maps, training environments that you see on the slide here. And, throwing this all together, and where it gets its name from, of course, is that you can then generate as much test data and test scenarios as you want, and, get a huge amount of diversity in that. Of course, does it work, right? Does it help you do anything? And so I'm going to play a video now, which is a model, an end-to-end neural network that has been trained purely on real-world data, and we're now putting it in our simulator. It's got, it's never seen the simulator before, and we're able to drive zero shot in the simulator. So even though what we have here is clearly visually, worse than the real world, it is sufficiently good to allow us to cross at least the real to sim gap here and drive well there. And we find that when we measure this, we are able to use performance in simulation as strongly predictive of what we see on road driving. But we want to go further. And so one of the things we've been looking at is resimulation using neural radiance fields. So taking a real-world scene, not one of those artificial scenes, and turning that into something we can drive through. If any of you saw our booth earlier in the week, we had a little toy demo of allowing you to actually get behind a steering wheel and drive yourself around this. But you know, the key point is that we can reconstruct these environments in beautiful detail and then re-render them. Perhaps you can also do things like semantic segmentation within this, where you get a lot more consistency both temporally and geometrically across views, etc., because it's all done in 3D. But the ultimate reason to do this is so that we can start to test and potentially train our models using this kind of data. So here's an example where, again, we've taken a real-world model, trained only on real data, and can drive it through this neural radiance-based, field-based simulator and compare it very, very closely with what we saw in our log replay. So, in simulation, I mean, for my money, the grand challenges here are how to, you know, first of all, how to further close this sim to real gap. I think neural radiance fields offers a very interesting way to do it in terms of the visual realism, but there's all sorts of other things, especially behavioral realism, which we'll come on to in a second. How do you prove a simulation is good enough? And how do you get the best of both worlds between things like neural radiance fields and these more you know, procedural and model-based simulators that we saw as well. So moving on, let's look a little bit at reinforcement learning for driving. And this aligns, going back to that menu earlier, this aligns very much with the advances that we've seen in games and simulation over the last few years. Just a quick recap, I'm sure most of you are aware of this, but reinforcement learning, the situation is you have some environment, you have an actor or a policy that takes actions in that environment, gets observations, and of course gets a reward, some form of reward signal that can be used to then update that policy to improve your driving or whatever else you're doing in this environment. Wave has been looking at this for a while, and you know, one of our early works from 2019 was learning to drive in a day, where on this track here we were effectively randomly exploring to start with. The driver would take over whenever it was about to go off the road, repeat a few times, and if I skip ahead a little bit, by the end of the day, after a few episodes of this, we were able to drive smoothly and performantly on this road using very, very simple RL techniques. But of course, the world does not look like that image on the left, and it looks much more like the image on the right. And the thing that you notice about the image on the right is the people, the people either on the street, the pedestrians, or the people driving the cars and the buses and the bicycles, right? And so it's the real-world complexity of behavior that makes this challenge hard. So coming back to sort of what's good about reinforcement learning, you know, it's superficially a bit like human learning. You can encode in those reward signals some intuition about the actual rules of the road. You get to explore and cover a large amount of the state space. You can do it end to end, and there's many success stories, especially in gaming, of this working really well. But of course, it tends to be fairly poorly data efficient. You get this phenomenon of reward hacking, where it tries to like find the best, the easiest way to get reward that's not exactly what you actually wanted if you don't get those rewards right. And of course, most importantly, it requires exploration in an environment. And that's not something you can do on the real road. But you can, of course, do it in simulation. And so we come back now to the Infinity simulator we saw earlier. And we've been working on multi-agent reinforcement learning in this simulation for urban driving. So same kind of maps we saw earlier, but now we have all of these little dots moving around. This is sort of sped up for visualization purposes. But these are all independently acting learned agents, learned through reinforcement learning. that are able to move through this. We can learn this. Most critical to the success of this is we've been able to learn this at about 700 times real-time speed, partly through distribution and partly through a very efficient tokenized input. And over a few billion training steps, you're able to get really beautiful, dense driving behavior as you see here. As we've been doing this work, we've been thinking, working with a few principles, or at least, considerations that we wanted to explore. Having the agents act independently as we do in the real world. We don't talk to each other as we're driving along. Having a very, very simple set of rewards that can lead to emergent behavior. So the reward signal here is basically making progress to forwards and not hitting into any other vehicles, and that's basically it. The ability to quickly, as we improve the simulator, as we bring in new parts of our ODD, to be able to quickly retrain that and see that these agents will be able to cope with an expanding complexity of the world. And a single algorithmic approach that is capable of dealing with all of the diverse types of agent that we see on the road. As I said, one of the keys to making this work is just a very low-dimensional tokenized representation that can be fed into our learning network. When you do this, this is just a different visualization of those maps I showed you earlier, but you get some really interesting emergent behavior. So here, learning to give way for this narrowing in the road because of the parked cars. Here, learning to give way, and there's a few different variants of this. And, again, resulting in fairly human-like behavior from very, very simple emergent, very simple rewards and emergent behavior. We also have played around with the concept of universal agents, a bit like what we saw with the car and the van earlier here, a bicycle that's driving the same policy as the cars here, but has learned how to navigate this scene, and we can learn from the diversity of agents in this scene. And this is a little bit. This was a fun video we put together, which is showing that you don't have to have just expert agents driving around the scene. You can have poor drivers and even adversarial drivers as independent agents acting in the scene. And so this is a particularly nasty intersection, which actually the bicycles probably aren't that far from what actually happens certainly in the UK. And of course, you wouldn't want to learn from this, but this is a great test bed that you should be able to be robust to. Now, the interesting question is, okay, we've got these agents that can drive performantly in our simulator. Can we actually turn them, and using privileged information, can we turn that into an actual driving policy that can take an image in and drive out? And the answer is yes, following this sort of idea from Zhang et al. And so here, this is just a very simple neural network that takes the image you see at the bottom left as its input and is driving off that rather than off that vectorized state that we saw before, and able to navigate through this dense traffic where all the other agents here are populated from with those RL agents that we saw earlier. So of course, there are some challenges that remain here, and I think the big ones are, can we close the sim to real gap so that you can learn those RL policies purely in simulation and then transfer them back onto the road and see driving that is commensurate with what we see in simulation. That's, I guess, the grand prize here. Can we learn those rewards? Maybe we've got the right set of rewards, but maybe we need to learn those. And can we shape these policies with human feedback? Okay, and then on to the next one, language meets driving. This one I'm super excited about. And of course, comes back to multimodality on this menu here. So large language models like ChatGPT already encode a huge amount of knowledge about driving, right? They haven't seen any driving, mostly until the very recent ones haven't seen any image data, but they've seen a lot of text. So you can ask them questions, right? You can ask, you say, you're driving along a road and a ball rolls out onto the road in front of you, what might happen next? And you'll get a reasonable answer, right? If a ball rolls out, you may have to brake or swerve to avoid hitting it. It could cause damage if you don't. It could be a distraction and cause an accident with another vehicle, so drive cautiously. And then you can, keep probing it, right? How would your answer change if you were driving near a school? If you're driving near a school, then you have to be extra cautious, right? There could be children around. And so, there may be additional crossing guards or crossing signals so there's a lot of information here. And then, is it still true if the time is midnight? And then it sort of correctly answers, well, there's probably not going to be children around, but you should still be cautious, of course. I actually, just before the talk, I did one from the talk earlier, where what should I do if I'm at a T-junction and I see a motorbike coming along the road, but the motorbike doesn't have a driver on it, right? So this is the example we saw earlier. And, lo and behold, it produces a pretty reasonable answer about what you should do. Now, of course, this is only text, and that is not a driving policy. But it points out that there is just a huge amount of knowledge, human knowledge, that has been encoded through all of its data sources, and increasingly, I believe, also reasoning capability that these models are able to show. And we've been playing around with using language to start to interrogate our models and to try and build a little bit of explainability from these end-to-end networks. So here's a little example in simulation here, where we have this, this green car cutting across, and we're able to get our language system to output the text below. As we drove, the green compact car in front of us suddenly changed lanes and started moving in our direction. To avoid a collision, I slowed down significantly. Meanwhile, the brown sedan on the left continued moving out from left to right, crossing our path. It was a bit tense, but we managed to handle the situation safely. Of course, the last bit, less relevant, but this is, I think, a really, really interesting avenue for us understanding and being able to question these models about what they're seeing, why are they making decisions, and to build confidence that they are taking into account all of the important things in the scene. And we've all heard the phrase, a picture is worth 1,000 words, but actually, in this world, I think a paragraph may be worth 1,000 pictures, right? If you look at this image here, which is, again, from one of our test runs around London, I can answer questions as a human about this that provide a huge amount of context to someone or some AI that is trying to learn about how to drive. I can say, well, what do you need to pay attention to? Well, there's a zebra crossing straight in front of you. There's pedestrians on that crossing. You need to make sure that they have cleared the crossing before you are able to move forward. Once you move forward, you're going to be at a T-junction, so you have to stop and wait and make sure that there's no traffic coming. You're also going into a 20-mile-an-hour zone, so your speed limit will have changed now. And there's cars coming, and there's a car emerging from the end. So there's just so much information that you can very, very cheaply and easily describe in language that would take an enormous amount of image or video training data to convey to a model. And I think this kind of language-based supervision is a really, really interesting avenue to bring to help these driving models to understand causal factors in the world and the driving task more generally. We are actively working on recording and capturing data sets. This is an example from one of our safety operators driving around London, and just some of the kind of data that we're getting here. And I need to move to the left very slightly, so I'm checking to my left and ahead. Very, very interesting commentary that comes out very quickly and naturally to these drivers. So this is really just a beginning, but and huge challenges ahead here. But first off, can we ground vision, language, and action together? Can we learn the rules of the road from written laws? Can we take intervention reports and write them up in text and explain why something went wrong and use that as a rich source of supervision? Can we use the reasoning capabilities that LLMs encode to help address the long tail in autonomous driving? And can we use vision question answering to help us build a more explainable and a system that we have more confidence in? Okay, I'm going to finish with the last section on world models. And this is going to, as you'll see, play very much on these topics of self-supervised learning and foundation models. So to be able to drive well, you clearly need to have some ability to predict the future and then the different possibilities of that future. From a single image, you don't know whether this car is moving or stationary. From a video, it's a little bit more clear, right? They are actually, stationary here. But there's a possible future where they accelerate wildly out in front of you and you have to brake suddenly. So you need to be able to understand this. And the concept of a world model is really a generative model of the world dynamics conditioned on your actions that you can then use to improve your policy. And so there's been some exciting work recently in game playing, using this for model-based reinforcement learning. Lots of excitement from Yann LeCun. He's very, very keen on this and believes this is a key part of how you build a general intelligence. We've been looking at this task for a while in different guises, and I'll just very quickly go over a couple of those. Fiery, which was out a couple of years ago, was learning from a sort of bird's eye view semantic segmentation representation, some of the diverse future possibilities that you see here. And you can start to see in these turns some of these multimodal futures that are coming out of this. More recently, we published MILE last year, model-based imitation learning, which working in Kala, we were able to learn how to build this world model that would be able to predict and unroll stably into the future, as you see in that example in the bottom right. And at the time, at least, it gave us a significant boost on over the state of the art on the Kala situation, and gave us this really remarkably stable representation that would allow us to effectively unroll indefinitely and get meaningful results out of this. This was a pretty simple autoregressive architecture where we would encode from the observation, the image, up to some hidden state, and then we could decode back to the image or that bird's eye view representation or the action that we should take. And to imagine, to dream the future, we just unroll this and take the action, whichever action it decides to predict as the next step. And what's interesting about this is you can then unroll this multiple times and get diverse, different futures coming out. So, the top example, it decides that this world model decides that the traffic light is going to turn red, and the car stops there behind it. The bottom example, it decides that the traffic light stays green and the car drives through it. Here's an example where we're going to drive under the control policy, and the light's going to turn, and then it's going to pause. It's going to imagine going around that corner, which is what you see in the top right, and then it's going to go back and actually drive around that corner and complete the turn. And of course, just a few examples of this actually driving closed loop in Kala. But Fiery was supervised, and MILE only worked in simulation, or at least would need a lot of supervision if we were to take it onto into the real world. And I think the real question and the real opportunity here is to be able to build a world model that is built on real world data without supervision. So really and autoregressively predicting the next frame. So very, very much aligned with the concept of self-supervised learning and the foundation models that we're seeing in language, right? Language models predict the next token, and that is enough. So I'm going to give you a very, very brief sneak peek of some of the work we're doing here. And there'll be more coming in the coming weeks, so keep your eyes open. So first off, can we sample diverse futures? So we saw that example earlier where from the Mile paper. But now can we prompt this thing from a real driving scene that's the top bit, and then can we unroll the predictions into the future and see what happens? So let's click go. So the first little bit you can see was supervised, and then it was prompted, and now it's going to imagine making this right turn. And lo and behold, it completes the turn, and you end up on this high street. Let's do another sample. So exactly the same initial prompt. It's going to come up to this intersection. It's going to imagine making this turn, and lo and behold, it makes the turn, but it's a completely different street. Let's do it again. This time, it's going to imagine doing a left turn. So it comes up to the end here and makes a left turn. And what's really remarkable to me is that the objects are so permanent, and it's really learned a model of the dynamics and the street layouts, the objects that you see there, etc. Here's another example with a traffic light. So we're at a red traffic light here. Again, a short prompt of real data, and then it's now imagining, the light stays red and the traffic keeps crossing. And again, you've got this really interesting object permanence, which has come out completely unsupervised. Another example where again, it's just a sample, so it just predicts the light goes green, and lo and behold, we move through the intersection and onwards. And you can just let it drive, right? And so, this is just a slightly more extended clip where we're letting this thing drive along the road, and it's just imagining all of this. It's none of this was completely unprompted, and it has just sampled this entire world, this entire learned simulator, effectively, in which it can drive. Okay, so. Of course, we're not done. Can we control these through action, through language, etc.? And can we, of course, take these models and take them back onto the road and make sure that they improve our on-road driving? Okay. So I'm going to wrap up. Thank you all for listening. As I say at the beginning, autonomous driving is an embodied AI problem. And those underpinnings of AI that we've seen over the last few years are already starting to accelerate progress in autonomous driving and embodied intelligence, with huge, exciting avenues for further research ahead. Thank you.
Any questions for Jamie?
Thank you, I really like your presentation. I was just wondering, for real-life adoption of those systems, we need to somehow guarantee safety, right? That no one gets hurt or we don't damage the car itself. And I was just wondering, what are your views on the most promising techniques for embedding safety guarantees for learned controllers, like you presented? Thank you.
Yeah, so embedding safety guarantees, obviously there's some very, fundamental stuff that you do with safety, functional safety in particular. When it comes to safety of the learned system, it comes down to building confidence with yourself and with regulators and the public that this thing is going to drive safely. I would love to have guarantees that things are safe. I think in the practical realities of the world, you cannot guarantee everything is going to be safe all of the time. What you can do is thorough testing, really, good on-road testing, really good simulation testing, and really thorough and rigorous processes internally to make sure that things are doing what you expect them to do. I do think there's plenty of avenues for further work in that space, though, especially when it applies to end-to-end learning.
Thank you for the presentation. These unrolled videos look amazing. Video prediction is, future frame video prediction is quite an old topic, and they never look like that. So what did you get which makes it so good?
You'll have to watch this space on that one, I'm afraid. But we'll be talking about it more soon.
Thanks for the presentation. I was wondering whether if you ever tried to learn using dreaming, and if you ever compared the driving performance of learning on this mapping from real-world images to actions versus dreaming. Thank you.
Yeah, I mean I think that's one of the next big opportunities, and we're definitely exploring how to do that.
My last question.
So the dreaming is very interesting, but it's also as amazing as it is. I mean, things jitter and move and a bit dreamy, right? How do you check that you even hit something there, or like how traditionally with these image representations, if that's what you're trying to reconstruct, like you when you worry about the long tail, there are small things or things that almost never happen. How do you even get to dream about them so you solve them? How do you think about it?
Yeah, it's a good question. I don't know yet, and I think it's early stages in this. What I will say is we've seen some really, really interesting extrapolation of these things, driving in scenarios they've definitely never seen in training. So, for example, we can take that dreaming and direct it to drive into a wall. We've never done that in our training, because that's definitely not in our training corpus. It produces a relatively convincing answer. Now, that's not exactly answering your question, but it's indicative to me that these things are really very, very capable of understanding how the world works, and things like perspective and physics and things like that.
Thanks for your amazing presentation. So I have one question about the last generative video. So in the video, we can see the dynamic vehicles is inconsistent right, among sequential frames.
Yes.
So do you have any insight how to make the consistency among sequential frames?
Yes, but not that I'm sharing here yet. Sorry.
Let me change another question. So it's a basic, simple question that for the output of the end-to-end module. So for Wave, I see the output of your end-to-end network is a waypoint or trajectory that it has time information, and also why not go to the real and the control signal, the control commands? Why?
We explore with various different alternatives. Yeah, you could go fully to the end controller. For practical purposes, we don't usually do that, but that is I believe that there's a world where you do actually go all of that way to the end, but equally I think there's just so much a lot of the functional safety stuff goes into that last bit of the stack that it probably, and the benefits of going there are probably really quite marginal.
All right, let's send it to me again.
Thank you.